Good morning, everybody. So welcome to the Tuesday plenary. The first speaker we have today is Robert Beverly, who will be presenting remotely about geo-auditing RIR address registrations.
Okay, hi everyone. Go ahead and start. Going to take that as a yes. I hear my own echo. So hello everyone. My name is Rob Beverly. Some joint work with my pastor, and here to tell you about some of the work that we're doing geo-auditing RIR address registrations. So let me just start with a bit of background of the what and the why of this work. So as I think we all know, regional internet registries are the organizations that are responsible for receiving large chunks of contiguous IP address blocks from IANA, and then subsequently distributing those addresses. And today there's 5 RIRs, and those RIRs have regional responsibilities. So of course there's Aaron, APNIC, and today we're in the room with RIPE. And if we take a moment to look at some of the documentation that specifies the role of RIRs, there's a couple of documents that are of interest. The first is, of course, the ARIN Number Resources Policy Manual. This appears in some of the RIPE documentation and the NRO documentation as well, that says the primary role of RIRs is to manage and distribute public internet address space within their respective regions. RFC 7020 talks about the explicit goals of internet number registries, including being a body that can allocate resources. Of course, IP addresses are a finite resource and they must be unique. It talks about doing hierarchical allocation for efficiency and about operational needs. And the quote that's of interest here, that's in RFC 7020, talks about the core requirement is to maintain a registry of allocations to provide accurate registration information of those allocations in order to meet a variety of operational requirements. So a quick overview on our work, what I'm going to talk about this morning. We did the following. First of all, we examined IPv4 address registry information across all 5 of RIRs. Then we performed active latency-based IP geolocation of the allocated IPv4 prefixes in order to determine where physically these allocated prefixes were being used. We then developed a taxonomy of prefix registration geoconsistency. What we mean by this is we're comparing the physical location of the RIR service region to things like the registration info, to things like where it's physically located. And then finally, we use this taxonomy to complete an audit of the prefix registration consistency to understand how geoconsistent the registrations are across the different RIRs. So one of the first things that you're sitting in the room probably saying is, Rob, wait, what are you talking about? Out of region use is allowed. And so let me make a couple of things clear just at the offset. First of all, we're not looking at inter-RIR transfers. These things are publicly logged. Other people have done research on these. Of course, they're vetted by the RIRs. Instead, what we're looking for are instances of out of region use that can only be uncovered via measurement. Secondly, we adopt a rather conservative view of what we mean by out of region use. For instance, if the prefix is used out of region, one of the things we ask is it at least consistent with the registered organization's location? And of course, it's complicated, as with all things on the internet. Different RIRs have very different policies. So let's take a look at that quickly. Here's a quick snippet from the NRO Comparative Policy Overview that looks at some of the policies for the 5 RIRs. And you'll note that some of these vary quite a bit in how strict they are with respect to out of region use. So for instance, ARRN says to receive resources, ARRN requests organizations to verify that they plan on using resources within the ARRN region. AP-NIC is one of the more loose organizations, I would say, where they only require someone to have an actual account with AP-NIC, and they explicitly allow out of region use. They say they permit account holders located within the AP-NIC service region to use AP-NIC delegated resources out of region. RIPE's policy is the network that will be using the resources must have an active element located in the RIPE NCC service region, and AFRINIC is one of the most conservative, saying they require organizations or persons to be legally present and the infrastructure from which the services are originating must be located in AFRINIC's service region. So our motivation for doing this work was threefold. First of all, we wanted to increase transparency and help the community understand where this scarce resource was being used. Secondly, we wanted to quantify the extent to which the registry information is accurate and can serve the operational needs as specified in some of these RFCs. And then third, inform some of the ongoing discussions that have occurred recently about in-region address use and policy. And I throw up a couple of examples of this that have made some headlines recently within the media and across the various RIRs and different NOGs. I also want to talk about what this talk is not going to be about. And so we explicitly recognize that there's an economic value of IP addresses. And of course, there's a need for efficient and equitable use of IP addresses. And we also understand that there's sort of operational realities of the real world, things that are done just out of the various constraints that are in place or simply for expedience. So our goal is really to shed quantitative light on IP address registration consistency. We're not claiming to find policy violations, and we're not advocating for any policy changes. We're really just trying to quantify what's going on. Okay, so next let me talk about how we're doing this. But let me start with an example just to make sure everyone's on the same page. I think most of us have looked at some of the whois records, but here's an example of a record of a /24 that comes from a /8 that IANA has allocated to RIPE. This is an example where the registered owner is in Hong Kong, so they're outside of RIPE's region, and the question we ask is, where is this /24 physically? And there's a couple of different possibilities. First of all, it could be in RIPE's region physically, it could be in AP-NIC's region, or it could be in neither RIPE's region nor AP-NIC's region. Again, we're taking a very conservative view of what it means to be out of region. And so we say, okay, this means that it's consistent if it's in the RIPE region, it's consistent if it's in AP-NIC, but it would be called inconsistent by our taxonomy if it's in neither RIPE nor AP-NIC's region. So I want to just briefly talk about this taxonomy that we've established that essentially goes from being fully geoconsistent, where we have all of the different values for the RIR matching, to fully inconsistent. So what are these different values? So for a given prefix, we're comparing 3 different values. First of all, the RIR that's responsible for allocating the prefix. Secondly, the RIR that's responsible for the country of the registered organization. And then finally, this notion of doing geolocation to figure out where the prefix is, we figure out which IRR is responsible for the inferred physical geolocation of the prefix. So if all of these match, we call it fully geoconsistent. And if none of them match, i.e. they're all three are different, they would be fully inconsistent. And then we have a range of different consistencies in the middle. So how are we doing this? I'm going to go into each of these steps in a bit more detail, but let me give you the high level of what we're doing. First of all, we parse the bulk whois records from each of the RIRs, the base where we've extracted all of the relevant information. Secondly, we find responsive addresses that are within each of these prefixes using IP hit list. This will allow us to drive a probing logic. The probing logic is tied to ripe atlas, where we use it to select ripe atlas nodes that are within the country of the registered prefix, as well as ripe atlas nodes that are located on each continent to represent the different RIRs. All of these results that then get fed back into the database, where we then use an algorithm to identify the most likely continent that allows us to identify which RIR is actually responsible for the geolocation of this prefix, and then it gives us our per prefix RIR geoconsistency. So going through each of these steps in a bit more detail, the first part is to parse the bulk whois records. This is a bit of work because all the different RIRs, different schemas, have different idiosyncrasies, but we do pull all of this out and we do a bunch of munging to figure out which different records are tied to which different prefixes. Of course, we parse the prefix and the registered organization's mailing address, and we're careful to ignore certain records, things that are transferred or things that are non-managed records. Down in the lower right, here is an example of something you might see in the ripe data bulk whois database it actually specifies that it's in the ripe database, but it's not maintained or managed by ripe. So this first step in our methodology gives us these first two values of our taxonomy, the registered RIR and the RIR responsible for the organization that has registered the prefix. So just looking at that data before we do any of the actual measurements to find the geolocation, we can get some bulk whois stats on what's going on and how many of these prefixes actually belong to organizations that are out of region according to their mailing address. First of all, the number of prefixes that we look at in total from all of the whois, bulk whois, is approximately 8 million. So this is quite more granular than BGP, for instance. You'll see that out of all of these, in terms of the number of prefixes, the percent of prefixes that have an out of region owner, Aaron has 2.5%, Ripe has 0.8%, and Afrinic actually has the highest percent as a fraction of prefixes at 14.2%. If we look at where these are going, we can see that, for instance, most of the Aaron addresses that are registered to organizations outside of the Aaron region are in countries that belong to APNIC or RIPE, whereas Afrinic, most of the countries belong to APNIC and Aaron. And again, at this stage, I want to just emphasize this inter-RIR region registration is fairly common and in many cases may be explicitly allowed. So the second part of our methodology is to look at to find targets within each of these prefixes in order to do our geolocation and do our latency-based measurements. So we utilize a hit list of known or likely responsive IPv4 addresses, and then we use a longest prefix matching so that we match hit list addresses to the RIR prefix to which they belong. Of course, we're going to have to ignore prefixes without any responsive addresses. We're going to have to ignore any cast prefixes because that wouldn't make sense. For this work that I'm going to describe today, we randomly sample 10,000 non-anycast prefixes with responsive targets from each of the RIRs. So we take a total of 50,000 total prefixes for the measurements I'm going to talk about today. I want to take a quick diversion to thank the Atlas folks. Atlas is a huge and valuable resource to the community, and it's really been essential to our work and doing what you're hearing today. So some of the things that are really nice about it, first of all, it has extensive physical coverage, especially in country. This is critical because we really need the ability for some of these latency-based measurements to be in country. Otherwise, it really doesn't work the way we might want to, especially for poorly connected countries. It also has a very sane and usable RESTful API, and it also has very nice properties of being fair or findable, accessible, interoperable, and reusable. If you want to look at any of our measurement results, we've got them tagged with different values so that they're easy to find, and you can look at all of our measurements yourselves. So the third part of our methodology is to do this delay-based IP geolocation using RIPE Atlas. So we use a total of 20 RIPE Atlas nodes to send 3 ICMP probes to the target prefix addresses. We select Atlas nodes in the following way. We select 3 of them within each RIR. That's going to give us 15 total vantage points. And then we select 5 nodes within the registered country. There's some more details that are in a technical paper, but in essence, what's going to happen here is that the inferred geolocation is going to be the RIR that's responsible for whichever node is in an RIR region, returning the minimum round trip time. Of course, there's some limitations. So let's run through these quickly. First of all, we're selecting 10,000 prefixes at random from each RIR. The reason we did that in this initial work is that, of course, there's a drastically different numbers of prefixes in each RIR, and we wanted to get an equal number of prefixes for these measurements in each RIR so that we could do something comparative between each of the RIRs. Of course, there may be no ICMP responsive target in the prefix, in which case we can't do anything. That's why we're selecting randomly selecting 10,000 that have a responsive target in the prefix. It may be possible that there's no Atlas probes within the prefix's registered country, but that doesn't happen, at least for the prefixes that we consider, because RIPE Atlas, 43,000 nodes, 87% of all countries are actually covered. In terms of the geolocation, of course, the Atlas node itself may indicate the wrong physical location. To try to deal with this, we of course have multiple RIPE Atlas nodes, and then we also do a refinement round. And so what this means is that once we find an inconsistency, we do a second round using different Atlas nodes to try to verify that inconsistency. Again, the registration country may of course be a corporate headquarters that's located somewhere else, but remember, we're using this registered country as a second chance in essence to be consistent. All the work that we're doing would stand if we were only looking at the RIRs and the geolocation. And then of course, it could be the case that the prefixes themselves are inconsistent. I have a quick slide on that. That's something that we're looking at currently. Now, why are we doing latency-based geolocation? There's many reasons. The primary reason is that the latency-based geolocation, of course, relies on the physical signal propagation constraints, and it's hard to beat physics, especially when we have small RTTs. If we look at things like BGP and AS origin, of course, that can obscure the true location. If we were to look at IP geolocation databases, the problem with those is, of course, not only are they known to contain inaccuracies, but they often use the whois themselves. So this wouldn't make any sense to try to measure something that's already using whois when we're trying to validate whois itself. So to minimize error, again, we're using this latency-based geolocation, which is generally known to be accurate, especially at the continent and the country granularity. It's sound in proving geoconsistency, and again, if any geo-inconsistency is found, we select a new set of 20 nodes and repeat in this refinement round. All right, so let's talk about some of the fun stuff, the results. I like to start with a picture and actual walkthrough and example. So here's a fun case study. Here's a /16 that's registered within RIPE to a big CDN. And it has a corporate headquarters in the UK. So what's our system going to do? So the first thing that's going to do is it's going to select 5 Atlas nodes in the UK. When it did that, it turns out that it got a minimum RTT of 129 milliseconds, which, as you might know, is rather surprising to be in country of an RTT of 129 milliseconds. The system also selects nodes that are in the RIPE service region. So in this particular example, it selected some nodes that were in Germany and France and elsewhere. And of those, it actually had a minimum RTT that was even higher of 149 milliseconds. The Atlas nodes in Africa yielded a minimum RTT about a quarter of a second, so even higher. But then when it got to North America, we started getting lower RTTs. Indeed, the nodes in Canada started giving us 71 milliseconds. And as this refinement proceeded, it turns out that we were able to constrain it to a node in Phoenix, Arizona that had a 7 millisecond RTT. So in this particular example, this is an example of something that has a RIPE registered prefix. It has a RIPE organization because the CDN's headquarter address is registered in the UK, but it's actually physically located in Aaron's region, service region. So this would be, on our taxonomy, this would be an example of something that's registry geo-inconsistent. So here's our findings. Overall, so there's some really good news here. Overall, 96% of all the prefixes that we examined are fully consistent. So the really good news about that is that that implies that the things that are inconsistent may be possible to look at in more detail or to do some more manual investigation of what's going on, especially for these things that are fully geo-inconsistent. If we look across the different RIRs, it turns out that RIPE actually has the highest consistency with 98.1%, whereas AFRINIC has the lowest consistency, around 81.3%. AFRINIC has the largest fraction of inconsistencies, and these are dominated by prefixes that are physically located in Europe and in China. And if we look at what's going on in RIPE, the primary contributor to the fully inconsistent RIPE prefixes are prefixes that we geolocate to be in North America, so Canada, Mexico, and the United States. So I mentioned some of our current work. We're looking at intra-prefix inference consistency. I'll tell you about that in one moment. We're also extending this to IPv6 prefix registration auditing as we speak. We're also doing a bunch of analysis. So we're looking at correlations with the registration age, the prefix length, different status attributes. Some of this is actually quite difficult using the information that's available in the bulk WHOIS. And then looking at the ASs that are responsible for the most inconsistencies, and we're working with some of the RIRs for validation, and we would love to work with RIPE to do some validation as well. So here's an example of intra-prefix inference consistency. This was an example where we looked at 2 targets on the hit list that were within a single registered prefix. This prefix is a /20, and it's actually a large gaming provider. And here's an example where our 2 different measurements to 2 different prefixes inferred different regions. It inferred that the one target was actually in the RIPE service region, whereas the second target was in the Aaron service region. And when we actually look at this in some more detail, it turns out that this actually is explained by the fact that there's subnetting within the BGP. This is an example of a /20, a WHOIS record that's a /20 that's registered, but the BGP is actually subdividing this with different subnets. So our current measurements are actually taking this into account as well in order to separate these from the other prefixes that can't be explained by BGP. All right, so with that, the takeaways, first of all, the things that we want you to take away, different RIRs have very different out-of-region address use policies. But today, there's really limited visibility on where the resources are used, especially post-allocation. So some RIRs are able to do and do quite a bit of vetting once the resource is requested. but then don't have a ton of visibility after the resource has been allocated. And that's where some of our work is actually coming in. The IRR allocations are largely geo-consistent with some notable exceptions. Again, we see this as being a good thing because this implies that there's actually a small, most of the system is working really well. There's a small number of prefixes that are indeed very inconsistent that probably are worth looking into with some more detail. Third, geo-inconsistencies raise particular operational and security concerns that suggest the registration information should be updated or at least investigated. And then finally, the IRR WHOIS records are quite difficult to parse because of their inconsistent schemas. We're hoping that things like RDAP will hopefully fix this. So thanks. If you're interested in actually more detail about this, we have a paper on arXiv. Here's the link. We're hoping this is the first quantitative geo audit of our IP registry information. All of our data is open and public for transparency in RIPE Atlas. And again, we're doing future work and we're very interested in your feedback and or flames.
Thank you, Robert. We now have some time for questions. If you would like to come up to the mic, please remember to state your name and affiliation. Oh, here you go.
Hello, Sander Stefan, 6Connect and old address policy working group chair. Thanks for doing this research. It's really interesting. I'm actually surprised that RIPE and NP hit 98.1%. So I think congrats to the staff of those RARs. And yeah, I think taking into account the BGP stuff is going to be really important because 6Connect is a US company. We have a blog from Aaron, but we actually use the addresses for our US data centers, our Dutch data center, our Slovenian data center. We have a couple of prefixes for Anycast. So yeah, that we are one of those /20s that's spread all over the world. So yeah, cool. I'm really interested to see what's coming out of your next step of research. Thank you.
Awesome, thank you.
Good morning, Marco Schmidt, RIPE NCC. Yeah, also thank you so much, Robert, for this very interesting presentation. And actually, from the registry side, we also can confirm parts of it because we receive quite a lot of requests from companies that are based outside our region, and we were sometimes wondering, okay, what happened to those resources? And on that part, I want to extend, of course, our offer to help you with the validation because you mentioned that you're looking forward to that. And I have also one question. Did you already research what are the reasons for these inconsistencies, especially with Afrinic, and if or you have any idea to come to these reasons?
So we have, of course, in some regions it's quite politically sensitive. We have looked at what we think are some of the reasons, but we're trying to stay away from some of those political, aspects of it. So for example, we have looked at some of the ASs that contribute to most of the inconsistencies, things like that. But at this point, before we say anything more, we were really hoping to get some more validation from the RIRs. So that's wonderful, and we would be delighted to follow up with you.
Thank you.
Thank you, Marco. And we have an online question from Elvis Vilea from V4 Escrow. For the inconsistencies found, do you further look whether assignments are registered? That may explain, for example, an assignment of the /23.
Okay, so I'm not positive I understand the question. So maybe take that. Maybe best to take that offline. Of course, everything that we're looking at in our view is registered in the sense that it's in the WHOIS, and so it has a bona fide record. Of course, there's different kinds of records in there. So there's, provider independent or provider allocated, but we are looking at those different features of the records. But for what I presented today, we're not differentiating between those.
All right, thank you, Robert. Oh, Elvis is trying to speak. Let us give us one moment so we can try and put him online.
And I will
Elvis,
put my...
okay. I think we're going to take that one offline. Thank you so much, Robert. And all right. And next up, we have Massimo Candela and Sasha Romijn. They will be presenting on the present and future of IRRd.
Hello. Good morning, everybody. Thank you for the introduction. Also, thank you for being here in my city, finally. Here. My name is Massimo Candela. I'm a principal engineer at the Global IP Network of NTT. And today we will see the present and future of IRRd. IRRd stands for Internet Routing Registry Daemon. And Daemon because we are going to talk mostly about the software that is that basically is managing, it's running many, if not most, of the routing registries that you are familiar with. And together with me, there is Sasha Romijn. She will join me on stage in a bit. She is the developer and maintainer of this amazing software, and she will do the second part of this presentation. So briefly, what are we talking about? Well, routing registries, I'm pretty sure all of you know, essentially we can just say something like a extension of WIS that allows operators to exchange routing information like routing objects, routing policies, and this data set needs to be managed by offered by a software, and IRRd is the software that we are talking about, in particular IRRd version 4, and you can also see this logo with the this blue elephant, this educated blue elephant. And this software has the role of validating, cleaning, storing the data, and also provides several ways to query this data, and also several ways to import and do mirroring, including by using a protocol called NRTM. And about the ways to query this data and about NRTM, Sasha will tell you more in a few minutes. But let's start with a bit of the history of this software. So this was commissioned and funded by NTT in 2018, commissioned to Sasha. The reason why we did this was because we used to have a previous version of IRRd, but it was mostly maintained by NTT employees. But at some point, it reached the end of maintenance life, let's say like this, because it was really difficult to add new feature. It was an old piece of software, so we decided to just start from scratch, wipe it, and start with a new, more modern language, and go with a more flexible architecture and future-proof, and also have tests in the unit test to cover the code as much as possible. And also we decided that it has to be open source. In general, we love open source, we use it, we support it. We also produce like a open source, another open source software that I'm mostly talking often, that is, for example, BGP Alerter for BGP and RPKI monitoring. We are not new to the open source. One of the reasons why also we released it is because it was going to be more audited, more eyes looking on it, and bugs were going to be discovered sooner, but also because I think there is nothing quite like this, and possibly we were going to essentially improve the routing registry ecosystem. So later on, other organizations started requesting new features directly to Sasha and providing support. And I put the names. I hope I included all of them in this list. So now, who's using today this this software? So first of all, we are using that to run entity.com, and this was essentially the main reason why we did this. But also Reliably is using this, managed by Merit. So two of the largest routing registries, I would say private hosted routing registries. But there is also ARIN, LACNIC, and there is a conversation going on with APNIC as well. Plus, there are others. So you can already see that in addition to the two large entity and Reliably, there is also 2 and potentially 3 out of the 5 regional routing registries. So it's an important piece of software. That's why we care. So a few milestones. 2019, first release, feature parity and test coverage. And then 2020, more features, among which the first round of performance improvement. We will see why it's important. And then the RPKI aware mode, where essentially data in the routing registry that conflicts with RPKI is going to get suppressed. Then in 2021, GraphQL to query the data and other APIs to interact and create the data, and so on. More feature again in 2023, and again in 2023, 4.4. This is the latest version that came out like really recently, and the reason why we did that is, I mean, the main things that we achieved with this release is to have a more secure, to improve the security of this important software, and also again performances. Now, there is a total refactoring of authorization and authentication, but to understand what's going on, let me start from the basics. So in general, there are the various objects in the routing registry are managed by the maintainer, and so if there are various users in an organization that has access to edit this data, in general, they share a password of the maintainer. So this is a problem because it means that several users share the same password, so it's not really auditable. It's not a good approach. The second thing is that if one of these user goes crazy, can change the password and screw up with everybody else. And the third thing is if having authentication information directly in the maintainer object is also complicated for the application that has to manage this data, because it has to be careful on not outputting any of this data in any of the query. So in this refactoring, the entire authentication and authorization data is split in another data set. And each user has his own account, even if at the end it leads to the same maintainer. Each user authenticates with his own account. And in addition, there is the possibility for each user to have what we call here scope. So essentially, a user can be a full maintainer that can edit whatever objects, including the maintainer, or a bit below, which means like you can edit everything except the maintainer object. So for example, you cannot change any authentication data or whatever. So in addition to this, we introduced a new super user role that is mostly related to the organization that hosts the routing registry. We will see later some of the things that this super user can do. Two-factor authentication, API keys for programmatic access, so all the modern thing that we needed. And it's important to mention that migration from 4.3, so if you're migrating from 4.3 to 4.4, you don't have to really worry about any of this. Nothing is going to break, it's absolutely back compatible. And this enhanced security is opt-in, so you will have to essentially start a migration process, which is a few emails and links before you can. Otherwise, you can just keep using the old approach. Nothing is going to break. So the second, still in terms of security, a safer person, role, and maintainer data handling. Again, historically, so if you have a object that refers to, like, for example, has an admin towards a person object, and this person object at some point is removed, and the reference is essentially broken, points to nothing, somebody can go there and create again a person object with the same nick handles, and then claim that he basically is the admin. And even worse if somebody does with a maintainer. So already since version 4.0, there is a mitigation feature that says that you cannot delete any object like a person if there is still a reference coming in. So you have to first remove the references. This already since 4.0. However, this can happen anyway, and still happens. We verified this in the data, and this can happen because you are mirroring, importing data from other data sources, maybe old data or whatever, or also because this is something that needs occasionally to be done. For example, a person doesn't want to be in the registry and contacts the maintainer doesn't act on it, and so for privacy, GDPR, whatever, at some point the organization that hosts the routing registry gets contacted and they have to do something, and they can, and this is where the user, super user comes into effect, they can actually, the super user is the only one that can actually break the reference and essentially delete the object. Now, however, when the referring object gets the next update that somebody has to change something, that reference must be fixed. It doesn't allow to leave a broken reference for any update. And even more important, in nick handles and maintainers names cannot be ever reused inside the dataset. So we prevent this, and since version 4.4, not only based on the routing data already available, but also based on even if it's currently not referenced anymore, if it was generated, the name in the past is not going to be allowed to use, and this to prevent essentially that kind of squatting, let's say, of the reference that we were talking before. Now, performance, again, another performance. So when you do queries in routing registries, a lot of these queries are like hierarchical, are recursive, and this can impact the performance quite a bit. And there is now in this version a data structure that is pre-computed and stays in memory, that has bits and pieces of the data, and it's used to recompile, to provide an answer much faster compared to before to your queries, including complex reference like the one done by maintainers by ref. And this is, we measure it's 3 to 9 times faster, and I have an example here. So you can see at the top, so left is 4.3 and right is 4.4. There are 2 different queries, and you can see for the same query, the same first query goes from 8 seconds to 0.9, so quite a reduction. And the second one, again, is another of those nested recursive query, and it goes from 30 to 5 seconds. So overall, a great improvement in performance. Now, before giving the mic to Sasha, we are still, nothing is written on stones. We are brainstorming with her about the next possible steps for this IRRd software. And we would like to include support to integrate this with SSO solutions, for example, like Keycloak, another great open source project. This would allow organizations to essentially easily integrate this in their system already. For example, a routing registry like RIPE, for example, a regional routing registry, they can use their own SSO, for example. Or user would be able to use their PeeringDB as an identity provider and share basically the same account to log in. And we are also thinking even more performance improvement. So to shift those big queries from 5 seconds to possibly below 1 if we manage. So anyway, this is just, as I said, brainstorming. Please provide feedback if you want to provide guidance, you have feedback, or if you want to contribute. Remember, this is the link of the Git repo. And now I give the mic to Sasha. She's the real expert about this. And yeah, this is the clicker. I'm going to go down.
So I'm going to talk about a few specific features of IRRd because there's actually a lot more going on than just port 43, which is our most well-known feature. And so first, one of the things that distinguishes IRRd from, say, RIPE database is that we have a lot of different users, many for authoritative databases, all with their own policy. Entity has different ideas about their IRR than, say, RADB. And so one of the goals is to include features that suit everyone's different needs, but also remain compatible with everyone else's application of it, which can be an interesting challenge. And sometimes I've also implemented features reluctantly, such as AS.query support. If you weren't around 15 years ago, this was a way to write 4-byte AS numbers, killed about 15 years ago, but still used extensively enough that this was a migration blocker for a major registry. IRRd is also a very big project by now. There's 17,000 lines of code, 15,000 lines of tests. They make sure that people here still like me. There's a very low rate of bugs released to production and also extensive documentation. And one of the ways to look at complexity is all the data flows in IRRd. So there's a lot of ways that IRR data comes in. I will not go through all of them in detail. But there's authoritative mainly and various kinds of mirroring. There's different validation modes to deal with data that is a little less precise and valid, but maybe we can still work it out. But authoritative is very strict. There are, Massimo already mentioned RPKI, so there's RPKI filtering in IRRd, but you can also filter on scope set by the authoritative operator. You can do filtering that depends on the presence of other objects in other registries. So you can do very interesting things as a mirror suspension if you don't pay your bills in certain registries. And then there's a number of query mechanisms. And one I want to highlight is there's now also a WebSocket stream where you get continuous parsed data of everything that happens in your IRRd. I can go into any single one of these points for about an hour probably, but I will spare that and then I would not be allowed back. So I'm going to focus on some of the more widely interesting parts probably. So first of all, querying beyond plain TCP, because our most well-known interface is port 43. You connect to it, you run some obscurely formatted queries. There's no way, like, you have to read the docs to know how they work. And there's no authentication of any kind on this. There's a number of other issues with this. There's about 20, 25 different queries, limited flexibility, but also no verification who you're even connecting to or whether this data is from where you thought it was. So one may we introduced at some point is querying the same API over HTTPS, which has, of course, the benefits of having authentication. In the exact same query format, exact same input. That is, by the way, the URL of my home testing instance. So you can use it if you want, but it might die at any moment. And if you're too annoying, I will block you. But the most interesting one that we have now is GraphQL, which is not a widely known format. It's sort of like JSON, JSON-like, and it's an interface that allows you to explore the IRR more through individual fields and relations. So this is a query for all RPCL objects made by a certain maintainer. And one of the interesting things about it is that you get access to the parsed data that we have inside the database already, not just blocks of text. So the output you get is already processed into individual fields. So you don't have to deal with RPSL parsing, which has some very weird features that are not widely used, but sometimes. So you don't have to deal with all of that. The parser will just pick it up already. We already have all this metadata. You can even do things like explore related objects. So for certain objects that meet certain filters, look for all maintainer objects, then for all their admin sees, and then find if they have any addresses, and it will dig through the graph of IRR data. This has some scalability limitations currently. Those can be fixed, but they haven't yet. And also, especially to help deal with latency and HTTPS, which is of course larger, you can run a lot of unrelated queries in the same request and get the data back in bulk. There's some limit on scalability, but it stretches pretty far. And basically, there's also a little playground included where you can play around with it, see what fields are. It's a completely self-documented API, so it has defined fields, defined queries. But it's actually just not a very complex thing. It's just a little layer on top of HTTPS posts. There are client libraries that will help you and make it easier. But you can just do it with curl pretty easily, and it'll work. And basically, every time someone asks me like, oh, can I query this? Can I query that? How would that work? I just say GraphQL, because every time it's the answer is like, oh, just write this query, and then it's done, and you get structured JSON data. And every time, if you happen to know IRR Explorer, which I built for NLNOC, it's basically just a GraphQL front end. It's front end on top of IRRd GraphQL with some extra data from BGP. So this one is really nice. There's not a lot of public interfaces yet. You can, of course, run your own mirror. NTT is looking into opening up their HTTPS on their instance. Second, I want to talk about NRTM version 4. Massimo already mentioned there's mirroring and replication between IRRs. So we have about 1 or 2 dozen authoritative IRRs, and they mirror and replicate data from each other. One of the benefits being that you can query from a single source and get a mix of data. And some people also run local mirrors for performance. I don't know how many. And this is all based on NRTM version 3. And there was another RFC for routing policy system replication. No one actually uses this currently, so it's all NRTM version 3, which is not really a protocol. There's a website page. There's no integrity or authenticity check at all. So it's like it's querying plain text over port 43, but worse because this affects everyone who then later queries that source. So it's kind of a big deal that this data is authentic because we trust it. It's tied to whois to port 43, which also means it scales very poorly. You can't really scale it up to too many users. Part of the data is actually published on a dump, which is somewhere else on some HTTPS or FTP site. And you have to hope that the dump you retrieve and the source from which you then stream have the same data stream. Because if they don't, very strange things happen and you can't detect it. There's no consistent character set at all, so there's encoding glitches, and there's no error detection. There are just a ton of very interesting ways in which you can break your replication, and then I get emails about it, and the answer is like, yeah, you got to reset the whole thing. You can't detect this, you just got to do it every once in a while. So version 4 is a replacement for this, which I authored together with Job Snijders, Ed Strahan, and Stavros Konstantaris. And it draws the inspiration from IRDP being JSON-ish files on an HTTPS endpoint. And delivering files over HTTPS is something that I think is quite a solved problem by now. There are signatures and hashes for authenticity. So the transport is HTTPS, but also there's a path of a signature from the publishing IRD to the one parsing it, and also a single publication point. The object format of RPSL is notably out of scope. As the spec says, there isn't really any uniform standard of RPSL. There's just rough outlines, so this is left out of scope. We don't define what the objects look like. This is already a problem with NRTM v3 that we tend to work around with pretty well. How does it work? There's a small update notification file, which is sort of an index. It's very tiny. You can request it a lot. It can't be cached, and it refers to a snapshot, which is a large file, full dump of the whole database to start with. And then there's 1-minute batches of changes in delta files. Snapshots and deltas are immutable, so you can cache them very well. So the scalability of this is well, whatever infrastructure you can pay for, really. It's very easy and cheap to scale on commodity services or hardware. And the format is JSON, and snapshots and deltas are JSON sequences so that you don't have to load the whole thing into memory, as we discovered while trying to write implementations. And so the latency here is about 1 minute. Like every minute, you get a new set of changes by pulling the update notification file. The goal here is that we improve reliability, security, and scalability. So secure transport, secure end-to-end signature processing, scalability because downloading files over HTTPS is not a difficult problem. But especially also detection of errors, loss of synchronization. So if the source instance loses its history for some reason and can't produce Delta files anymore, it can restart and actually tell all the mirrors that I don't have a coherent history for you. You need to reload, which is currently not possible. You have to email people and hope you get all of them. Maybe more open access if it becomes more scalable. And of course, if you have your own NRTM implementation, who here has ever written code for NRTM v3? I did actually, but yeah, I figured. So status, RIPE-NC has a mirror server implementation in production on the RIPE database. IRRd has a mirror client in testing, and they work together. They've been streaming data. It's actually not a very difficult protocol. There's just a few details here and there to deal with some obscure things, but overall it's pretty straightforward, so it works. There are some still features to be implemented. Key rotation we haven't tested yet in interoperability, and also the other direction we haven't implemented yet. So RIPE-NC as a client, RIPE database as a client, and IRRd as a server, but we'll get there. The draft has been adopted by the Global Routing Operations Working Group. We just published a new version, and also I want to note that my work is supported by LACNIC and the RIPE-NC Community Projects Funds for NRTM versions 4. That is all we have for you. I think we have a little time for questions, but also if you have ideas or questions about related to IRRd, then feel free to find us at any time. I think we're both here all week. I think one of my wheels is a little squeaky, so I shouldn't be too hard to find. And thanks for listening.
Massimo, we have some time for questions if you want to come up to the mic, or if you're a remote participant, you can submit your question in the Q&A in mid-techo. Yes, Maria.
Maria, does it work? Yeah. Maria, developer of BERT. We are often telling users that they should, if they want to check their routes against the RRIs, the information from IRRs, that they should configure it as an RPKI thingy, loading it from RTR protocol from an RTR cache. My question is whether you were thinking about adding a support for producing RTR stream to make it possible to directly connect to these informations.
Oh, you mean to pull the RPKI data into IRRd?
No, the other way around.
Oh, to publish RTR data, to publish IRR records as RTR. I have never thought about this before, but I think it's interesting.
Thank you.
Hello, this is Harald Michel from Vienna University Computer Center. If I understood it correctly, you can mirror the data stored in all the 5 RIRs with this NTRM something. Do you have an idea how much data this is? So if I want to do this on my own, for example, how much data would I need to be able to mirror this, all 5 RIRs?
Do you know for your instance?
No, I also did not quite get the question.
The order is gigabytes, I think. Like the Postgres database, it's all Postgres behind IRRd. It's the order of gigabytes, definitely less than 15.
Okay.
It's not that big.
Thank you.
Most of the data is indexes actually to query.
Randy.
Randy Bush, Arcus and IIJ. I'm an old Unix user of I don't know how many years. Is there any feature you chose not to do?
Yes. Yeah, absolutely. So I looked, of course, at IRRd version 3 back then, and we also actually pulled a few 100,000 queries from NTT-Con and ran them through and compared them. And one that we intentionally did not implement at the time was email from authentication.
Darn. I used to run IRRd the current version has more dependencies than the overly attached girlfriend.
I always have the philosophy that I prefer not to write things myself if other people have already done it before me, and better, and with more maintenance behind them.
All right. There are no questions online, so thank you so much, Massimo and Sasha.
Thank you.
And I would introduce our next speaker, Raffaele Sommese. He will discuss how amassing country code top-level domains from public data is going.
So, hello everybody. I'm Raffaele Sommese. I'm a postdoctoral researcher at University of Twente. And today I'm going to talk to you about this work that I did in collaboration with my colleague Matthijs and Roland from University of Twente on how to learn country code second level domain from country code top level domains from public data. And before starting, let me say a special thanks to the RIPE Academic Cooperation Initiative to let me be here today. It's a great initiative where academics can participate to RIPE meetings. So thanks for this initiative and thanks for letting me be here today. So let me introduce this topic. Why we want to learn domain names. The web is basically a vast and intricate network. And as academics, we studied the web a lot. Also, industry studied the web a lot. And we studied from a lot of different perspectives. We studied from a technical perspective, we studied from an economical perspective, and we studied it from a policy perspective. one is from list or top list of domain names. And to explain you why we want to learn domain names at the University of Twente, let me explain you what we do in our OpenIntel project. So our OpenIntel journey to domain names. OpenIntel is a research-oriented, large-scale DNS management platform that measures around 65% of the global second-level domain namespace every day. So every day we measure more than 252 million domain names. And since 2015, we collected 9.1 trillion data points about the DNS. And out of these, we get out more than 60 papers in collaboration with other academic institutions and industry too. So our goal is to be the long-term memory of the DNS ecosystem. It's to answer that question like, how the DNS looked like 10 years ago? What that domain was pointing to 10 years ago? So this kind of question, it's the question that we are trying to answer with our platform. And to do this, to measure the domain name ecosystem every day, we rely on this list of domain names. So from where we get this list of domain names? The first source of domain names, it's for sure the public top list. So there is this list, the former Alexa top 1 million that now is retired, the Cisco umbrella, the Franco, the Cloudflare radar. These are top lists. These lists represent the domain that are most queried on the internet. And they have like a lot of definition of how they are the most queried one. They, for example, Cloudflare and Cisco uses the fact that they run an open resolver. So they collect the data from their open resolver and they look to the popular domain name. There is Franco that use a different approach. So all these domains have like a way to identify the top 1 million domain as they consider so. But what's the problem? 1 million domain represent just the 0.25% of the global DNS second level domain namespace. So we have a really biased view. We have just a view of the nichest part of the domain name population. And this is basically, these are great because they are public, but these are, it's just, we are telling the story of the internet by telling the story of the richest part of the internet. Like we are telling the story of the richest part of the population, saying that we are telling the story of the entire world. We are sure biased if you just use this domain name. So the second source that we use for feeding our list, our measurement, is the so-called open TLDs, in this case, open CCTLDs. There are several CCTLDs that expose their zone to zone transfer. So you can effectively run an AXFR against this zone and get the full zone out. And these are Switzerland, Estonia, Liechtenstein, Niue, and Sweden. And here, listen to me carefully, I meant intentional AXFR because there are some CCTLDs and some GTLDs that misconfigure their zone and you can do IXFR, but we are not measuring them because these people are not publicly saying that they are sharing their zone, so we don't want trouble in that. And there are other top-level domains. For example, they share through open data, so they have like a catalog on the website. You can download the file every day, and you can download the list of domain name every day. It's the case of French and Slovakia. And these are great. These are fully representative of the internet landscape of a country, and they are public. And for us, it's really important that this data is public because the things that we learn in a public way is the things that we can share back with the research community and with the industry. And I put here hic sunt dragones, that basically it's the Latin definition where the word "and" in all the Middle Age, because this is really the boundaries of our data sharing. All the measurement data that we feed from public sources, we can openly share to all the community. And you can go to this website and basically download our measurement data that we measure every day and get the measurement data for these sources. Then we start to the data for which we need to sign a sort of agreement. And the first one, it's ICANN CZDS. When ICANN introduced the set of new GTLDs, so the .xyz, .amsterdam, .tokyo, .whatever, they decided that to prevent abuse and to prevent malicious registration, operators of these GTLDs should start to share their zone file to people that make requests for. So they create this platform that is the centralized zone data service, where people can register, can put their personal information, and can request access to this zone. And this is great, but this data that you can get is not reshareable. So you get for yourself, you get for your own organization, but you cannot reshare to the party. So again, as the example that I made before, this is data that we measure, but unless the person that comes to us has the same agreement with ICANN, has the same access to the portal of CISPA, we cannot reshare the data with them. And the next one, the fourth one, it's the NDA CCTLDs, or the beers CCTLDs, how I usually call them. Because while for CISPA, it's easy, you just create an account, you go there, and somehow they approve your access. It's not the end of the world. You don't need to provide a lot of data. Obtaining domain lists for non-open CCTLDs, it's a complex task. And sometimes it involves negotiation, sometimes it involves restrictive contracts. You need to go through NDA. Sometimes it involves beers because you need to have a direct contact with people. You need to know people to get access to this zone. And in this way, we managed to get access to 13 CCTLDs. What's the problem? Is that all these contracts that we got are under NDA, hence they are not reshareable. And then there is from now on, it's a bit of joke side, the no way CCTLDs, where, for example, we have Germany that say 999 privacy. Sorry, Peter, if he's in the audience. And the most funny one was the Italian one, register.it, where we ask the access for the zone and say, yeah, in principle, we can give you access for the zone. There is just one minor requirement. We should ask all the Italian domain owner to grant us the approval to give you access for the zone. That, I mean, if you know Mazzoni novel, this is the executive boogie lawyer. It seems like when the executive boogie lawyers start trying to stop Renzo from filing a case against Don Rodrigo. So it's exactly that. It's the Italian bureaucracy as finest, I would argue. So, and then there is we should share CCTLDs. When the European Union created the .au regulation, so the regulation for creating the .au CCTLDs, they said that the .au should share information, should share basically the content of the zone of the data that they collect with public and private body of the European Union that works in cybersecurity and information security. Now I will argue, we are a university, we are a public body of the European Union, we work in cybersecurity, we didn't get access to .au. So to recap, what is the problem? The problem is that barriers in data sharing hurts the research community because we cannot perform our job. We cannot let other researchers to use our data that are really precious for a lot of work when researchers want to join, for example, different data sets together. And the other problem is that if we just look to GTLDs, the web extends beyond GTLDs. There are a lot of interesting element in country code top level domain that represent a significant portion of a country internet landscape. And all this lack of transparency in our internet measurement, in our internet research, leads to an underrepresentation of CCTLDs, leads to an underrepresentation of the global and regional web ecosystem. And on the other side, I understand the point of view of CCTLD. CCTLD says they are not subject to ICANN policy that say, yeah, you should share the zone on CISPA. We mandate you to share the zone on CISPA. They are subject to the local policy. They are subject to their government policy. So they have privacy concern, they have liability concern. And on top of that, GDPR really messed up the stuff because some people think that domain names are personally identifiable information and they cannot share this information because of GDPR. So that boy was our last hope. I'm a stubborn person, so I think that there is another hope. And the other hope is, let's look on the web. Let's see if there is other sources of domain name. And if we look if there are other sources of domain name, we can find two large sources of domain name, two substantial sources of domain name that are certificate transparency log and common crawl data. So the main question here is how these sources are representative of the CCTLD landscape. How much we can tell of the CCTLD landscape just looking to these two sources. So what we did is that we start to collect these data sources. We start to collect certificate transparency data since 2017. We start to collect common crawl data, all of them. And CT logs, for the one of you that doesn't know what it is, it's basically a mechanism for which every CA that is operating and want to be recognized by modern browsers need to report every certificate is issued through them. So every certificate, X509 certificate is issued nowadays on the internet is reported to certificate transparency log. So it's a large source of domain name, I would argue. And common crawl instead is basically a crawling of large-scale crawling of web data. So we consolidate this data set, we amass this data set, and our methodology lies on the fact that we cross this data set with the ground truth. And you may argue, what's your ground truth? I mean, you don't have ccTLDs. I mean, we don't have ccTLDs, but we have some of them. So we have 19 over around 300 that are out of there. And 12 ccTLDs, as I said before, were obtained through NDA agreement, and 7 of them are public. The ccTLDs are in this word cloud, basically. And our data set goes from 2018 to 2023. That means that we can do a nice longitudinal analysis. And the nice result that we found is that half of the zone of ccTLDs that we have are already public. And the coverage that we can see from public sources already span from 33 to 80% in 2023. And this coverage is increasing because more and more people are adopting TLS, more and more people are registering certificate for domain name, so we can learn more domain name from certificate transparency log. And the certificate went from 37% in 2018 on average to 59% in 2023 on average. And this, if you think about, already negates the privacy and the PII concern that some ccTLD has, because this information are already there, already on the public internet. And to show you really the powerful of this way of collecting domain names, I want to put your attention on one specific ccTLD. That is .ru. With the current situation nowadays, probably .ru is one of the most challenging ccTLDs to get access to. But with public sources, we can learn 70% of the domains that are in .ru. So if we break down the contribution from CT logs and common crawl, as I said, on average, we have 59% of coverage for the ccTLD that we have access to. And if we look to, it's 24% of the domain names appears both in common crawl and in CT logs, 28% just in CT logs, and 7% just in common crawl. And I'm saying this because common crawl is a source that appears every 2 weeks instead CT logs is a continuous source. But still there is value in amassing data, amassing domain names from this source because we had a nice 7% to our coverage. And the other thing that we saw is that basically this coverage by common crawl is decreasing over time, but not because common crawl is scanning less over time, but because certificate adoption is increasing. So the number of domains that shows up in certificate transparency log is increasing. Now, you may think, okay, you can know domain names, but you can know domain names like who knows how late after they are registered. The truth is that we are pretty quick if we look to certificate transparency log. We did this analysis for one ccTLD that was .Slovakia, for which we have the data, and we found that nearly 60% of newly registered domain name appear in CT logs in the first 24 hours, and in the first 5 days, the 80% appears. That means that CT logs can also provide us timely data about newly registered domain name. So it's not just data about historical registered domain name, but we can learn also something that's just been registered. Now, the sample that we had is pretty small, 19 over 300, I agree. Scientifically doesn't sound like that huge sample. However, we had the GTLDs that we can collect through ICANN-CZDS. So let's try to generalize this result by looking at GTLDs. Let's see how much of the coverage we get through GTLDs by looking at public sources. And surprising things, we get similar number. The ranges goes from 38 to 80%. The average percentage is more or less the same. And in general, this proves our argument that looking at public sources, you can already have a substantial coverage across different top-level domains. But what's the part that we don't see? what's in that 40% of domain name that we don't see. And on the 40%, our initial hypothesis was that, okay, these domains are not used, for example, for web purposes. These domains are just registered and just let lying there around, or use it, for example, for mail or some other purposes. The truth is that not really the case. I mean, we saw that domain name showing up on city logs and common crawl sure have a larger web adoption. They have like 91% of open web port, but also in the other part, we have 70.5%. So it's still, they are still used for web. They are for sure not used for HTTPS because, I mean, the larger percentage of HTTPS deployment we have more for city logs and common crawl. But assuming that they are not used for web, yeah, it's not a great assumption. So our appeal to register with this data that we collected, and register in particular of closed zone, is that they should really consider to open their zone. They should discuss what are the challenges in open the zone, what are the legal challenges in open the zone. There are security concerns, sure. For example, if you want to prevent abusive registration of newly registered domain names, someone trying to sneak a similar name to a popular one that has just been registered, something like that. But this can be solved by introducing a delay, by publishing the zone several days later. This still works. And if there are legal concerns, I argue that these things should be discussed at European level on how we can handle this data sharing, how we can really handle data sharing for cybersecurity. And I think on this, NIS2, the new directive of European Union, is really going in this direction. It's really going in this direction of we need more data sharing to do cybersecurity. So to conclude my presentation, with city logs and common crawl, you can see more than 50% of closed ccTLDs domains. And in the project, in Open Intel project, one thing that we will surely do very quickly, I mean, we are working on that right now, is try to measure this domain name and share this domain name back with the community and make more measurement data available to the community because the community really needs them. And we hope that this result can spark a discussion with ccTLDs for more transparency and data sharing efforts. So with this, I thank you for your attention, and I'm sorry for the technical inconvenience, and I'm open to get your question on data sharing. Thanks a lot.
Thank you, Raffaele. A big round of applause for him. And we have a couple minutes for questions, so please go ahead.
Hi, Marco Davis, SIDN. Thank you, Raffaele, for this presentation. Maybe a little bit off topic, but I have a question nevertheless. Have you ever considered looking at Web3 domains, such as Ethereum and all the other ones, to include them in your data set?
We never actually measured them. We consider at a certain point, we never investigate how we should integrate that in our measurement platform.
Jim Reed, freelance consultant and random member of the RIPE community. I think your ideas about trying to get ccTLDs to become more open is a nice idea in theory, but in practice, it's not really going to work because lots of ccTLDs are subject to national laws and locally developed policies. And even though they're talking about things like privacy considerations, there are other considerations too. I know that many of these ccTLDs assert compilation copyright over the registry database, and the TLD zone file is therefore an instance of that compilation copyright, and they have to protect that. If they make the zone file available to anybody, they lose that intellectual property they have, which in some cases the only thing that the registry really does have is an asset. So it's very difficult to change that kind of mindset when that's the local policy. And I think it's all very well for you to say, well, ccTLDs should do this, the CCC to do that. But what I hear from that is pretty much the same as the argument we'll be having in ICANN for a long, long, long time over WHOIS. The people say all WHOIS data must be published, and then other people say, no, it can't because we've got these privacy considerations and GDPR considerations and all the rest of it. So I think if you try to open up this date, you'll just have a screaming match between two groups of people with a whole fundamentally mutually exclusive positions, and there'll be no hope of a compromise. So I think that what you really should try to do, in my view, is figure out other ways to harvest the data that you're trying to get through, for example, this thing you're talking with the certificates. Another suggestion might be to try to get data from some of the open resolver services, the all4 services, but again, that might not be considered public from your point of view and therefore invalid. But I think those are the approaches I think you should take rather than tell CCTLDs, here's how you should run your business, because frankly, that's never going to get anywhere.
Yeah, thanks for the comment. Regarding public resolver, I mean, passive DNS data, there are some providers claims to have like 97% coverage over the entire global DNS space. The problem there again is that these data are not public, so we cannot reuse it. And I agree with your argument that some CCTLDs may have also economic incentives in not sharing their zone. There are CCTLDs that provide service, for example, for trademark protection out of their service. However, I think there's still a way in which they can share that zone. If they share a few days later, for example, if the service that is sold for trademark protection is in immediate site, that may still work.
Morning, Sebastian Castro, Registry. A couple of observations. One is you're missing one category on your slides, which is lawyers got in the way.
Yes, definitely.
Yeah, when you have sort of the handshake agreement, it's like, oh yeah, we'll give you the zone, and then gets messy because lawyers. But the other thing is, so I predict that you're from public sources, you only get to 85% coverage, because there is a sort of underlying 15% of domains are registered, but they're never activated. So their DNS doesn't work, their web doesn't work, email doesn't work. So they won't show up in any public source. And it's for portfolio domainers, portfolio building, and intellectual property protection.
Yeah, I agree with you. There are actually some domain names that never shows up also in zones because they don't publish NS records. To which extent they are relevant to the academic community, I would argue that very little. So we are not really interested into that. But if we can get a good coverage, that's an interesting perspective still.
All right, that concludes the questions. Oh, we have a few online. Sorry about that. Dmitry Serbilov, I didn't understand why we need an open domain registry to help spammers.
I didn't got the question. Oh, you mean if someone starts to crawl the zone and see, for example, there are new domains and start to send spam of that new domain? Again, they can learn in other ways. They can learn using other data sources, for example, this one. And my argument is also that the benefit towards the academic community, I mean, the benefit that we can provide to the DNS ecosystem in studying the resilience, the stability, the adoption of protocol like DNSSEC, how this protocol implement, how this protocol are stable, goes beyond these challenges of helping basically spammers.
Thank you. Next question is from Elvis Villela, B for Escrow. Have you thought about opening a public DNS server and providing it as free service with the conditions that you will use the data?
Not really.
Okay, and the last one from Vadim Mikhailov from cctld.ru. By what principle were 19 ccTLDs selected? I see 3 ccTLDs from Russian region, but I'm not seeing many of EU in the slide with graphical result.
Oh, they came out from agreement that we had in the past. So that's again one-to-one agreement that we had in the past with ccTLDs, and we get access to the zone in the past to these ccTLDs. So we don't really have like a re-choose of which ccTLD we can have access to. It's mostly someone grant access to these ccTLDs, and we we managed to do this analysis.
Okay, thank you. And that concludes the questions.
Thanks
Thank you so much, Raffaele, for the patience. And thank you to the ops team for the quick recovery. They only took a few minutes, so thank you so much for that. We now are going to head over to the coffee break and be back for more content at 11 a.m.
Thanks.
Yeah, great recovery, man.
Okay. Good morning, folks. Hope you've all been reinvigorated by your coffee. And we have installed additional breakers and a small nuclear power plant outside the room to hopefully have a nice, smooth session. I'm Brian, and along with Antonio, we'll be chairing this session. So 3 very interesting talks. Get the opening slide up there just as well, would be useful. There we go, excellent. So first up, we have Christian Petrasch from DE-CIX talking about building a big data platform with open source.
Yeah. Good morning, ladies and gentlemen. Thanks for having me. My name is Christian Petrasch. I'm product owner of Service Insights of DE-CIX, and I want you to bring you to our journey for big data platform. At first, let's talk about why we want to do that. We want to provide our customers and especially our smaller customers a tool where they have insights in their ports, deeper insights in their ports. A lot of them are blind because they are too small to have own services or telemetry metrics at their company. And we also want to be technical state of the art, and have the observability possibilities we have at that point of time. And at the end, yeah, it's a good idea to have better possibilities to do network planning, capacity planning, and so on. And for sure, as the metric is showing you, in the last 5 years, traffic is increasing, it doubles. So we have to do something faster as the old one. The first challenges we figured out was that we have more or less a 5 GB a second load of data, which consists of 300,000 packets a second of flow data, of IP-fixed data, which is coming from our routers, our edge routers of the DE-CIX platform, and 10,000 values a minute, which consists of the telemetry data, which is the statistics of port counter, error counter, discards, and so on. And doing analysis and enrichment and big data stuff with that amount of data is a challenge. So we invented a 3-step solution: data ingestion and storage, front end, and enrichment. And for that, we went on the shopping trip, and it should be fun, we heard. And the first step was getting a data house and a data lake. And for data house, there are a lot of companies relying on Kafka. Kafka is wide scalable, it's fast, so it looks like a good idea. And for data storage, we mentioned about the last RIPE meetings where Cloudflare is doing some talks about ClickHouse, and a lot of people are using ClickHouse, so it's a really fast database, and it fits perfectly together with Kafka, so we choose ClickHouse. So we have our IXP platform, and the data is coming in. We need some collector miracle. I will come to that later. And then we put the stuff to Kafka and ClickHouse. So next step was at which tool we are using for the collector. And at that point, there are more or less two big players on the market, it's GoFlow and PMX. And we had a look to the transport formats. At first, we used JSON, but JSON is the JSON packets are very big, and this means that it's slow parsing. And so that was the first lesson we learned. It's too slow for that big amount of IPFix data. So we thought about, oh, binary formats could be nice. So the battle of binary formats starts, and we had a look to protobuf and Afro, and more or less protobuf wins because in a later step we knew that we want to use Rust, and the implementation of Afro and Rust was at that point not really well. So we said, oh cool, let's use protobuf. And at that point, only GoFlow 2 was able to use protobuf. And at that point, thanks for developing and supporting that, Louis. He's at the right meeting if somebody wants to talk with him. Ah, here it is. Here he is. And yeah, for example, we had a finding that our platform consists of Nokia routers, and Nokia has a different template. So an IPFix template. So we had to change something in cooperation with Louis, and that was really fast. Really appreciated. So, yeah, our platform is running at the cloud, but my journey is not, you have to run that on the cloud if you want to do that. It's possible wherever you want to run it. But we run it at the cloud, and we thought, oh, cool, let's run GoFlow at the cloud, and we tried that, and we sent our IPFix packets. And I said, okay, wow, we are losing around 75%. Why? And after some investigations, we saw, okay, the network of the cloud provider has a maximum MTU of 1400 bytes. That is complicated because a typical IPFix packet has 1460 bytes. So it is UDP fragmented. And because of the fragment SMAC attack, the cloud providers or our cloud provider says, okay, we are dropping unsorted fragmented UDP, which means 75% or more of our IPFix packets are dropped. Damn. So at that point, Nokia people, if they are in the room, maybe it could be a good idea to have a configuration option to have for the MTU size of the IPFix export. So our second lesson learned was we have to run the GoFlow collector on premise. The next step of the three solution journey was to search for a nice front end to present the visualizations, the data in visualizations. We had a look to Grafana, we had a look to Superset, all the typical players on the market. At the end, we chose Superset because Superset has a really nice embedding framework where you can embed your metrics as an iframe in your homepage without the need of a separate login. So it's creating a guest token, and then it creates an iframe in your homepage with the login of your homepage of your user. At that point of time, Grafana can't provide that. So we said, oh, cool, superset. And on the left side, you can see how superset graphs can look like. It's in our portal, but it doesn't matter in which website or the superset graphs at the normal superset page are looking like that. So we had Kafka ingest, ClickHouse, and the dashboard request coming via superset from our customers or from the people who wants to look like. So after that point, at that point, we start to cook with the data. And first step of cooking was the enrichment of the data. So flow data, we started with the flow data, has no real combination to the business data of your choice, or in our case of our customers. So we want to enrich the data with additional data to get better metrics. So we had a look what ClickHouse is providing, and ClickHouse is providing a techniques, it's known, it's dictionaries. It's really fast because it's tables in memory, and you can combine that with a lot of sources, with other databases, with APIs, and everything what you like, because you can program a web API if you like. We did that to have an API to our database. And you have the possibility to automatically renew that data after several hours, seconds, what you want. So that was the next step for the enrichment. But now we figured out we had a large pile of data, 300,000 records a second. And we said, okay, we can't store that in a raw granularity. So we said, okay, 5 minutes, 1 hour, and 6 hours granularity. We put them in buckets and do aggregation. And at that point, a technique came in discussion, which is called materialized views. But at first, what is a materialized view? It's a database technique. And a materialized view is more or less a permanent running query, which is looking for insert triggers of a table, which is configured for. And it's a little bit like iNotify for Linux. It's really fast, and you can combine data or manipulate data, join data. So it looks really promising. But I want to mention that it never knows the data itself. It only knows that insert triggers. Remember that? Because now our exploding or our bomb begins. We configured that. We said, okay, great. We have an enrichment materialized view. We have another materialized view for aggregation. Stack that together, and then we switched on replication for data redundancy. And at that point, our load was tremendously. The queries were slow, and nobody knows what really happens. But after some investigations, also with ClickHouse support, we figured out that stack materialized views with a high database ingest load is not a good idea. On the other hand, we had the problem that our aggregation, our 5-minute buckets, we started with 5 minutes, this was strange, because in that 5 minutes buckets, there was not the data you are expecting. Sometimes it was more than 5 minutes, sometimes it was less, so it was strange. And the reason is because the materialized view only knows that insert trigger, and it only ingests data if a inside ClickHouse bucket size is full. So you never will have the typical 5-minute bucket you're expecting. So yeah, what to do? And we airflow to the rescue. So airflow is from the Apache tool stack, and it is more or less a scheduler, a graphical user interface scheduler, which can catch up jobs. You can see what is failing. You have dependent jobs. So you can write everything as Python, as Bash. So it's really, really powerful. And so batch processing was a better idea to have a better control. And we did it. You can see that is a screenshot of a typical Airflow job with dependencies. And after getting the aggregation under control, one of the last steps was, yeah, we have to take care about GDPR. We have to anonymize it. And the anonymization we combined with our Flux tool. Flux is a proprietary tool. It was the algorithm was presented at RIPE84 from our research team lead Matthias Wichtelhuber. He's also here if you want to talk with him. And it's written in Rust. It's doing the DDoS mitigation and the anonymization. We anonymize the last octet. And then it writes the data to the ClickHouse database. And it's with Rust, it's very fast. But that maybe it's the anonymization part is open source somewhere. And last step was to implement telemetry. Implement telemetry was more or less get the data from the telemetry and use the stack we developed. And then we thought, oh, it's a lot of stuff. And then we wrote a filter, a telemetry filter. It's just a Python script where we filter out the relevant data and put it to our database. So we have everything together. And that is the final cluster structure. We got the data from the IXPs. We put it via GoFlow or directly to Kafka. Then we have the telemetry filter docking to Kafka and this Flux DDoS anonymization tool. And then we write the raw data to ClickHouse and doing some enrichment and aggregation and provide it via superset to the users of the data. And that is how it can look like, even at your side as well. It's superset only. You have plugins. You have a lot of metric possibilities, like it's known from typical big data systems. It's really, really nice. So I can suggest it. And what insights we have, it's something the most people, I guess, want to see. It's metrics about ingress, egress, metrics about top talkers, and ports, pie charts, and so on. And we also created for DDoS traffic a chart which also consists on pie charts. And for a product we have, it's a Cloud Router product. Yeah, I'm happy to ask questions, to answer questions if you have some.
Okay, thank you very much. Do we have any questions? We do, please.
Hi there. Thank you very much for your talk. This is very relevant to what I do for a living. I'm Tom Hill. I work for British Telecom.
Hi.
I was curious where you were using GNMI to export streaming telemetry. Which models, Yang models, presumably, are you utilizing?
Yeah, the Yang models we are using as the one Nokia is providing, and at Nokia you have that prefixes for the statistics, you have that for the VPLS, for the services itself. with that young models we are using. Is that answering your question a little bit?
It does. I mean, I'd refer to them as the proprietary.
Yes, it's more or less the ones you can have from Nokia, and there is a Nokia GNMI module for Python, which can subscribe on the channel.
Sure. I mean, so is a follow-up question is, have you considered providing telemetry streams to your connected members?
Not yet. Yeah.
Okay, thanks.
No problem.
Go on the back again, please.
Rens Kloek speaking from Delta Fiber from the Netherlands. This is a very nice presentation. I'm doing currently a project implementing Nokia routers, and I still had something open about how I would do streaming telemetry. So I'm interested in your project. Two questions. You mentioned some enrichment API. What kind of data you enrich your telemetry data? And second question, do you plan to release parts or the whole project at GitHub?
At the first question, for the first question, we are enriching more or less the business data of our customers to the telemetry and to the flow data. So everything what we have, and with that embedding framework solution, we have a row limit securities that you are only see the data of your own data. For the second question, I'm not sure. I have to talk with my boss.
Okay. It would be very nice if you could release a part or the whole part of it.
I think the biggest issue we have with that is at the moment that we are only 2 people inventing that, and we have to. I think we will have problems to support that at GitHub.
Yeah. Okay. Thank you.
No problem.
Please.
Sure.
Michael Richardson, Sandelman. I worked on a bunch of graphy-like things with data, mostly from DNS servers. And one of the problems I had was that in order to have a set of test data big enough to do things like your 5-minute thing, that sounds exactly what I was fighting 10 years ago, kind of thing with MongoDB. Don't ask. But the problem I had was that to get enough data to actually replicate it, I would then have too much data, too much personal data in the thing, and I did not feel confident in the anonymization of that, such that I could actually make those into test cases that I could actually put on GitHub or something. And I'm wondering if you're dealing with that, or where are you with that?
Yeah, we for the anonymization, we have the last octet of the IP addresses, and for all other data, we are fine with that to put that in the database. So we are allowed to do that.
But would you be fine with it being as a regression test in a public repo? No, yeah, that's
probably not.
Conflict. Yeah, that's the conflict that I had. It's
probably
so you
not.
say to the person who submits a patch, and you say, "Did you run the 10 gig test data through it?" And they're like, "What 10 gig test case? Oh, the one that I can't give you."
Yeah.
Right.
Yeah.
So I think we have this over and over again with big data and PII, and it's like we need a alternate internet with, I don't know, all the octets above 256 or something, and you know.
Yeah, you're right. I guess a worldwide solution would be really appreciated for that problem.
Please.
Maria, developer of BERT. I'd like to ask whether you are thinking about using the data basically online, feeding back into the platform and stopping the DDoSes you have found right away.
No, not yet. What you can have is if you're a user or customer of our platform, you can have a look to that, and you see it. And if you see the DDoS, and you can see, for example, also the protocol and the rule which fits to detect that, then you can do a IS prepend and switch on black holing, which you can do. That is the only possibility at the moment. Maybe later at some point, but not yet.
Thank you.
No problem.
Okay, I don't.
So if you want to come in touch or want to have a little demo, it's a coffee break, feel free. I'm happy to do that. Thank you.
Cool, thank you very much. Don't steal the clicker. Okay, thank you very much. So up next, we have Jayasree Sengupta, who will be talking about too many windows. Who'll be talking about evaluating DNS resiliency with truncation, fragmentation, and DoTCP. Is that how we're pronouncing it? Fallback. Please, thank you. There we go. Okay, cool. Yeah.
This one, right? Yeah. So hello and welcome everyone. So my today's talk is about evaluating DNS resiliency and responsiveness with truncation, fragmentation, and DoTCP fallback. So the main authors couldn't be here today to speak, so I'm talking on behalf of themselves, and I would do my best. So yeah, so we begin. Yeah, so this is, though everybody here probably already knows it, but this is just a general overview of the stuffs so as to get us into the topic. So we all know that today, mostly on the internet, we are using the UDP because of its latency, because that it is pretty much faster in terms of latency, but there are also certain other issues with it, like because of the size, it is not able to always catch up with the DNS responses, and hence this might at some point of time create troubles such as leading to truncation and fragmentation, and also in certain cases when truncation happens, it may also lead to DoTCP fallback. And as we know that on the DNS flag day of 2020, it was said that in order to cope up with these challenges, it is better that we have buffer size of 1232 bytes, which is recommended as the standard buffer size these days. Therefore, the experiment that we conducted was actually to find out that how is the failure rate of both DOUDP and DOTCP in the current internet traffic that we have across the globe, and to also test that what kind of buffer sizes are currently in use in the global traffic of the internet today. So this is what that leads us to our major motivation, and that I already spoke about, that that the current payload size of DOUDP, as we all know, is 512 bytes, and which might lead to truncation, which is not the case of DOTCP. And also with the introduction of this extension of the DNS mechanism, that is the eDNS buffer sizes, this can be somewhat dealt with, and we are also trying to find out whether the DNS traffic today is trying to follow the DNS flag day recommendation or not. So this takes us into the major research questions that we try to focus here in this talk. So the major research questions are: how resilient is DOTCP and DOUDP over both the IPv4 and IPv6 address space? And what is the scale of the usage and performance of both of these protocols in general, again, both over IPv4 and IPv6? And also the last question is, what is the buffer size that is currently in use? And so we will go ahead with the findings and through the talk and find out what we see. So yeah, to talk about the methodology here. So we have used the RIPE Atlas probes, and the experiments have been conducted with the RIPE Atlas probes that are deployed all over the world. And we have mainly used the version 3 and the version 4 probes, the latest ones. And these probes are are at least supporting the IPv4 and IPv6, either of them or both. So we actually worked on this 2527 globally distributed RIPE Atlas probes, whose density is somewhat like this, which is more dense in the European region and North America, and the rest have very less density. So the figure on the right side actually shows our major experimental setup. So what we try to do is we try to analyze this performance both from the edge and the core of the network. So we have captured the interactions between the resolvers and the DNS client on the edge, and on the core side we try to capture the interactions between the resolver and the authoritative NSS, and yeah, so that's how it is. And we do it for both the probe and the public resolvers. And so we try to, yeah, we'll just go to the next slide. Yeah, so from the for the evaluation from the edge, what we try to do is we try to use the cached DNS requests, and for both the resolvers, and this is the experiment is performed over the course of 1 week with 10 blocks every day and 10 requests per block per resolver. So, so this is the heat map, which actually tries to show. So the heat map that's on the top, it actually tries to show the DoTCP failure rates over all the over the public resolvers and probe resolvers and across continents as well as autonomous systems. So we have actually used the 10 most popular public resolvers, and the heat map on the bottom is actually trying to compare the performance of DoTCP versus DoUDP for the same set of experiments. So the major thing that we observe here is that for the public resolvers, we see that DoTCP has lesser failure rates compared to DoUDP, whereas for the probe resolvers, the picture is pretty much the opposite, where we see that DoUDP actually performs way better, and it's almost like 74%, approximately 74% better than the DoTCP. And when we look at these values across the continents, we also see the similar trend. However, there are quite some exceptions to this. So if you look at Komodo from Asia and Oceania, we do see that for all these cases, DoUDP, so DoTCP actually performs worse compared to DoUDP. But in general, the first one is, so in general, the normal conclusion is that DoTCP performs better. So from the edge, we also try to analyze the eDNS buffer sizes that are currently in use. And we see that 4 out of the 10 resolvers that we have tested actually follow the DNS flag day recommendation of using the 1232 bytes of buffer size, whereas 4 other resolvers, they actually use 4 other resolvers, that is the Komodo and Newstar and OpenDNS and OpenNIC, they actually use the larger buffer sizes of 4096 bytes, which might also lead to the problem of fragmentation. And the general observation is that for IPv4 and IPv6, the difference in the buffer sizes is generally very low, except for Quad 9. And for Quad 9, we see that for approximately 24% of IPv4 cases, there is it doesn't at all use any eDNS options, which is pretty interesting to note. So yeah, so then we actually move into the next set of experiments which we do from the core of the network, and here we actually try to analyze both for the 2 KB and 4 KB response sizes, and the experimental setup is still the same, where we perform it over the course of 1 week, 10 blocks every day, and 10 requests per block per resolver. So we have the same set of experiments here as well. So we have this DoTCP performance on the top, whereas the comparison between the DoTCP and the DO-UDP performance on the bottom. So here we also kind of see the similar trends. That is, we see that in case of public resolvers, DoTCP actually performs better when compared to DO-UDP. That is, the failure rates of DO-UDP are more. But if we try to analyze these results with the results that we had seen in the previous slides, that is for the experimentation from the edge, we see that the failure rates from the core are actually more than the failure rates from the edge. And this is true for both DO-TCP and DO-UDP cases. Similarly, when we look for the probe resolvers, we kind of see the results to be synonymous as to what we had seen in the earlier slides. That is, even here, the DO-UDP actually performs better than DO-TCP, and it is way ahead of DO-TCP as well. And even here, we have some of the exceptions where we again see Komodo expressing the same kind of results as it was in the previous case as well for the experimentation from the edge. And there are also some interesting results, such as when we look into Asia, especially, we see that there are pretty much high failure rates at for certain of the resolvers and not just Komodo, so which is also interesting to note. And also similar results we see for Oceania. And when we actually try to look into the autonomous systems, we also see that we have this kind of higher failure rates for ASs like DTAG and also Comcast and also Vodanet. So yeah. So we kind of do the same experiment of looking into the eDNS buffer sizes from the core as well. So here we see that 3 out of the 10 resolvers show larger buffer sizes, like 4096 bytes. For example, we see this for Komodo again, and Newstar, and also Yandex, which is the newer one, which was not showing the larger buffer sizes when we were looking at from the edge of the network. And we also find that 4 out of 10 resolvers, they actually follow the recommendation of the DNS flag day. And resolvers in general over here, they try to exhibit preferred buffer sizes for more than for more than 95 majorly 95% of the cases, but at least for over 90% of the cases. Yeah. So next, we also try to see that what are the other eDNS options that are being offered, and what is the percentage of these offerings in the current DNS traffic. So we see that there are, apart from eDNS 0, we also have the eDNS client subnet, which is the ECS option, and also the eDNS cookie option. So if we look into the data, we find that that Google actually offers ECS option, and also uncensored DNS actually offers the cookie option. But in general, if we look at all resolvers, we see that for more than 99% of the cases, eDNS 0 is being offered by these resolvers. And also, if we look at IPv4 versus the IPv6, then we see there is a smaller difference in the usage rates between the two. And Yeah, that's pretty much sums it up. And this also pretty much ends my talk here. So we will look at the key takeaways, but for the IPv6 results, it's there in the papers. I did not want to bore everybody more with the IPv6 results, but in general, the IPv6 results pretty much follow the similar trends as we have seen in the IPv4 results here. So overall, summing it up, we see that the failure rates of DO-UDP is greater than DO-TCP over both IPv4 and IPv6. And it's also true for both the cases, that is when we evaluate from the edge as well as when we evaluate from the core. And as we have already seen, that 3 out of 10 resolvers in case of the core and 4 out of 10 resolvers in case of the edge, they actually show larger buffer sizes, which might potentially cause fragmentation issues, and the resolvers in general exhibit their preferred buffer sizes for greater than 95% of the cases for both the part of the experimentation. And I would like to say that we tried out with DO-UDP and DO-TCP here because that is the most widely available traffic in the internet these days. But with DOQ coming up pretty much in the traffic, we would also like to look at the DOQ traffic at some other point of time in stage. And I would also like to say that we do have interesting DOQ work coming up, which again, I'm presenting right after lunch. Yeah, so that pretty much sums it up, and I'm open for questions.
Okay, thank you very much. And we have a question.
Yeah, Linkova, Google. I was slightly surprised to see difference in V4 and V6 behavior, and that made me thinking in many networks, well, in some networks, when you talk to, let's say, 8888, you're actually talking to an ISP intercepting your traffic and serving it from their servers. I'm wondering if you actually checked if you were getting responses from Google or like some other DNSs you tested, or was it some man in the ISP in the middle?
No, so far, so we only checked for Google from the edge and not for others. I guess that was your question.
No, like I'm saying, you do not really know if it was 8888 responding, right? Or it was your ISP intercepting your 8888 traffic and pretending to be 8888.
Okay, well, so I have to actually get back to the main authors. Like... Yeah, I'll get back to you.
Any other questions, folks? In which case, no. Thank you very much. Thanks. Yeah. So I do wonder, just with my anti-abuse hat on sometimes, about how much of an entire conference you could get malware through a QR code on a slide. It's one of those interesting ideas, which none of you should ever do, obviously. So moving on to our third speaker of the session, we have Jen Linkova from Google talking about turning IPv4 off in the enterprise network.
Hello. Okay, on. Can you hear me, right? Okay, hello. I'm Jen. I hope your laptops are successfully low on power so I can get your undivided attention now. Great. So I'm going to talk about things which even I considered impossible a few years ago. And I'm going to prove they are possible now. So it's basically talk about unicorns. It's a talk about turning IPv4 off in an enterprise network, Google Enterprise Network. It's a kind of continuation of the presentation I gave like 2-3 years ago when we've tried it for the first time. So, first of all, why? Why would any reasonable human being would try to disable IPv4? First of all, because we actually run out of address space. We run out of private address space, which is much worse. You cannot buy it really, not enough. And shocking content, when you deploy dual stack, it does not solve your problem. If you deploy dual stack, you still need IPv4 everywhere, and you're still running out. So the only way was to start turning off IPv4 in one places and use it in some other places. And also, I am hands-on person, and I hate dual stack. It's nightmare to operate, right? You have basically two protocols, failure scenarios, unpredictable, much harder to troubleshoot. So why bother? Let's try to get rid of the legacy protocol. Who cares, right? What kind of network we are talking about? We have a large corporate network, a lot of sites, let's say 4-digit number, and every site, like everywhere, we are not using DHCP v6 for address assignment, only for prefix delegation, and I'll talk about it. So basically, we assign addresses through Slack. Well, servers have static stuff, but again, this talk is focusing on offices, like places when people come with their laptops or have their desktops. It's not about DCs. It's not about like management part. It's like endpoints, desktop, laptops, phones. So yeah, they're using Slack. Every site has a device which does NAT 6.4, basically the same device which does NAT 4.4. And to access v4 only destinations, we obviously have to deploy NAT 6.4 and DNS 6.4. So yeah, we're doing NAT 6.4 in the edge. And in router advertisements, we provide hosts with DNS 6.4 addresses and with Pref 6.4. So hosts know which Pref 6.4 we are using for NAT, which is well-known prefix, actually. We have a centralized DHCP v4 infrastructure, and you'll see why it's important. And also wired ports, they all have .1x enabled, and we put devices into different VLANs, like a lot of them based on authentication results. So previously, you might remember, I gave a talk about the day I broke all the treadmills, because when we tried it for the first time, we wanted to do a proof of concept. And for proof of concept, we selected the largest Wi-Fi network we have, the guest network. And we turned off IPv4 for Google Guest Wi-Fi and for wired guest. And we created dedicated IPv4 enabled SSID instead, because we knew there are going to be some use cases for IPv4. We did it back in 2020. We did reclaim a lot of address space, which was very good. Management was happy, deploy people were happy because we were able to reuse that address space. But, well, it kind of worked, right? But we found out that having a dedicated v6 only network segment and dual stack network segment is not a good idea. It's very confusing for users because users come to on-site, see different SSID, pick up the random one. As a result, they sometimes connect to dual stack SSID, even if the device can actually work perfectly fine on v6 only. For example, some phones, which work actually very well on v6 only, can still connect to dual stack. And they would consume my precious IPv4 addresses. It leads to high v4 consumption. And also, I do not have any visibility to problems. Why people join dual stack network? Is it just random choice? Or it's because something does not work, something I might be able to fix? Nobody tells me anything, right? Also, multiple SSIDs, Wi-Fi team hates it. And I realized that for wired network, I would not be able to do this. We have so many VLANs. If I start doubling number of VLANs for .1x, it would be like operational nightmare. So we wanted something better. What if, instead of doing dual stack and v6 only, we're going to do what I like to call IPv6 mostly? What if we can let devices coexist on the same network segment, and some of them can be v6 only, like new devices, which I know can operate in v6 only mode, and some devices, like old devices, would be still dual stack. How can we do this? Let's say a client can signal v6 only capability and say, hey, I can be v6 only if this network supports this. If it's just a legacy network which only has v4 or dual stack, fine, I can be dual stack. But if this network supports v6 only or v6 mostly mode, I am happy to be without v4 address. As a result, these devices can move between different networks and operate in the mode which the network expects them to. Because yeah, I was considering, can I just turn off IPv4 for corporate devices, but then as long as users go outside to public or like Starbucks Wi-Fi, everything would get broken, right? So how did we do that? We wrote RFC 8925, or you probably heard about this, especially if you attended tutorial on Monday, option 108. So we decided that the best way to turn off IPv4 is to use DHCP v4. Because if you have v4 network, you probably have DHCP v4. So how it works? In DHCP Discover, the client includes the option 108, which basically indicates the client capability to be v6 only. So if DHCP server is not aware of that option, let's say like normal Starbucks network, nothing would happen, right? The normal DHCP v4 process would complete, everything works fine. If that device connects to my enterprise network, and it connects to the network segment which I already have converted to v6 mostly mode, then my DHCP server say, oh, for this network segment, I will return your option 108, which means shut up. Don't do DHCP v4 for a specified period of time, by default 5 minutes, be v6 only. And again, it only gonna happen for clients which support this. So for example, if you take some, I don't know, very old network device, nothing gonna happen, that device will get v4 as before. So now I can have two types of devices in my network and only some of them gonna get IPv4. So what do we mean when I say device can operate in IPv6 only mode? It's a kind of very vague definition, right? For some devices I know because I tested. My laptop been sitting on v6 only network for like 5 years, but I only use browsers and SSH. So for me, it's like everything works. But some people, you know, they playing some games and that stuff for some reason breaks and they're unhappy. Well, so practically, the only way you can say that device is capable of operating in v6 only mode if you know that the device runs 464X LAT. Because mobile operators, they are way ahead of us in the game, right? They've been deploying v6 only network for a long time. Why? Because most of mobile phones run 464X LAT, which means they run a special translation daemon on the device. And that daemon provides IPv4 address and IPv4 default route to applications. So if applications cannot operate without v4, what happens on v6 only network application? Oh my God, I don't have v4 address. I can't connect to v4. Go away. I'm not working. 464X LAT tricks it and like, yeah, here is the v4 address. Here is the default route. And CLAT layer on the device translates the traffic from v4 to v6 and sends it over v6 only network as a v6 packet. And then it's translated by NAT64 device at the edge as normal. So yeah, that stuff works on mobile phones. And it also works on your MacBooks if you have something, if you have macOS 13 or newer. Obviously, it probably means that if your device can operate even without DNS64, strictly speaking, right? Which is also good for DNSSEC. I know there are DNS people in the room. You should love this. So for me, practically, it means that I want devices which run 464X LAT to send option 108. And obviously, yeah, I can manually opt in some devices without 464X LAT if I want to. So project scope, what we actually did. We were disabling, we were migrating our network to v6 mostly, and the scope was all user-facing Wi-Fi and wired network infrastructure all across the globe. So all our offices, well, most of them. There are a few which I did not touch because they're very old. But basically, yeah, I want to cover the vast majority of user-facing VLANs. So devices in scope, all devices which you can send option 108. Currently, Android, iOS, and macOS, they send option 108 unconditionally. You just turn them on, option 108. They detect pref64, either by receiving NAT64 prefix and router advertisement or by using DNS lookup of IPv4 only name. And they enable 464X LAT and everything works. I also have selected Linux and Chrome OS devices as opt-in pilot when users can enable option 108 selectively and try it and disable it if they don't like it. But Mac OS and phones, they all like automatically opt-in, no opt-out mechanism. So how long did it take? We are currently at 90% of rolling out. I mean, 90% of all network segments. I'm counting VLANs where this is enabled. Fingers crossed, 100% will be reached next week when I'm back from RIPE. So we started with doing like extended pilot, first in 3 locations. Like I started in Sydney where I was. Then we extended it for 1 month in 5 big offices. And then we flip the switch and say, okay, from now on, all new offices are turned on with option 108 by default, as a v6 mostly mode. And we started doing brownfield, retrofitting existing sites. And it's basically took us 4 months to do this. Yeah, so I started in March, and we really started in May doing the large brownfield rollout. So results, can't believe it. Fingers crossed, nothing wooden here, surprisingly well. So no real like showstoppers found. We found a few cosmetic issues. We found a few bugs in macOS, and thanks Apple. Apple been amazing. They've been fixing those bugs I'm reporting. So I would say Sonoma currently just works fine. Like we did find some issues for which we had to implement workarounds, and I can talk about this for hours. All right, but I only have like half an hour, so my apologies. I'm not gonna cover all war stories and funny cases we found. I have some backup slides so you can take a look at them. Maybe I have time for them, we'll see. So yeah, we were able to do this. Well, 90% done. I hate reporting stuff which is not 100% done, but sorry, we should have right meeting 1 week later. So yeah, average utilization drop, like 3-4 times on average network. There are a few networks which did not show much utilization drop, probably because there are a lot of Windows devices or Chrome OS devices there, but in average, I basically expect to downsize most of the subnets between like 2 and 8 times subnet size reduction. Yeah, so we basically start reclaiming address space and estimation at about like 300,000 addresses to be reclaimed by the end of the year. So this is not really a typical network because here is a really significant utilization drop. So you can see like it was, what was that like? Almost 40% utilization before, and it's /19. It's a really large office Wi-Fi network. So, and obviously I would not be able to downsize this because if I just make it /20, it will be 80% utilization, much higher than acceptable threshold. So after we did that, you see it dropped below 5%. So I just downsized it to /22, got 7K addresses back instantly. I'm very satisfied. So lessons learned. The most important lessons learned is that the only way to do this, like you can get much further with a good word and a gun than just with good word itself. So until you actually in a danger of running out of address space, nothing happens. I've been working on this for I don't know how long. We launched Google public DNS-CIX for what it was, 2015, 2014, because we needed that for this project, right? But until we ran out in like 2019, it never was a priority. Now it's like very important thing. Lesson number 1 is that I got a lot of surprises, right? 10 years ago, I was very unsatisfied with the quality of v6 in the network, but then I spent significant amount of time making it better. And I had a false sense of security. I was thinking, we've been operating v6 for so many years. My v6 network is perfect. It works as well as IPv4. Oh my God, how many things I found. Thanks to happy eyeballs, right? Nobody, like you do not have a proper visibility to v6 issue while you have a safety net of IPv4. For example, like UV6 would mostly work, mostly like 98% of the time. Who would notice if your workstation or laptop, when it wakes up after sleep, would lose a DNS configuration for, well, until the next array comes. Maybe seconds, maybe minutes. Nobody would notice it as long as you have v4. But when you turn off IPv4, oh, that's all fun started. And again, users do not report the issue. And all those issues on endpoints are really hard to detect and test, right? Because sometimes it's a race condition, sometimes it depends on what users do, right? So it's not something I can easily test. And as a result, when you have v4, nobody reports anything, nothing gets fixed. So yeah, so if you think your network is like v6 ready, well, you might reconsider. So, some discoveries we made. If something looks like a host, behaves like a host, is it actually a host? Yeah, I was thinking so, right? People put some devices in the network, like some box with some screen name maybe, and it gets a IPv4 address over DHCP, gets IPv6 address over Slack, and then actually we discovered that when we did v6 only guess, so it wasn't option 108 yet. We found out that it's actually a router. Might be a router, might be something inside. I actually had to take a screwdriver, open that box, and found the OpenWRT box inside, a tablet, and a few other things connected. And for me, it was a host, right? No. And as soon as I took away IPv4 from that thing, right, everything got broken because this device cannot extend the network anymore, right? It was using NAT for IPv4, but it was not able to extend v6 connectivity downstream. Well, obviously we can use 464X LAT here, but is it a good thing? Do I really want all these tethered systems to stay v4 forever? No, we actually want IPv6 there. So what we are doing, we using DHCP prefix delegation to give prefixes to endpoints. It was some discussion at IETF. It's not strictly speaking a host anymore, right? It's a router. The line between host and a router is now so blurred. Like my phone, is it a host or a router? Strictly speaking, it's a router because I have my laptop tethered to it. Chrome OS, and I'm going to talk about it later, right? Have like 5, 7 VMs inside. Is it a host or a router? Tricky question, right? So let's say a node. Something which looks like a host, okay. So, I have so much time. We can talk about this more. Good. Yeah, so this is a slide which actually summarizes 1 hour talk I gave at IETF. Yeah, so we could talk. I have some backup slides. Yeah, so first of all, surprisingly, the biggest issue we discovered, biggest in terms of number of support tickets open, was people, oh my God, I came to the office and I cannot connect to Google Wi-Fi anymore. Why? Because they had IPv6 disabled on their laptops. Why they had IPv6 disabled? Because for years, support people were saying, you have a problem, right? Did you try to disable IPv6? Oh, it helped. Ticket closed, problem solved. I asked many times how exactly we are going to re-enable that thing back. Nobody cared. Well, until we suddenly stopped providing IPv4. So yeah, so we had to like use a script to go to every single corporate device and re-enable IPv6 just to make sure it stays enabled. So fragment extension headers, so I love extension headers. They are actually used. I know some people think they don't, but they are. There are 2 very useful extension headers in the wild. One of them is fragmentation. Okay, let me find supporting slides for this. Yes, so fragmentations, obviously. For end users, it mostly DNS and some other UDP applications like Mosh, for example. If you're using Mosh, you might get unpleasantly surprised if you block in fragment headers. ESP header, it's actually IPsec, right? Which means VPNs and Wi-Fi calling, right? Wi-Fi calling. Your phone actually established IPsec tunnel to a voice gateway. And if you're using IPv6, right, you need to remember that you need to permit not just TCP, UDP, ICMP, but also ESP headers. Yeah, we found some actually funny issues on some platforms. Some NAT64 devices were really happy doing NAT64 unless IPv4 packet was coming with 0 UDP checksum, which is perfectly fine in IPv4. Well, some NAT64 devices start putting some garbage inside, which made endpoints very unhappy. So some other devices decided that, yeah, I'm a stateful firewall indeed, but when I'm permitting outgoing ESP traffic, I'm not going to create any state for return flow, because for state, I need port numbers. No port numbers for ESP, so no, just drop it on the floor. Well, that was easy to fix. Fortunately, it was just an explicit rule, but still. Yeah, fragmentations. Surprise, surprise, IPv6 header is 20 bytes longer than IPv4. So inevitably, if your NAT64 device receives a 1500 bytes from internet and the F bit is set to 0, NAT64 device will fragment it. Well, unless you have more than 1500 MTU in your V6 infrastructure, but I know that some endpoints don't really like getting packets of bigger than 1500. So yeah, so what's gonna happen? Your NAT64 will create 2 packets fragmented with fragment headers. And by the way, some devices are not even using 1500 as a packet size. They're using 1280 as a default fragmentation size in this case. Fortunately, it's configurable. But again, it's something I was not aware until people started to complain about some packets disappearing in the wild. And again, like for endpoints, as I say, it's UDP applications. If you start using V6 for network infrastructure, radios becoming a problem, right? Because radios as DNS wants to get an answer in one packet. And if you start using certificates for .1x, well, packet will be definitely bigger than you can fit into MTU. Okay, yeah, I talk about this. Let's go back to summary slide. So yeah, talk about NAT64. Oh yeah, this one probably deserves much longer discussion. So I start getting complaints that Chrome OS devices having connectivity issue and kind of strange connectivity issue. It's not like nothing works, which is normally easy to troubleshoot. Some applications losing connectivity from time to time. What happened is, as I say, Chrome OS, it's actually a very complicated thing. Inside, it runs a lot of virtual machines, namespaces, a lot of them. And each of them obviously get an IPv6 address, more than one sometimes. So you can easily see your Chrome OS laptop using Chromebook, using like 10 or even 20 IPv6 addresses at the same time. Wireless devices are trying to be very, very helpful. They're trying to do neighbor discovery proxy. They're trying to respond on behalf of other devices. And for this, they keep in a table which client has using which IPv6 addresses. Size of the table might unpleasantly surprise you. Some vendors use like magic number 7 and after, oh, you've seen more than 7 addresses on a device? And okay, I've seen 20. And this is actually, and the problem is, right, troubleshooting this is a nightmare because when n+1 address appears, it just fails to install it into the table. So everything works except this one address. Troubleshooting that stuff was fun, really, right? And again, then some addresses disappears from the table, that problematic address started to work, and some other addresses falling off the network. So job security, I was very busy for a while, yes. Obviously, and also, let's say you have a VXLAN infrastructure, which probably means every address is a route. Now you suddenly have 20 times more routes in your routing table than you planned. And this now translates to money because it's completely different hardware now. So kind of doesn't scale very well, right? People start complaining about that IPv6 thing because it's very expensive. So, and this is actually a very similar problem to one I had on the slide before about device extending connectivity behind itself. So what we're trying to do, and there is a work in progress, is to start delegating prefixes via DHCP-PD to such devices. So instead of maintaining a huge route neighbor discovery cache and wireless table, which has 10 or 20 or 30 addresses per device, we only need to maintain a single route and a single entry for device link local address, which now scales linearly to the number of devices I have. Okay, another interesting issue. Where is Jan? I know he loves renumbering case. She's not here, disappointing. So, renumbering case, you probably heard about that, right? For ISP environment, your CP reboots, gets another prefix via PD, your devices did not realize that prefix changed, and now you have old prefix and new prefix, and only one of them works. Surprisingly, we have the similar problem in the enterprise. Okay, let me go to my backup slides for this. Yes, so .1x. A desktop boots up, gets into, let's say, machine VLAN, right? Gets an address from blue machine VLAN A. Then a user comes to the office, logs in, .1x authentication happens, device moves to another VLAN, gets an address from another VLAN, the old address stays, right? Theoretically, indeed, the machine must be smart enough and realize that when .1x reauthentication happens, you need to do something with your network stack. I had this exact discussion with Microsoft support back in 2001 for IPv4. For IPv6, it's still the same. Network manager is total nightmare in this case. So basically, in half of the cases, what happens, right? You basically have two subnets on your interface, two addresses, and only one of them really works. However, there is a solution for this. Because again, this is a case which we never noticed until we got v4 off. There is a RFC for detecting network attachment, which says like, if your device disconnects and reconnects, for example, Wi-Fi network, like layer 2 roaming, devices are kind of trying to do the right thing. Am I still on the same network? Do I need to completely refresh my network stack, or am I still fine using the old address? The first thing they all do, they check if my default router changed. If my link local and MAC address of my default router is still the same. Theoretically, after that, they still need to get a router advertisement and compare prefixes, but it's not all of them do that. So basically, a lot of devices kind of realize that when your layer 3 network changes, your router changes as well. However, if you use VRRP, your MAC address is always depends on your group ID. And any reason to have more than one group ID? I'm just using the same number everywhere, right? Why would I have different numbers? And actually not so many of them, strictly speaking, it's just 256. Some devices also violates RFC and generates virtual link local address from its MAC address, which means that every network segment which uses the same VRRP ID will have the same link local address and the same MAC address everywhere. Well, never been a problem, right? Until another renumbering case appears. I have two buildings, two different subnets, but they are too close to each other. When you walk from one building to another, you actually move between two subnets. But again, the same VRRP ID everywhere, same link local, same MAC address. Device like, I'm definitely on the same SSID, same layer 3 network. I'm keeping old network config. As a result, nothing works, right? No connectivity. Yeah, people start complaining. What can we do? Oh, there is a solution, actually. Default address selection, RFC, says that when you select it, you have multiple addresses. It's fundamental thing in IPv6, right? If you have multiple addresses, you need to select which one to use. And there is one of the 8 rules says that if you have multiple routers and each router advertises you its own prefix, and you selected a router, please use the source address from the prefix advertised by that router. Makes sense for multi-homing, right? I have two ISPs, for example, right? I always want to send a traffic to ISP A from source address from ISP A address space. Mars people shall agree, right? So if host implements this, then all your renumbering cases are very easily solved. You're basically making sure that if you get a new prefix from a router, it should be different router. which means as long as every VLAN in my network has its own link local address. Basically, yeah, it sounds crazy, right? Globally unique link local addresses. Well, I don't know. I can probably make them city unique, but why bother, right? I just make them globally unique. What I'm doing in my network, because it's easy, I'm just using global/64 prefix as an interface ID for the IRRd. Very easy to code, one line of code change. Works like a charm, I can tell you. So many people are now happy. So yeah, and I think it basically applies for CPE case as well, right? So as long as your link local address is a function of your prefixes, and by the way, Rule 5.5, supported by Jan, you are late. I was talking about renumbering cases. I'm not going to repeat it. So Rule 5.5, been supported by Microsoft for a long time. macOS supports this. And I know there is a work in progress for Linux, so we might actually get most operating system covered. So what other issues have we discovered? Going back to my favorite slide, 1 hour slide. So by the way, until recently, macOS was doing very funny thing. It was using 464 slot address, special one, and consider it to be a normal address because it's assigned on the interface, and it was sending MDNS packets from that source. Well, it freaked out some wireless devices because like, oh my God, it's a spoofed address, definitely, it's a bad client, I'll just block it and you're not getting on my network. It also makes VXLAN networks very, very, very unhappy because they see the given IPv4 address start moving between all ports in the network at the same time. CPU goes up to sky. Operational people are also unhappy. So basically, strictly speaking, the only issue you would probably see now is a cosmetic issue with traceroute, if you do traceroute from your MacBooks. And by the way, this network is using the same approach. So most of your MacBooks are probably V6 only right now. You probably would not see anything in traceroute, but this is work in progress. But besides that, yeah, so make this happen. We had to publish a number of RFCs to document that stuff. And thanks for open source community, right? That was implemented in various operating systems even before I was able to deploy it in my network. There are some ongoing work at V6 Ops at IETF to document stuff I was talking about. So feel free to read more details. For example, yeah, we're talking about how exactly to enable 464 slot, what should be criteria, when to enable it, when to disable it. So all operating system, all developers at least have some common guidelines. So next step for me, because as I said, I'm mostly done, famous last words, with Apple devices. Chrome OS, starting from 1.1.4, supports option 108. It's disabled by default. You can go into flags or settings, whatever it's called, and enable it. For Linux, you can again enable that stuff manually, but there is no 464 CLAT implementation in the standard package of Linux, so there's some work to be done there as well. So it's basically my next step, and we have time for questions.
We do indeed. Thank you very much. So yes, please.
Rinse Kloek speaking from myself. Very nice presentation, thank you. One simple question, do you expect Microsoft to support 108 and 464 XLAT shortly?
Can we skip shortly? I mean, okay. There is a work in progress on this. Let me put it that way, right? I can speak for them, but I have asked.
Okay, thank you.
So yeah, a very good point actually is, yeah, so I understand enterprise people would be mostly interested in Microsoft. Mm-hmm. So if you have support contract, please, because it would make everyone's life easier. I guess the more people ask for it, easier it would be for them internally to justify that work. So if you would like to see that, ask your Microsoft representatives, yeah.
Thank you, get your point.
Hi, Sander Post for Ventus IT Professionals. As a person who's looking for the means and the why to implement IPv6, I would like to thank you for your experiences and sharing them with us.
My pleasure.
A question from Elvis Daniel Belea before escrow. Can I sell your reclaimed IPv4? Just joking.
Private ones?
Seriously now, since you have done most of the work, how hard would it be to replicate this transition in a company, offices, and infrastructure?
I would say it's getting better and better. As I say, I believe that right now, if you take macOS Sonoma, well, again, it depends on your client base. I would say if you have recent, like up-to-date macOS and reasonably up-to-date phones, you can do it easily, right? And the beauty is you do not care about legacy devices really, right? Because legacy devices will be just dual stack, right? So your most problematic part might be if you have, let's say, Sonoma 13, well, I mean, sorry, macOS 13, when you might see some issues. But again, there is no like showstoppers. You can have workarounds for everything we found in Sonoma. Network infrastructure, well, I guess it depends. As I say, we found some bugs. We got them fixed, right? So assuming your network infrastructure does not have all those problems, yeah, I actually I would say it should be like reasonably easy for people to do this. Cisco and Juniper supports Pref 6.4, advertising Pref 6.4 in array in recent releases. I just don't remember the numbers. So yeah, you can do this now. You can do this now. And again, the great thing about that, your devices which do not work very well with V6 will be just dual stack. So yeah, it could be done.
Is there a follow-up there that I saw on that? Yeah, no, so that, yes, you asked the follow-up question. If this is very simple, how long until I need to find a new job?
Oh, no, I'm not concerned about that. You see, I just have a slide. You see, I want to get to like, well, let me tell you a story. When I started at Google 2009, it was 0.2% of V6 traffic or something, and people were, just you and Lorenzo, nobody else is using this. So I want to get to the point when I look in V4 traffic and I'm like, who cares? Nobody using that. We are not there yet, so I'll be around for a while. Okay. I'm not retiring yet.
And Elvis will have a job for a while as well, which I think is his main concern.
No, nobody's getting out of the job yet. Stay in the room, please.
Okay. I think if there are no more questions, thank you once again for a fascinating talk. So thanks to all our speakers in this session. Just before you all rush off to lunch, I would just remind you, please, to rate the talks. I will say that also there's still an opportunity to nominate yourself or with their consent, somebody else for the program committee. And we'll be talking about that later. And also the NCC have asked me to tell you that the meeting t-shirts are available. It's downstairs. That's where they're available. There is a maze of twisty passageways. Do not get eaten by a grue, but they are available downstairs for your fashion plans for the rest of the week. So thank you all very much.
This follow-up question because we were talking about RFC 1980. I want to ask a question. Who am I to? Yeah. It's a pleasure to work with you, Brian. Yes. Thank you, Brian. See you.
Yes. Well, sorry. It was very rude. No problem. Yeah. No. Talk to you later. Absolutely. All right.
Yeah, yeah, no parrot.
Hi everyone, good afternoon. I am sorry I can't be with you in Rome. My poor body's going, oh no, not another long haul. So I find myself back here in Australia recording this. Why am I recording it?
Okay. Thanks, everybody. Nice team here. The front rows are quite empty. Use them if you can. This is installment of RIPE meeting with the opening presentation by Jayasree Sengupta. My apologies for possible mispronouncement about web privacy by design, evaluating cross-layer interactions of quick DNS in HTTP/3, which is just H3 for short. Please.
Yeah, thank you, and good afternoon, everyone. So, I begin today's topic on web privacy by design. Yeah, so as the figure shows, we all know that unencrypted DNS resolutions using DNS over UDP is traditionally used, and it is the most common form that's used in today's internet. So, though the web communications are encrypted these days, but the DNS still remains largely unencrypted, which can actually release a lot of information about the users, and therefore attackers might actually be able to gain a lot of insights into the user profiles and also create user profiles in the long run. And therefore recently the browsers have actually started to offer encrypted DNS options, and they actually allow us to use DOH, which is an encrypted option. But as we know that both DOH and DOT, they are constrained by several factors, such as the head of line blocking problem and also the multiple round trips. So just to avoid this kind of problems, DOQ, that is DNS over quick, is the new player of the town. And DOQ actually gets over the disadvantages that DOH and DOT have by offering the multiplexing support and by also using H3, which avoids the multiple handshakes. Therefore, it's potentially faster. So even when using DOQ and H3, we realize that the improvements are pretty much uncoupled. So what we try to analyze through this talk is how to improve the web browsing experience with inbuilt web privacy by design. So as I already mentioned, that with quick in place, what we can actually do is we can use the underlying quick connection for DNS resolution over DOQ, as well as the web content delivery using H3 over the zero RTT that's supported by quick. So so as a result of which, what happens is that every H3 request to the same web server, so every also we reuse the same connection for the fresh H3 request as well. So as a result of which, what we gain is that it offers optimization potential, as well as not only the web communication, the web communication also becomes private and faster. So this is the figure that we actually try to propose in this. So we say that in spite of using unencrypted DOUDP, the DNS resolution also happens over encrypted DOQ, and we actually reuse the same quick connection for communicating to the web server. So what we say is we actually coalesce the connection on the server side so that we can reuse the quick connection. We'll just go to the methodology in the next set of slides to explain it better. So what we try to do here is we try to again analyze that what is the impact of reusing the same quick connection on the web performance, as well as how does it impact both the fixed and the mobile access network technologies. So this actually shows our methodology, and what we do here is that so what we do here is that we decouple the DNS resolution on the client side, and we have the DNS as well as the H3 server running in the same process on the server side. So we actually use the Linux network namespaces to create this, and then to create this setup, and we then use Netim to measure all the metrics that we are trying to measure here. So for this set of experimentation, we actually look into 3 different websites or web pages. So one is a basic HTML page, and then the other is an HTML with a JavaScript. And finally, we also have HTML with JavaScript, CSS, and cookies embedded in it. So, and apart from this, so for all of these 3 websites, we actually try to analyze it under different network conditions. That is, we have the fiber, the cable, the DSL, the 4G, as well as the 4G medium. And we use the FCC measuring broadband dataset for the fixed broadband connection, and the IRRd dataset for the mobile wireless access technologies. So we also make certain changes to the core DNS and the Chromium as well in order to set up our measurement setup. And yeah, so we also normalize the data points based on the scenario's delay or the round trip. So when it comes to the measurements, so we actually perform 3 different measurements. So first, we try to analyze how Quick interacts with DOQ and H3 in general. So if we look onto the graphs, so the major takeaway from this is that the performance of DOQ and H3 1RTT are majorly synchronized. So in general, metrics scale well with round trips, where we show distinct steps, and each of these steps are actually as a result of the different access technologies that we try to measure. So next, what we try to do is analyze the same thing and the scaling capability of Quick while interacting with DOQ and H3 under different network conditions. So here we are showing both the extreme network conditions, that is the fiber scenario as well as the 4G scenario, and we realize that the connect times do have a longer tail in the higher percentiles, and 1RTT has a relatively large left tail from minimum to the 20th percentile. And so what we actually summarize from here is that the processing delay is large for the lower RTT access technologies, while in absolute terms, the processing delay is same for high RTT access technologies. So it basically weighs in much less relatively, resulting in observed differences being small between the H3 0 RTT and H3 1 RTT setup. So for the next set of experiments, what we try to analyze is what is the overhead of DOQ and DOH in comparison to DO-UDP, which is considered as the baseline. So here also we see the distinct steps which are occurring as a result of the different access technologies. So the major takeaway is that DOQ and DOH, they do not exhibit the expected number of round trips. So only DO-UDP does. And in general, DNS exchange duration of DOQ is 1 round trip faster than DOH, which is also pretty much expected. So next, we again see how the DNS exchange duration actually varies or scales over different network conditions. And we again show it for the fiber scenario as well as the 4G scenario. And from these 2 plots, the takeaway is that the lower RTT access technologies, they exhibit longer left tails, which eventually get smaller with increasing delay. So finally, we actually move into comparing our proposed setup, which is using DOQ and H3 over 0 RTT, and we try to compare it with different variations of the protocols with different variations. That is, we also compare it with how DOQ performs with the normal H3 1 RTT setup and how DOH performs, and all of these is compared with respect to the DO-UDP baseline. So what we see ideally here is that DOH has the highest relative increase across all forms of web pages, and the web pages are actually ordered in terms of their complexity along the x-axis, whereas the access technologies are also ordered in terms of their delay. So we see that the example page actually shows the highest relative increase among all of the web pages. And we also see that the relative increase for the Wikipedia page is generally greater than the Instagram page, which is mainly again due to its complexity. But there is a slight exception to this case. That is, we can see for the Fiverr scenario, the Wikipedia page actually shows results which are pretty much comparable to the baseline, that is DOUDP. And we also see that the performance of the access technologies degrade in an order of the respective round trips, but this also has a few exceptions to it. For example, DSL actually performs worse for the example page in case of DOQ with H31RTT. And the other exception here is that DSL again, so Fiverr actually performs worse compared to DSL for DOH with H31RTT. So what we learned from this slide is that the emulated DOQ with H30RTT performs best across all web pages and access technology combinations. Moreover, it also replicates pretty much similar performance to the baseline when we see for the Fiverr scenario under the Wikipedia page. So this we actually see with respect to the median PLT increase. So in the next slide, we actually dig deeper and we see it for all other, we see in general, what is the general trend of the relative increase of PLT. And here we see that for all access technologies, the example page has a shorter left tail, and Wikipedia page has a comparatively longer left tail, whereas the Instagram page has no tails at all. And when we compare the difference in the percentage points between the protocols, we see that Wikipedia has the largest, whereas Instagram has the smallest. And if we compare DOQ with DOH, we see that they scale with round trip except for a few situations. And the difference between H30RTT and 1RTT doesn't scale with the round trips. So what we basically learned from this set of slides is that both dimensions have an effect on the relative increase over the baseline. Now, with increasing delay between the client and the server, it reduces the potential time savings of 0RTT, while savings for using DOQ instead of DOH increases. So, and the last set of the measurement, what we try to analyze is how the median relative increase across the protocol combinations are with respect to the DOUDP baseline. So what we see is, so here for each protocol combination, we actually have 15 data points and one for each web page and access technology tuple, and we see that DOQ with H30RTT, which is what we emulate here, actually matches with the baseline for one of the tuples, as we had earlier shown. That is basically the Fiverr scenario for the Wikipedia page, and the median DOQ setup is slightly higher, and whereas the DOH setup has an average relative increase of approximately around 15%. So, and it's interesting to see that even in the worst case scenario, the DOQ plus H30RTT still performs better than other two competitors. So what we learn from here is that when we are using H31RTT, the PLT for DOH gets inflated by greater than 30% for the fixed line and greater than 50% for the mobile. And when we are trying to use our emulated setup, which is DOQ with H30RTT, it reduces the PLT by 1/3 over fixed line and by half over mobile when we compare it to the existing normal DOQ with 1RTT setup. So that pretty much brings us to the end of this discussion, and here we actually point out that there is scope for improvements because there are certain limitations in our study. So for example, the presented findings represent an emulated setup where we try to decouple the DNS resolution from the web page browsing in case of the client side, and therefore we have to actually refine it to make it work better. And then the measurement setup also is limited currently to web pages having a single DNS resolution, and it's also implemented with a single H3 web server, and therefore it can be extended to web pages with more than one DNS resolution, where we can also emulate cross-traffic network conditions. And finally, websites with several DNS resolutions should actually have a scaling factor, which also needs to be analyzed. So this brings us pretty much to the final overall takeaway. And as we have seen, the final takeaway is that that the DOQ with H30 RTT, which we try to propose, and we have established that this is actually the best option for encrypted communication on the internet, because it actually shows that we have this a better performance. Because it reduces the page load time for both the fixed line as well as the mobile. So yeah, that's all. And I'm open for questions.
Thank you. Well, thank you. That's insightful. We have two mics over here, both work. Please feel free to queue and state your name and affiliation. And just a reminder, you can rate any talk, that one, the future ones, the past ones on the RIPE meeting page, and that would help both PC and the presenters to know how well they were received. Yeah, please go ahead and ask, or maybe I'll check with Jan if he sees any remote questions. Okay, thanks. Sorry for that. Thank you a lot. And it's very insightful. I'm happy that DOQ is taking over. Thank you. And now for the usually present, but unfortunately not present today, and still is insightful, I hope, Jeff Houston with exact title, Starlink and LEOs, Law Enforcement Officers, I assume. You're welcome. Live.
Hi, everyone. Good afternoon. I am sorry I can't be with you in Rome. My poor body's going, oh no, not another long haul. So I find myself back here in Australia recording this. Why am I recording it? Because quite frankly, I don't want to see myself trying to do a talk at 2 in the morning, and neither do you. So I figured it was kind of better if I recorded this during daylight hours my time, so at least I'll sound slightly coherent. So what are we talking about today? We are talking about Starlink. If there's been a revolution, I think, in the connectivity area over the last few years, it's actually been in this sort of revitalizing of that old satellite system. And Starlink has been the tool to do that. So what I want to talk about is what's so special about Starlink, some of the physics of it, and then look at how today's internet protocols actually perform across this medium. There's no doubt that Starlink is generating a lot of interest. And part of it is that it's actually possible to use handhelds and actually connect in to orbiting spacecraft. As long as the spacecraft is low enough, there's enough power in the budget, and you're not after hundreds of megabits per second, because handhelds just can't do that, I'm sorry. But in Australia, Optus has signed up. In America, it's been T-Mobile. There's deals going on in Japan, all kinds of places. And so it's kind of big news. Now, why Starlink? Why LEOs? Well, the physics of LEOs predates Arthur C. Clarke by, geez, about 300 odd years. Newton worked out that if you just get slightly higher than the Earth's surface and fire a rock sideways with a magic speed, and I'm not sure how he measured it, furlongs per fortnight or something, but in metric terms, the magic speed is 11.2 kilometers a second. And if you neglect the effects of friction in the Earth's atmosphere, if you fire something at 11.2 kilometers an hour sideways, and you're just high enough to get above all the Earth's mountains, it'll just go round and round and round and round forever. Slightly faster, off into space. Slightly slower, it's going to hit the ground. So Newtonian physics suggests that you know, if you fire it fast enough, it'll just stay there. Now, of course, the real world is somewhat different. There is an atmosphere, but there's also something else, and it's called solar radiation. The good news is, for you and me and every other piece of biology on the Earth's planet, we have a molten iron core, which is rotating, unlike Mars that doesn't. Rotating iron cores produce a strong magnetic field. The strong magnetic field deflects solar radiation. So all of a sudden, we're sheltering under something called the Van Allen belt, which actually means that the level of radiation that hits you and me and our atmosphere is much, much lower. This allows the Earth's gravity to keep hold of the atmosphere, and it allows us biological life forms to actually be sheltered by its effects as well. The Van Allen belt actually has two belts. There's the outer belt and a smaller inner belt. And what you're trying to do with low Earth orbiting satellites is to actually sneak it in under that inner belt. And there's this area between, you know, just above the top of the stratosphere, 160 odd kilometers up there, up to around 2,000 kilometers, which is this magic zone sheltered by the Van Allen belt, but also, of course, above the Earth's atmosphere, so it's not generating heat and friction as it sort of bounces off the atmosphere. Starlink itself is running at 550 kilometers. Hubble was at 595. You know, it's a well-populated spot in so many ways. Leo belt, that's high in grazing, but not so high that you're outside the Van Allen belt. And also, interestingly, it's higher than the legal definition of outer space by almost all the world's countries. The countries can't agree when outer space starts and when their laws finish, but variously, it's between 100 and 160 kilometers, depends on the country. But above that altitude, you really are in outer space. You're not operating within any national jurisdiction, which is important, I think, in this satellite land grab that's going on in LEO space. You're also in what is ostensibly a vacuum, which means electromagnetic radiation travels 50% faster than what it does in fiber. So at 550 kilometers to get there and back takes a mere 3.7 milliseconds. Even when they're relatively low in the sky at 25 degrees angular inclination, it's still only 7.5 milliseconds to actually bounce a signal off that satellite and back again. So they're close, they're fast. How much does the satellite itself see? Well, as I said, there's a usable elevation of around 25 degrees. If you go much lower, there's too much atmosphere in the way, signal to noise degrades quickly, not worth doing. But what a satellite will see is kind of a circle on the Earth with a diameter of 1,800 kilometers, or a radius of 900, which, if you remember your basic geometry, is around 2 million square kilometers is visible to that satellite at any point in time. If you look at the surface of the Earth, do some basic maths, you'll figure out that if you could evenly space your satellites, you'd only need about 500 to cover the entire Earth's surface. And that's wishful thinking, of course. You actually want better than that. And for high quality coverage, you'll need somewhere between 6 and maybe as high as 20 times that number to actually do this. But those aren't that bigger numbers. And in essence, what's going on now is that Starlink is actually launched up until a few weeks ago, 4,276 of their spacecraft in orbit. And if you go to this rather natty little website, satellitenap.space, you can see a simulation of the entire Starlink constellation. They're in a belt. They're not in a polar orbit. They're actually in an inclined orbit of around 56 degrees, and a small number of them are in polar orbits to service some of the more remote areas like the Alaskan oil fields and possibly some Antarctic weather stations. I don't know. Those trains, by the way, on this simulation, recent launches, they pop out of the spacecraft in a densely packed train, and over the ensuing weeks, they tend to space out and then become an evenly matched sequence. So that website has a beautiful simulation of what's going on. They're interesting. Why are they interesting? Well, they're really close to the Earth, which means, yes, even mobiles can actually raise a signal and send them a signal because they're not far away. They're not like a geostationary at 38,000 kilometers away. If you have a big enough antenna, and this is too small, you need something, you know, big-ish. Not that big. Luggable, I think is the appropriate term. At luggable, you can actually get some decent signal speed. And using phased array antenna and focusing, you can get very, very good performance. The other thing is they're quite low in the sky, so it's very hard for a third party to try and jam them. And so in areas which are hostile, and Ukraine was a good example, Starlink services were ideal for, you know, communication services, which are actually relatively challenging to jam with conventional jamming techniques. But on the other side, you need a lot of them. You're going to do a decent service across the entire Earth, you're going to need a lot of them. Now, that's always been a major barrier. That was the reason why Motorola's Iridium went bankrupt almost the day after it finished its final launch. It just cost them too much to launch all this stuff. And they were never going to make their money back. So, whoopo, off they go into bankruptcy. But SpaceX changed all that with its reusable rocket technology. The rocket comes back down to Earth, it has no humans in it, so you just simply refuel it and send it off again. And all of a sudden, the launch cost to get things up into a low Earth orbit, which conventionally is around, you know, $10,000 to $20,000 a kilogram into orbit. SpaceX's, the Falcon 9 was doing it at $2,200 a kilo, and Falcon Heavy is even lower at, you know, around $1,700 a kilo. So all of a sudden, there's a new economics of pushing things out into orbit, and it's dramatically cheaper. And that makes a huge difference on what you can do and how many you can push up. Now, these are filings that have been lodged with the ITUT. Some of these are fantasy, you know, some of them really are. But these dreams are pretty amazing. You know, there's SpaceX, which is doing direct retailer, OneWeb, which is trying to be a wholesaler. Amazon is getting close to launching in Project Kuiper. There's the Chinese projects and a bunch of others. The combined total of all of these is around 90-odd thousand in the current filings. So there's almost a bit of a satellite grab going on in trying to get orbital slots, or at least orbital altitude slots in the LEO space over the coming years. And there will be a lot of them up there. They're also getting cleverer. The original satellites, even the geostationaries, you know, were just basically mirrors in the sky. You send a signal up, the signal gets, you know, bounced down again. What that means, if you've only got 1,800 kilometer diameter of the Earth's surface, is that every user has to have an Earth station somewhere in that same sort of radius of reachability. They have to be no more than about 1,000 kilometers apart, preferably closer. So you've got to dot the Earth surfaces with Earth stations, but no more. With the current generation of Starlink satellites, some of them are equipped with interlaser links, and increasingly now with Gen 2, they're all going to have interlaser links so that you can send the signal up and then across and then down where there is an Earth station. You don't have to have a mirror. You can actually do routing between spacecraft. And so what that's allowed is that if you look at some of Starlink's coverage maps, they're now claiming they can cover all of Australia. Even halfway between Sydney and Broome, you can take your little trusty Starlink and get a decent signal, and it will work. They've done this in the western part of Mongolia, and I found a trace route from one of them that's saying to get from Mongolia out in the west, where there is very little there, not even a mobile tower, but there is power, across to Japan and back again, using inter-satellite links, you're getting around 90 milliseconds, which is probably faster than doing it with fiber. And it's not a bad service. So, you know, it is appearing now, and it is a thing. So let's move from that to very quickly the issues of satellites and signals. they're low, they're moving very fast, 27,000 kilometers an hour. Horizon to horizon, 5 minutes flat. So they're quick. And here's a simulation. If you looked up and looked at the hemisphere above your head, almost at any point on the Earth, as long as you're not at the pole, you will see a picture a bit like this, where the spacecraft are actually tracking across. The inner circle is that 25-degree angle of inclination. And what you're seeing is moving across as the Earth rotates and as the satellites move past. At any point in time, there are somewhere between 30 and 50 satellites in view. So there's a rich sort of picking for an Earth station and a user to pick from to use as a relay. And they'll traverse across that inner one every 3 minutes. But they don't use a 3-minute switch. They actually use a faster switch. Starlink schedules a receiving station on Earth to a satellite in 15-second increments. And you can actually see that if you look at the latency. And this is actually a latency across 20 of these 15-second intervals, where if you look at the minimum latency and you get your bracketing right, you can actually see the switch from service to service to satellite to satellite to satellite, because they'll have subtly different latencies. And on top of that is the standard latency variation you actually get to see with Starlink. So the switching is you will get a semi-stable service for 15 seconds, then it will quickly switch to an entirely different service with an entirely different RTT as a result. And again, in 15 seconds, you're going to get another switch. So the characteristics in latency is a lot of low magnitude sort of jitter, and every 15 seconds, a larger jitter component. And that's what protocols have to deal with. Now, before we move away from this, let's just also look at the actual satellite itself. They actually run an array of transponders. So they have 2,000 megahertz of spectrum, 8 channels, each of 250 meg, 3 down, 1 up. That's 8 beams and 2 polarizations. So they've got 48 beams down and 16 up. And if you actually look at it, what you're seeing is a set of these beams are focused as they move across the Earth's surface. The implication is interesting, because if you look at a fixed point, it will see the first of these beams, and then it will transition to the second of these beams, and then to the third. So as it moves across the sky, the signal-to-noise ratio will get better and worse, better and worse, and better and worse. And as you probably remember from Shannon's law, the signal-to-noise ratio has a lot to do with the available capacity of that system. So the carrying capacity of these circuits will vary continuously. Now, you can see this if you actually connect up to a Starlink modem. And I have done so, and I've brought up the gRPC tools, and it reports, amongst other things, the instantaneous download throughput, the capacity, the uplink throughput, and the ping latency to their pop in milliseconds. And so if you do this often enough and report the results, you get graphs that look a lot like this. On the right-hand side is latency for 1 hour, across a 1 hour period. And you see that Starlink sort of varies between around about 30 milliseconds to a little over 60 most of the time, but it's never stable. It's constantly changing. As we said, both in the small and every 15 seconds, it will change in a large leap. Because of the constantly varying signal to noise, the reported capacity of the service will also change continuously. And here's a plot of the reported capacity over a 1 hour period. You notice that most of the time it's between around 130 to 180 megabits per second for downlink. But occasionally when you actually get full throttle with multiple beams helping you out, and in this particular case, there was just one interval where it said, hey, I can do 900 megs. That's my channel capacity. So on the whole, though, don't get your hopes up. Somewhere between sort of, 80s up to 200 is much more likely. If I blow it up a little bit and look at just 300 seconds or 5 minutes, you start to see, even at a very fine-grained scale, you get this extraordinary amount of variation in both the available link capacity and in the reported circuit latency. But this is a highly unstable system. This is not fiber, and it's not even mobile telephony. It's not even sort of, 5G. It's much less stable than that. And what that means is that TCP, which assumes wires, is going to struggle. It is really going to struggle to actually get performance out of this. Not only is the latency and capacity varying, but the loss is also interesting. This is a ping every second for 1 hour. And you notice that across that 1 hour period, around about 4,000 times, I lose one packet. Just lost it. It's not a burst of loss, it's just micro drops, one loss. So you're getting both micro drops and a very unstable jitter. And that's kind of what the TCP protocols have to deal with. Now, how does it work? Well, we commonly use, or probably you do, speed test. And here is speed test every 30 seconds for a couple of months on a service in California. And what it says is most of the time Starlink will report a down speed of above 50, closer to 100 megabits per second. And occasionally, if you're lucky, it'll even get over 200 megabits per second. And some of the outliers are up around 300, which is pretty impressive. But is it true? Well, you've got to actually match what TCP does against what Starlink is reporting. Sorry, Starlink speed test, because speed test does not do protocol throughput. It actually is doing circuit measurement based on packet pairing, looking at the amount of dilation a pair of packets occurs when they're sent in close succession and they get dilated by the network bandwidth variations. TCP reacts differently. TCP is searching for long-term stability. So the blue line, cubic, it probes upwards to a point where it gets packet loss, it takes the pressure off the network and then starts doing it again. Reno, slightly slower frequency, but exactly the same behavior. Gently probing forward, into loss, it finds loss, backs off, and then starts again. The other one I've got here, which is a protocol that's emerging, is of course bottleneck bandwidth estimates, BBR protocol, done by Google some years ago, where it does a completely different algorithm. It actually tries to estimate the link capacity, the path capacity end to end, and then sits with it. Except for one round trip time out of every 8, it probes upwards by 25%, putting stress on the buffers in the network. If there is no latency change whatsoever in that round trip time, it goes, well, it didn't even touch the buffers. I can go faster. So it will then lift up its capacity and go faster. If, however, you're working at capacity and any extra traffic you push into the network is going to start filling queues, then the latency will increase. And if in that one round trip every 8, where you're looking to see if I increase the sending rate, does my latency increase? If it does increase, you don't do anything. You stay at the rate you're on. And in this simulation here, what you see is just gentle probing into the network, but basically a much more stable behavior. That's theory. Let's look at practice. Cubic, and again, don't forget, Cubic is not given a chance to do what it normally does. Nothing is stable. There's lots of loss, almost at random. And the available link capacity is kind of random, and the buffers are big. So it's a sloppy system with a lot of noise. There's just one point where Cubic gives an almost classic signature from sort of second 17 to about second 30, where it kind of ramps up, finds what it thinks is a stable speed, which is around 45 megabits per second. Not a lot, by the way. And then starts to go up again, and then encounters loss. Oops. And loss and continued loss brings it down and down and down and down and down. Till eventually, around 10 because downgrade its estimates on what it can achieve stably, because Cubic is searching for stability. Well, what about Quick? Well, Quick's just Cubic. Cubic is sitting in behind that encrypted UDP. Now, there's also BBR versions of QUIC, but I'll talk about BBR in a second. But as you see, QUIC and Cubic behave much the same way as Cubic. The only difference in this implementation of Cubic is it started with a very high initial window size of 10 packets. And because, as I noted very quickly, the buffer size in these modems is huge, that initial window will look like it's viable, and it will maintain a pretty high sending rate, just filling up the buffers. But the end result is catastrophic loss. And that catastrophic loss will cause Cubic to rapidly, drop down its congestion windows and put the brakes on very, very hard. And so by about second 35 to 36, I'm down around 10, maybe 5 megabits per second. And even then I'm getting loss. And its acceleration is now much, much slower. So, it's still not a very stellar performance. BBR, on the other hand, is vastly different. And the reason why is, of course, loss doesn't matter for BBR. It's trying to estimate a sort of a stable-ish bottleneck bandwidth. And even if it varies a bit, it'll just keep on sending at that rate as much as it possibly can. So what you find is BBR is actually able to sustain up around sort of 130 to 200 megabits per second, except in that around second 30, but do so even in the face of relatively high packet loss. BBR certainly works better in these highly unstable, highly noisy environments. Here's all three. The red is BBR. And you notice that those 60 seconds, BBR was certainly able to kick a lot more traffic through that link, whereas both Cubic and QUIC, which is just Cubic, both collapsed pretty quickly. And in searching for a stable point, found that the continual issues of loss and jitter just defeated it. And 10 to 20 to 30 megabits per second is about as much as you can get out of these systems using that protocol. So it is very much protocol related. So, Starlink, with its very high jitter rates and its high level of loss, because these are fast moving systems going over very quickly, which means normal TCP just simply can't stabilize at the speed at which you want it to stabilize to make use of this. So all these loss-based flow control algorithms just simply overreact, pull back the sending rate, and just simply make everything collapse into, small capacity. Now, if you're doing voice, not very high capacity, Zoom, even video streaming, which is just buffer refresh, you actually won't notice this. It'll work just fine. And it'll look like, say, a DSL connection of somewhere between 20 and 50 megabits per second, and it will work well. If you really wanted to use this to move bulk data at very high speed, no, not so much. Bulk data transfer will not work with conventional flow control algorithms, loss-based. If you really want performance out of Starlink, you need to move over to something that isn't loss sensitive. And BBR is a good example of that gets performance out of the system. It sort of pushes it well up. Now, I don't want to leave you with the wrong impression of Starlink. It's good. And if it's the only thing around for literally thousands of kilometers, whether you're in the western plains of Mongolia or, somewhere in the middle of Australia, in the middle of a desert somewhere, good luck to you, it'll work. And it's the only thing that will work. And it will work acceptably well. It will do video, it will do conferencing, it'll do short transactions. It'll sustain 10 to 20 megabits per second, long held. And it will do it much, much better than an equivalent geostationary service, HF radio. It may not do it as well as 5G mobile, but when you're in the remote and very remote areas, there is no such thing as 5G mobile service. So, it's the only thing around, and it's pretty damn good. So if you're in remote or if you're in the middle of the ocean, this will work well, and it's extremely good. So for retail-based access services, it's very hard to beat it in the rural and remote application. If you want trunk infrastructure to connect up isolated islands in the middle of the Pacific, maybe not so much. It's much harder to get a stable service out of it. And so to sort of put a whole lot of multiplex sessions on top of it, things are probably going to collapse. So it's not a good trunk infrastructure, but high-speed last mile, brilliant. And of course, in settings that are hostile, it's very, very challenging to jam it. So, you know, Starlink has some incredible strengths. And the other part of this, it is not expensive. For satellite servers these days, it's certainly on a par with many terrestrial services. It's cheaper than most Australian mobile services as far as I can see right now. So, you know, it's cost effective. So with that, hopefully I've come to the end of the time. I will certainly clamber up, bleary-eyed, be ready and willing to answer any questions you might have at the end of this. Thank you very much.
Hey, exciting. And not much about DNS. The previous talk and this talk may lead to collaboration. Fine. You please state your name and affiliation, and then Jim.
Lavodopian speaking for myself. I have a question regarding the mobile phone connecting to satellites by 5G. How do you make sure that your satellite service comply with all frequency regulations of all countries across the world to make sure that phones can work in all the countries across the world to connect to? Thank you.
Thank you. Can you hear me, by the way, firstly, or am I, you know, an ethereal voice from the sky?
Perfectly.
Okay, terrific. The issue is, no, it does not comply with all the countries all of the time. While it's outer space and there are no laws above 160 kilometers, down here to send and receive, there are laws. And Starlink has to negotiate individually with each national jurisdiction when it gets a license to operate. So it has licenses in the United States. It has licenses to operate in Australia, I believe in New Zealand. But, you know, in other countries, it's a country by country thing. It does use the standard frequency allocations for both 5G and for satellite, the Ka and Ku bands, I think. But for individual countries, you know, realistically, it's a one-on-one negotiation as to when they can operate. So Australia signed up with Optus on 5G. The US has signed up with T-Mobile, but quite frankly, other countries, it's up to them. Don't forget, for a handheld to work, you need an enormous transponder. There's one up there which is the size of a tennis court. It's not Starlink, but you know, the astronomers are now objecting to this floating tennis court in the sky. So, you know, I wouldn't hold your hopes up for high-speed 5G from a handheld. I think it's more short SMS services that's about the only thing that's viable from that altitude. Thank you.
Yeah, and I think they had the license for the stationary Starlink terminal and for mobile Starlink terminal, and these are different, if I remember. But please, Jim, and then you, and then personal to Jim.
Jim Reed, freelance consultant. Great talk as always, Jeff. Thanks for that. You might be aware that there's been discussion about this kind of stuff in an IETF setting, and the arguments are being made that the use of these low Earth orbit satellites changes the paradigm for communication because you've got a fast-moving base station relative to a static observer on the ground, and that transforms the way in which normal mobile communication works. And the argument was being made by some people in the IETF setting, or not necessarily in a working group though, was that we needed new protocols for that, and that TCP and IP and QUIC were no longer good enough to satisfy those kind of concerns because of those sort of jitter and latency considerations that you mentioned earlier in your talk. So my question to you is, what's your perspective on that argument? And do you think the solution will be something like we did with TCP back in the 1990s when we had to first come across the use of the long fat pipes?
Yes, indeed, Jim. I think you're absolutely right. We actually didn't alter TCP very much with the long fat pipes. To be perfectly frank, you know, TCP just simply had so much stasis that trying to make it work well over hundreds of gigabits of pipe capacity didn't really succeed. And indeed, when the mobile revolution came along, TCP hardly adapted at all. It was actually left to the mobile operators to make their circuits look like wires. Because the TCP we use today, and in particular cubic, it's almost a monoculture, works over stable circuits. And the one thing you find with spacecraft zooming over you at 27,000 kilometers an hour is that you're getting massive variations in signal to noise, and massive variations in latency, almost in fractional second terms. TCP collapses. So while I'm giving it a 200 megabit per second bearer, I'm getting 10, 20 megabits per second of sort of sustained throughput because TCP doesn't cut it. And it's not TCP, it's loss-based congestion. And that model of loss-based congestion works well if you've got a carrier, a wire, a bearer. If you haven't, and you're in effectively free space, you're on the wrong protocol. If you really want a protocol to work, you've got to move to a different paradigm. I, frankly, am an ardent fan of BBR. It is the mammal of the reptilian TCP family. This stuff just scavenges bandwidth out of networks like nothing I've ever seen before. I can get gigabit, transoceanic, and even, one side of the earth to another without any kind of bandwidth reservation. It just literally elbows everyone else out of the way. It's a fantastic protocol. So, my view is, I don't know why we're not all running BBR. It really is just a totally different way of thinking about congestion and protocol behavior. And if you're not running it, and you're wondering why your service is rubbish over long distance, well, that's the answer. So I think BBR is definitely the coming protocol right now for this kind of multifaceted world.
Thank you, Jeff.
And I wonder what they'll be running between the mesh satellites, right, in the sky. That would be another issue for the Musk. Please, you, and then maybe you have to close the queue.
Hi, it's Harry Cross speaking on behalf of myself. Just an interesting question. Have you done much around what happens when a device moves between satellite while it's transmitting or while it's mid-flow? Because I can imagine that's going to be quite complicated.
Well, there's a switch every 15 seconds. So your phased array antenna, which doesn't move very much, but it manages to sort of refocus across enormous angular distance, does that switch literally every 15 seconds. Now, the reason why there is a 40 to 60 millisecond latency on Starlink, when the actual device is only 3.7 milliseconds away from you, is that there is an enormous amount of buffering going on. And so when it does that switch, it has some milliseconds to actually have a sort of a hiatus in connectivity as one half of the array locks into the new satellite and the other half of the array is getting prepared for the next switch in another 15 seconds time. So Starlink is continuously interrupting your circuit and flicking to another one. And it's not just you, the base station is doing the same trick, right? Because to keep your signal going, it's actually flicking across from satellite to satellite to pick up your signal. Oh, and the protocol between satellites, it's just IP. It's your protocol. Whatever you use for flow control is kind of whatever you're using, which
so
is why Cubic and
BBR in space is a thing.
Oh, BBR in space is a thing, and bloody hell, it works brilliantly. Switch to BBR.
Looks like we got our work cut out for you. Thanks, and please, thank you. Thanks. That's a good discussion now.
Blake Mazzeo, thanks for this talk. It's really good. Along with, I'll give a plug to Mark Handley's YouTube channel where he has all these very nice simulations of satellites whizzing around and things. Do you feel like there's still any room in the connectivity space for high altitude pseudo satellites, aka HAPS? This is like the weather balloon or the autonomous aircraft at 100,000 feet using conventional 5G technology kind of stuff, or this just blows it all out of the water?
Oh, the stuff that's sort of around the Loon area is much more stable, has much better signal to noise, and they're actually able to offer a femtocell in the sky. And using some very clever steering, you can do that. But the problem is twofold. One, you're not in outer space anymore. You need national licensing, so you're headbutting against all the local mobile carriers directly. You're offering a competing service. They have an entrenched business model, and you're the enemy. So you're going to get shot down one way or another with that. The other part of this is, quite frankly, you've still got a problem with earth stations, because the lower you get, the closer you need ground stations. So with Starlink, even before they did the laser links, you needed an earth station sort of in 1,000-kilometer grid, which quite frankly was never going to work. That's why they had to do inter-spacecraft laser links to try and get this thing running across space. For the high altitude folk, that's a problem squared. You know, it's just a nightmare. So yeah, you can go up across Puerto Rico after a massive hurricane and provide emergency service. Great, but that's a huge investment for a small window of service. And once everything's back to normal again, I'm pretty sure the Puerto Rican mobile company is going, no, 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 get out of my business. You know, that's my business. So I'm just not sure. Google sold off Loon, as you're probably well aware. And I think there was a Facebook one, and there are a few other experiments. They were interesting experiments, but I'm not sure if they have a commercial future. Starlink is kind of the first, because of its low launch costs, to actually take this on in spades and do it in the middle of the ocean, you know, anywhere. And that's kind of unique. In reference to Mark's work, I am not sure how many satellites you can relay through to get down again. I know they're working from Mongolia to Japan. I don't know how many spacecraft are there in the relay. You can't tell because, you know, it's all encrypted. So, yeah.
Thanks a lot.
Thanks. Any remote questions on? None. Okay, please be quick, and then we'll close it and go on to our next presentation. Thank you, Jeff.
Hi, Jeff.
Thank you.
Thanks for the talk. I'm Babhub from CISPA in Germany. So the question I'm wondering is, perhaps it's too early to say that BBR is the best choice for space networking, perhaps also because the goal of congestion control is not just to maximize throughput, right? It's also about fairness. And currently, if we do the measurements in an empty pipe where there is no competing traffic, of course, BBR will look the best option. But when there is competing traffic, maybe BBR is just sucking up bandwidth from every other Starlink user. So maybe we have to be a bit careful here, right?
Spoken like a true network operator. As a user, I don't care about anyone else. I'm just there with elbows going, get out of the way. And BBR suits me just fine. Network operators tend to go, how dare you be so greedy? Look, it's the same old argument generation after generation. You know, the mobile folk go, oh, this protocol's too evolved. And folk like me going, look, you had a network and I'm using it. What's your problem? And I think that tension isn't going to go away anytime soon. Thank you very much. Although I can't be there in person, it has been a pleasure to at least talk in this virtual way. Thank you.
Thank you, Jeff. Right, and now my pleasure is to announce our next speaker. Let me check the name. Rough time, securing time for IoT devices. Christer Weinigel. Apologies.
Weinigel.
I miss Weinigel. Okay, great. Thank you.
So, where are my slides? Lovely. My name is Christer Weinigel. I work for a company called NetNode.
Please be closer to the microphone, maybe.
Sorry.
Yeah, thank you.
I work for a company called NetNode in Sweden. So I'm going to talk a bit about securing time for IoT devices. So, next slide, or this one.
The big one.
Lovely, thanks. So I probably do not have to tell you why accurate time is important, but basically many security critical protocols today, they need accurate time. You have DNSSEC, TLS, both of them have sort of a validity. This certificate is not valid before time, it's not valid after time. So to use TLS, you really need time. You also have applications that need time. For example, if we're at a hotel and they lock the doors at 9 in the evening and they turn on open the doors again at 9 in the morning, if you can trick them into opening the doors at 6 o'clock in the morning, that might be a bit of a problem. So how do you keep time then? Well, any device can really keep time when they are turned on, powered on. You always have an interrupt that you can use to keep time. Devices, when they are turned off, might not do that as well. They might not even have sort of a real-time clock hardware. Even if they have a real-time clock, such as Raspberry Pi, the Raspberry Pi by default doesn't come with a battery. So to get a real-time clock that keeps power, or keeps the real-time clock powered while main power is off, well, you need to buy a battery cape or build your own battery cape. So it's quite common that you don't have a working real-time clock when power is off. There's something called shipping mode where, well, you have a device sitting on a shelf and the first time you start using it, you pull a small tab to connect the battery to the device. So the first time you boot, well, no power. and no time. Since we're talking to network guys, well, basically we're talking about network connected devices. So we have a pretty old protocol. It's from 1984, I believe, NTP, and everybody uses NTP today. It's the network time protocol. It's an old protocol. It's unencrypted, doesn't really have any security. There are variants of NTP with security, but it doesn't scale to internet scales. There is another protocol called MTS that I was involved with. It does add security to NTP, and I'd say it's a pretty good solution. It does have a bit of a bootstrapping problem though. So NTS depends on TLS, and as I said, TLS requires time. So where do you start? Do you try to get time first and then do TLS, or do you do TLS first and then you need time? Another problem with NTS is that it requires TLS, which is kind of heavyweight. So for a small device like the one up on the screen, it might not work that well, or it might be a bit too heavy. And if you have a fight between features and security, well, most people will choose features. So I want to talk about a possible solution called rough time. It's an IETF draft. It started out as a way to solve the bootstrapping problem. With security, it wasn't really intended to replace NTP because it was only supposed to have a resolution of about 10 seconds. So you can validate a certificate, but you don't really want to use it as your main clock. It has fairly low CPU usage. It has a fairly low memory footprint. So it's something that you can run even on very small devices. So rough time has evolved a bit since the beginnings. So now I'd say it's a pretty decent generic time protocol. It has a lot better resolution than accuracy than 10 seconds. It's actually down to the timestamps are in microseconds. So basically you can get as good time as your network will allow. It is secure. It can run on a fairly resource constrained device, and it still solves the initial problem, the bootstrapping problem. So one problem with rough time right now is that it's kind of stalled. There's a bit of fragmentation. There are 4 different incompatible versions of the draft, and they don't speak to each other. And a lot of the people who have been involved with rough time haven't had time to work on it. So RIPE has actually funded us to kickstart rough time, try to do something with rough time, get it working. So this is sort of a call to arms. Please talk to me, because we want to get more people involved. We'd like to ask everybody sort of, what do you actually need in timing protocol? Can you tell me your requirements so that we can actually figure out if rough time is a good fit? Do we need to add something to rough time? Do we need to subtract anything from rough time? So basically build a requirements document. After that, update the draft to follow the requirements. When we've done that, well, get the implementations into shape and try to make it into an RFC, submit it to RFC editors of IETF, so we actually make it a proper standard. So here are some resources if you want to take a look at this. I'm actually going to talk a bit more about this at the IoT workshop group session in an hour or so, and go a bit more into details. Otherwise, my mail address is right there. Please contact me if you're interested in this, because I really want your help. Thank you. Any questions?
That's amazing. One more time protocol, and thank you for taking care of small things.
And we have working code on a small device, actually.
Yep. You want to ask, please?
Yes, hi, I'm Robert Kostecki for the RIPE NCC. We actually hit this problem, the not knowing the time on the Atlas hardware devices, right? They don't have batteries or anything like that. We had our own solution, which was good enough for like up to a second accuracy or so, which is good enough for the purposes of Atlas. But I would love to talk to you because this is interesting and we may just get on board.
Yeah, I'm going to be here all evening today, and I'll be here at least Thursday and Friday. So
excellent, thank you.
Thanks.
Thank you. Any remote questions? No. Okay, great. So now we have a remote speaker, Truncation from Ukraine, and he'll talk about the citizenship, quote unquote, of resources. That's a recording, right?
My name is Taras Gaichenko, and today I present a lightning talk
citizenship of resources. This research was done when I participated in the execution of the work granted by RIPE-NCC Community Projects Fund. My part consisted of placing on the map labels that mark the location of resources that change their country attribute. To complete the task, I had to find the appropriate sources and make a set of scripts to get the result. Let's start with sources. Here is the list, but the main source of research was extended delegated statistics. The main subject of research was as numbers. I looked at IP addresses and have to say that IPv4 demands deeper research that takes more time. Unfortunately, it was a very limited resource. And IPv6 almost didn't change their citizenship. So what has been done? I took two files from extended delegated statistic dated 23rd of February 2022, the last day in Ukraine without the total war, and 1st of November 2023, let's name it today. I selected from these files as numbers that had UA attributes in the first file and root attributes in the second. There are 54 as numbers satisfying these conditions. Then I had to exclude as numbers who changed their citizenship due to the deployment of NWI-10. Unfortunately, RIPE-NCC doesn't provide a list of such resources. Do they have it at all, I wonder? However, I got the answer that the second stage of NWI-10 deployment was made on November 30th, 2022. I compared files dated November 29th and December 1st. 33 of 54 as numbers changed the country attribute during this day. It does not mean that there are no cases that we are working on, but for now I exclude these as numbers from research because they demand additional consideration. Except one as number of these 33 that changed its attribute from root to UA, later it changed the attribute again to root. 4 of 54 were absent in these files, so I think that they were returned to RIPE-NCC and then redelegated again to Russian LIRs. Only 6 of these 54 as numbers were mentioned on the RIPE-NCC site in the transfer statistics. So I got 18 as numbers to place on a map. Then I collected addresses from the WHOIS service and tried to convert these addresses to longitude-latitude coordinates. It was one of the most challenging parts of the research because most as numbers LIRs have Ukrainian addresses with country Russia, and services that convert addresses to longitude-latitude go crazy when trying to give an answer to such requests. Sad to say, this data was obtained from the RIPE-NCC. I know that this data was provided by LIRs, but something goes wrong if we have such a situation. And here are the labels of these as numbers located on the map with the drone-occupied territory of Ukraine. Nothing unexpected, but what we have now. So what? Initially, the data was collected for community as a repository to contact to the resource holder. Nobody cared about the country where the resource allocated, but times have changed and the NWI-10 confirms it. The set of policies and the RIPE-NCC itself did not adapt to the state of war in the part of the service area. For example, how a Ukrainian company can become Russian. This is very strange in real life, but it is a usual thing in the RIPE-NCC DB. Maybe we need a separate task force to consider these questions and possibly suggest some solutions to the community to make the data more clear and comprehensible. My thanks to the people who initiated this work and helped to fulfill it. Thank you for your attention.
Yeah, thank you, Taras. I hope you hear us. Okay. Yeah, I'm glad you spoke these results, and I'm thanking RIPE for sponsoring. Please remote question that Jan is going to read.
Okay, thank you. So we have a Q&A. We have a question. Well, it's not a question. It's a statement from Oksana Prihodko. First of all, I would like to say huge thanks to Taras for his extremely important and interesting contribution to our project Internet Identifiers in Time of War with financial support of RIPE NCC. Also, huge thanks to Adamant and Ivan Petucho in person, not only for hosting RIPE 87 Kiev Hub, but also for being a partner in our project. Unfortunately, we had an air alert in Kiev, and I can't go to the office of Adamant. All bridges in Kiev are closed. So I would kindly ask you to deliver my question to Taras and other participants of the meeting. What next steps regarding the citizenship of resources have to be prioritized? Oksana Prihodko.
Thanks.
Thank you for the question. First of all, do you hear me?
Yes, fine. Loud enough.
Thank you for the question. It depends. The next steps depends on what of our aims. I think that first of all we need the data more consistent and we need to have a better history of data to track the history, what was done, and possibly what really happened during the last time, to have the ability in future understand what was done. Besides that, I think that consistent data is important not only for the Ukrainian data holders, but for the whole RIPE community.
I would agree. Any questions you're reading? Thank you, Trust. Please read the question. I assume you have
like it's my own question. So to be a student at Max Planck Institute for Informatics, speaking for myself, I was wondering whether you looked at how the DNS changed for those prefixes which changed citizenship.
I did not consider DNS in this research. I only look at S numbers. As I said, I look a bit on IP addresses, but IPv6 really did not change citizenship, and IPv4, it is more complicated history, and to sort out what happened there, it will take more time.
Okay, I might be able to help with that, especially the DNS part.
Yeah.
Thank you.
Sorry. Go ahead. Right. Any other questions, Jan or? Okay, good. Thank you, Taras. I'm happy that you do this work, and I'm sorry what's going on in Ukraine for everybody who knows that. And I think we should continue this research because I think we can improve database handling processes, and maybe that's something for the working groups. But let's go on to our next step in the program. And by the way, don't leave before I end of that. We have an important announcement at the end of the session, actually 2 of them. And the next talk is another remote presentation, if I'm not mistaken. Yeah, Louise van der Peel from University of Delft. I assume we are broadcasting the video? Right. Oh, Miteko then. Thank you. Still not live. Are they on? Maybe need to be promoted to speaker. Yeah, she isn't connected to Miteko platform right now. We failed to find. Do we have the management right? You do, right? You can. Yeah, we see now. Speaker, correct. Show screen sharing, doesn't show the mic. Maybe we can put the slides on the screen and then we can click through them. That would be better than nothing. The deck is there in the system. I did check it.
Hello.
Hi, we hear you. So maybe we'll click through your slides and you can test that. Or
I've also uploaded a pre-recorded video, but if you want, I can tell about it now as well, if that doesn't work.
Yeah, better I think if you just do your presentation now live.
Okay, that's great. Let's see. Okay, yeah, it works. And hello, everyone. I'm Louise van der Peet. I'm a PhD candidate at the TU Delft in the Netherlands. And today I'm presenting a standard for increased transparency and privacy on the web called Privacy.txt. So while I was doing this research, I've been getting increasingly frustrated about privacy and cookies on the web in general. And I think most people understand this frustration when they see these types of cookie banners. So here you can see two examples. In the first one, you see that you can only accept any cookies you might get, might be tracker cookies, might invade your privacy, but all you can do is accept them. And in the second example, you see that you have to unclick all of the cookies separately in order to not be tracked or anything. So both are quite tedious and annoying, but there are actually laws for this in Europe. So the first law was introduced in 2002, the e-privacy directive for consent. And it says that all but necessary data collection requires consent. And eventually this led mostly to the first type of banner, where they just have to notify the user for saying, okay, we're collecting your data. So then in 2018, the GDPR was introduced, which gives new requirements for consent, specifically that consent should be freely given, unambiguous, specific, informed, and purpose limited. Nowadays, we still see a lot of consent banners that violate GDPR. For example, both of these do. In the second case, this cannot be considered unambiguous because you really have to do a lot to reject your consent, while you can easily accept everything. So I'm not the first researcher that looks into this. There are many problems with cookies and trackers on the web. So 90% of websites use tracking cookies. And even if you do not give your consent on a website, often this will still be ignored. So if you reject it, you will still get the cookies. and 80% of websites are not compliant under the GDPR currently. So I made a solution for this. It's called Privacy.txt, and it's based on other .txt standards like the ads.txt standard. And basically, we try to increase transparency by reporting cookies and attributes, banner information, and the privacy policy location. Also, the attributes of Privacy.txt is that it's server-side, it's self-disclosed, so the website owner will put the information themselves on their website. The format is machine readable, so it's easy to create and also audit, and it has a single reference point. It will always be put on, for example, website.com/privacy.txt. And here you can also see an example of a privacy.txt file. I also put some arrows to show which attributes are recorded, which are the cookie names, the cookie domain names, the duration of the cookie, whether it's first or third party, whether it's optional, whether it's HTTP only, and the secure value. So the advantages of privacy.txt is that it's machine readable. It's easy to adopt because the grammar is very simple. There's no change on the user side, only on the client side. It does not interfere with browser functionality. It is complete in most parts of GDPR compliance and also other compliance laws from other countries. It has a potential for high accountability, and it has transparency as a priority. Furthermore, we also made supporting tools. So mainly two tools, the data collector tool and the cookie compare tool. So the data collector tool collects cookies from websites real time and can automatically create privacy.txt files. The cookie compare tool can then compare two of these files or a file from the web or real-time cookies from the web in order for verification for privacy.txt files or for auditing purposes, which can eventually be used large scale. So there are some challenges in the automatic cookie generation. When we collect cookies from the web, sometimes the data collector will be recognized as a bot, and then it will not have access to the website and therefore cannot collect cookies. Sometimes cookies require user interaction to be activated. So, for example, the scrolling or the clicking on a YouTube video will activate a cookie, and the data collector tool does not do this. So then not all cookies will be recorded. Furthermore, we made a banner detection tool that detects the accept all button of the banner in order to record all cookies. And this banner detection tool has about an 80% accuracy, so it is possible that not all cookies are collected when the accept button is not clicked. And then another thing we found is that sometimes cookie attributes change quite randomly. So in this image, you can see a session tracker cookie, which in the first part has the secure value to true, and in the second part, the secure value is false. And this happened within a second of entering the website without any user interaction. So these changing attributes might cause errors to be in the privacy.txt files, which you cannot do a lot about. So now on to the real world impact. The solution could empower users by providing more privacy transparency so that users can see in one place what's going on with their cookies and data. It can help websites comply to the GDPR or other privacy laws by easily verifying the privacy.txt file and also being able to eventually see whether what they're doing is compliant. And third, it can facilitate auditing. So it allows for large-scale auditing of cookies and privacy features on the web. So to sum up, currently the GDPR compliance on the web is low, and we need more privacy and transparency for users. Privacy.txt is proposed as a transparency along with auditing and generation tools to make the use a lot easier. So thank you for listening, everyone, and let me know if you have questions.
Shane, you're there. Great. Please, you have some time.
Okay, thank you. This is an interesting idea. My name is Shane Kerr from IBM. So I think this could be useful, and it's definitely better than the situation that we have today. My question, though, is the objective to make this something that's required by regulation, or is the expectation being that websites would kind of opt in to using this technology? And the reason I ask is because my suspicion is that web providers are happy to provide a bad user experience to make us hate the GDPR instead of hating them for not protecting our privacy. So if that's true, then they're not going to adopt this technology voluntarily. They're going to have to be dragged kicking and screaming by Brussels. So what's the plan, I guess, is the question.
Yeah, so it would be great if it could be part of a regulation that this is just mandatory for websites, but I don't see that happening in the near future. So instead, what I think is that businesses do have an incentive to use this standard, because maybe it doesn't count for big tech, but small to medium sized enterprises might not exactly know how to be GDPR compliant, and they spend a lot of money on this. And eventually it would also help them to have a solution where they can easily verify their own compliance. So in that case, there might be some adoption from those types of businesses, and hopefully others will follow.
I share your hope. Thank you.
Thank you, Shane. Thank you, Luis. Any other questions, remote to local? Locals, I don't see. Must be invisible speakers. Oh, well, okay. We had two announcements. Brian would make the second one and I make the first one. There would be social tonight, and it would be starting not when it's printed in your badge, but now later at 9. There will be some buses which would depart from Sheraton 1 and Sheraton 2. There's actually a printed announcement closer to the main building, and it states exactly when these buses are going and when they're returning. And some of these even stop by the Ibis Hotel on the other side of the road. So yeah, see you there. And now to the Brian for his other special and more important announcement.
I don't know, how to get home is pretty important. Sorry, my ongoing and desperate need to speak in every single session today. So just to say, we would normally announce this at the beginning of the 4 o'clock or 1600 plenary, but as we don't have a 1600 plenary for lots of good reasons, we'll announce it now. Unless someone has literally sent us an email in the next 60 seconds, we have 9 candidates for the PC elections, and thank you all to the people who volunteered for that, for 2 seats indeed. And the voting will be opening at 1600, and it should be on the front page of the Route 67 website. And we're going to send you all an email as well, just to, make sure, because we know you're all spending this meeting reading your email. But just to say the 9 people who have volunteered, and again, thank you to all. We have Valerie Aurora, Alexander Asimov, Chris Buckridge, Harry Cross, Sandra Kamal, Dimitro Kamanuk, Hannah Crichton, Francisca Lichtbau, and Kevin Maynell. So there will be bios of all these people on the Ripe 67 website, and you can then go and vote and all the rest there. So thank you all very much.
Oh, okay, see you. Oh, and one more thing, it's NRO and C vote. You should have received that separate special email about that. NRO number council, that's the important thing. There's 3 candidates and you can vote for them. Some people can, but that's, I guess, a minority. Check your emails, please. And see you later.
Hello? Here we go, here we go. So, good afternoon. Good afternoon, everybody. My name is Massimo Candela, and welcome to the Measurement Analysis and Tools. This time in Rome. So I'm really happy about this. I was born and raised in Rome. I moved to the Netherlands at 26, so Rome is my hometown. And after many years of participating to the RIPE meetings, I'm really happy to see so many familiar faces in my hometown. So welcome to Rome for a definition of it, but still welcome to Rome. And as I said, this is the Measurement Analysis and Tool Working Group. We have a really nice and packed agenda, so we will proceed. We are also a few minutes already late, but we should have plenty of time. So these are the Math Chairs Working Group. And well, there is Nina and there is Stephen. We will alternate to chair this session. And this is a view of the agenda. So we have some interesting talks about censorship, about traceroute, plenty of traceroutes. And also we will see performance of Quick, and we will finish with the RIPE-NCC tools update. And I think we can immediately start with the closing agenda. Okay, this was fast. We can immediately start with the first presenter. The first presenter is Arturo Filasto. Arturo Filasto founded the Open Observatory of Network Inference, ONI, in 2011. He previously worked on the Tor project and created several free software projects that promote human rights, such as Global Leaks. He co-founded and serves as the Vice President of Hermes Center of Digital Human Rights. Arturo studied mathematics and computer science at the University of Rome, La Sapienza. So another from Rome. The stage is yours.
Thank you very much, Massimo. And it's great to be here in Rome with you all to tell you a bit about the work that we're doing at UNI. I figured, I'd learned about the MAT, the Measurement Analysis and Tools Working Group of RIPE when I met in Montreal, Stephen. And it seemed like an excellent opportunity to come here and tell you a bit about our own MAT. The Measurement Aggregation Toolkit. So I don't know. Maybe I only find this funny, but I thought it would have been a nice joke. So, anyways, I will tell you what we are going to talk about today, and the main topic is the area of work that we focus on as UNI, the Open Observatory of Network Interference. And what we do is we measure internet censorship. So before going deeper into that, it's maybe useful to clarify what we mean by internet censorship. So when we talk about internet censorship, what we're talking about is the intentional control or suppression of what can be accessed, published, or viewed on the internet, right? So a key part of this is intentional, right? And why this is challenging is that oftentimes I guess many people, even in the MAT working group, face it when doing network measurement. You deal with certain things that you observe as somebody carrying out internet measurements, and you don't necessarily know what is causing that behavior. So, for example, we deal a lot with this level of uncertainty where you see some signal that could be attributable to internet censorship, but it might also be attributable to some sort of transient network failure, some sort of error condition that's happening on the network and is not due to an intentional restriction. But before we go deeper into that, I think it's important to also say why we measure internet censorship. Why is this important? And I think it's important for a variety of different reasons. For starters, it's really important because the work that we do at UNI, it's in support of a lot of advocacy efforts aimed at fighting internet censorship. So we see ourselves as a provider of data to support evidence for these types of fights. We also believe it's important to offer a public archive of longitudinal open data on internet censorship worldwide so that we can study this phenomenon over a long period of time and understand how it has evolved. It's also really important to have oversight and transparency so that those implementing internet censorship are accountable and that we know what is blocked and how it is being blocked. We also support a lot of research interventions that study internet censorship from a technical perspective, but also efforts aimed at making the internet more resilient to forms of censorship. So we support a lot of internet like censorship circumvention tool developers in making their tools more robust against the evolving forms of internet censorship. So this is why it's important. But what is the real impact of censorship? When does censorship happen? I won't go too much deep into all of these, but just to give you an idea of when censorship happens, like what are the triggers for it? And so I think broadly speaking, censorship tends to happen when there are there's a baseline of censorship that is implemented basically everywhere around the world. But then we also see an increase in censorship around certain political and social events, whether that is elections. So we have seen, over the years, social media getting blocked during elections in many countries around the world. We see it during political transitions. When there was the coup in Myanmar, they started blocking WhatsApp. There were internet blackouts affecting the country. We see it during conflicts. So, when there was an increase in tension between Azerbaijan and Armenia, they started to block TikTok. We saw it obviously in the escalation of the conflict between Russia and Ukraine. But it's also very importantly targeting marginalized communities. So we see a lot of groups, whether for certain ideologies or beliefs, religions, or just attributes of their being, getting impacted by the restriction in accessing certain types of content on the internet. And lastly, we see it around protests. So like, one case that I will now dive a little bit deeper into is, when in Iran last year, there was a wave of protests following the Mahsa Amini protests. We saw a significant intensification of the forms of censorship being deployed inside of the country. And so around that time, we worked on a multi-stakeholder report investigating the various forms of internet censorship that followed the Mahsa Amini protests in Iran. This was a joint project between UNI, IODA, Measurement Lab, Cloudflare, Cantic, ISOC, and Article 19. It was facilitated by the European Commission and the United States government. And basically what we did is we took all of these different data sets and we used them to be able to study how internet censorship had escalated basically in the country following the protests. And I just wanted to pick out a few bits of information that I think are particularly interesting and relevant to this type of audience. But you can obviously find the full report on our site. So in terms of the timeline of events, as probably Mahsa Amini was murdered on 16th of September 2022, and this triggered sort of not unprecedented, but a significant wave of protests in the country. Right, protests emerged in many different regions, and following this, this enormous wave of social uprising and protests, the government started cracking down on the protesters, and obviously in the physical space, but also on the internet. And so we saw a significant increase in the forms of restriction to access to the internet. Specifically, one thing that we saw that we had not previously seen was the use of digital curfews, is how we were calling them, which is something that we had also seen before in Myanmar, but in Iran it was sort of the first time that we saw this type of technique being used, where basically for specific hours during the day, the internet was completely disconnected. So there was no access. And this was limited either to specific regions or in some cases it was nationwide. And access to the global internet was restricted for several hours. And this was done over the course of 13 consecutive days. And here we can see, the presence of this curfew in the IOTA data, for example, which monitors internet blackouts. Another thing we started to see was that several social media platforms that previously were accessible started to be blocked. Similarly, app stores started to get blocked as well, probably as a result of people trying to use circumvention tools to get around the restrictions. And so, they were basically cracking down on different ways that people would use to gain unrestricted access. Similarly, browser extension repositories started to be blocked. And then a few things that I think are especially interesting maybe to you is that encrypted DNS, which previously was mostly working in Iran, started to be restricted much more heavily. So we saw all of the main encrypted DNS providers being blocked. And this was, as you can see from these charts, previously they were somewhat working, some of them. And then, from around, this is October, end of September, October, they started to get entirely blocked. Other interesting things that we saw was that HTTP3 and QUIC were blocked only on certain networks, but it was like the whole protocol was entirely restricted. We do not know why QUIC and HTTP3 was specifically targeted. We speculated that it might be as a result of their censorship capabilities not being sophisticated enough to implement restrictions on these newer protocols. On some networks, we also saw a complete block of IPv6. So, there was a presentation before, like talking about adoption of IPv6. In some places, it is blocked. Like they decided to entirely block it. And so, this is stuff that I guess has an impact on, the rollout of new technologies that are, more secure and in some cases an improvement. But if they do not work, then that is quite unfortunate. So this is an example of the research that we do, but we really see ourselves as an enabler to conducting this type of research independently. So UNI was a project started back in 2011, 2012, and our goal is basically to empower decentralized efforts at understanding network interference worldwide. So we really would like to enable people to use our data, use our tools to do this type of research on their own. And so as a result of this, we have this open data set that counts billions of network measurements from basically every country in the world. And it's just out there for anybody to use. And the data set is collected through our app called UniProbe, which is a mobile app that you can install on basically every device, like mobile or desktop. But we also have a MAT. So the MAT is the Measurement Aggregation Toolkit, which is this open data platform that you can use to explore this giant data set, which is UNI, so that you can come up with your own inquiries of what kinds of network interference you might be interested in exploring. And one of the things that I thought is like a reflection to make for this audience is that there's kind of this challenge in presenting rich technical information to non-technical audiences, which is the audiences that we are mostly dealing with, in that, as I was saying before, there's this margin of uncertainty where you have some number of data points that contribute towards confirming or refuting a certain hypothesis, but ultimately there's always some sort of margin of uncertainty. And sometimes the margin is not, it's pretty clear. Sometimes the signal you see in the data is very obvious. Like in this case, when they started blocking WhatsApp in Senegal, you can clearly see that before it's all green, and then at some point for a brief period of time, it's all yellow. And then, it starts being green again. But other times it's not so clear, you know? So like this is from today in Italy, RT.com in Italy. So as you know, Russian news media is blocked in all of Europe, but not entirely blocked. Some networks do not block it, others do. And so, you know, what you can do is you can maybe break it down by network, and you can drill down and see, okay, can we remove the noise and try and look deeper? And sometimes that is possible, other times it is not. And so this is an example where we were looking at the blocking of these RFERL sites during the Kazakh elections. And the signal was not really clear. So we had to take steps in order to analyze it further. And basically, as part of this, we were able to confirm basically that in this case, it was not a complete block, but it was a form of throttling. So what we did here was that we were looking at the timing information related to TLS handshakes. And what we noticed is that we used as a baseline a site that was hosted on the same provider as the sites that we suspected to be throttled. And then, you know, sort of drew that baseline and said, okay, we expect the time to perform a TLS handshake to be this, but then, you know, we see in the data points for this specific news site to be significantly higher than what, you know, is our baseline. And so, you know, through this, we were able to effectively provide pretty strong evidence that it was intentionally being restricted, because there would not be any other reason why you would see such high, you know, TLS handshake times for only the specific site and not another one that would have the same network path. But yeah, this is only the starting point. I invite you to check out all the resources we have on our websites and get involved in our community. We have a public Slack channel, and I'm happy to answer any questions you may have. Thank you.
Okay, we're running fairly close to time, so if we can be fairly short on questions, but name and affiliation, please.
Maxim Tuliv, NetAssist. We are internet service provider that trying to provide internet access, clean internet without any restrictions. Is there some solution for us that can be used to know about some of our uplink ban something, just to change the road and use clean road that the resources available? So something what signals we to us that something goes wrong for this path, and we should change upstream to reach this or other city.
Like you're asking if there's something you can do to test if your upstream is implementing some form of yes. restriction. Yeah, I mean, I think running a tool like Uniprobe could help you collect this type of information. One thing to keep in mind is that, you know, we rely on testing lists. Like we cannot test all the sites and all the resources. So we have sort of manually curated lists that we work with the regional experts on, so that we have, you know, like a global one that we test everywhere, and then every country has their own that are kept up to date. But sometimes we might not be able to say, like we can say if something is blocked and we see it, that it is blocked. It is a bit harder for us to say nothing is blocked, you know, because we do not measure everything. But, you know, to some extent, you can definitely run a tool like Uniprobe, and it might provide you some useful insight. But also do reach out to me, and we can discuss this further.
Thank you.
I have a question, Bogdan Fury. Where do you get information about what to check lists? Do you track any countries or some countries who have own block list? You may get it maybe from some open.
Yeah. So we also do monitor block lists. So like, you know, I don't know, in Russia, there's Roskomnadzor that has an official list, and you can sort of download it. But as I was saying before, you know, the Roskomnadzor list is, I think, I don't know, tens or hundreds of millions of sites. So we cannot realistically scan all of those from mobile phones of our users. So we need to do some sort of selection of what is relevant to test and what is not. That's why we mostly rely, like we say, our testing lists are not block lists. They are sort of a hand-picked selection, representative selection of content that you know, might be blocked, but also might not be blocked, and that if it were to be blocked, it would have a significant impact on the country. And so, you know, we have a network of partner organizations that we collaborate with to update these. There's also a specific group called Metalytica who contracts researchers in specific region to update our lists. And so, yeah, that's sort of the process around that.
All right, thank you all. Thank you again. Round of applause. Okay, up next today we have Luca Sani. Please take the stage. Luca received his Master's in Computer Engineering from the University of Pisa and his PhD from the School of Advanced Studies of Lucca, with a thesis focused on the analysis of the tensor domain ecosystem. From 2014 to 2019, he was a researcher at the Italian National Research Council, where he worked on the Isolario project, which I know that many folks in here are familiar with. And he joined Catchpoint in 2019. So, Luca, the floor is yours.
Hello, everyone. Thank you for your introduction. I think you said everything. I just want to add a supposedly fun fact about me, which is that I'm Luca and I am from Lucca. This is usually fun for people living abroad, so I apologize for Italian people here. So that said, this talk is about traceroute, which is probably the oldest network diagnostic tool in this environment. It was firstly implemented by Jacobson in late 80s to answer the frustrating question about where are the packets going. So during the years, many different kind of traceroute implementations have been done to run especially on different operating systems, but also to address slightly different kind of problems. For example, there are traceroutes tailored to multipath tracing, alias resolution, non-traversal detection. I think everyone in this room knows, for example, the Paris, Dublin, and Pamplona variants of traceroute. So in our company, we leverage the famous Dimitri Butsko iLinux traceroute, which is very fast because it can send multiple probes in parallel per each hop. But most importantly, it is open source and it is easily extendable. So during the years, we enhanced this tool to offer new monitor capabilities. And I'm going to present you a few of them. Hopefully, you can find them useful. The traceroute enhanced is open source, so it is available to everyone. So following the tradition to name traceroutes after where the main developers reside, we decided to name it Pietrasanta traceroute. Pietrasanta is a nice city on Tuscany seaside, but also is the location of Catchpoint Italian office. So these are the announcements that I want to talk about today. Let's start from the support for QUIC. In particular, the possibility to run a QUIC traceroute. QUIC can be considered by all means a transport layer protocol, even if it runs over UDP, because over UDP it offers mechanisms like congestion control, session establishment, encryption. So it may be legitimate to think that QUIC packets may experience a different behavior in the network with respect to meaningless UDP packets like the ones sent by normal UDP traceroute. So in this mode, our traceroute sends QUIC initial packets that are used in QUIC to establish a session. These packets, as in normal traceroute behavior, have incremental TTL, so probes expiring on intermediate hops will trigger an SMP TTL exceeded error, which allows us to track the path toward the destination. When an initial packet hits the destination, we may have different possibilities, depending whether the destination speaks quick or not. If the destination speaks quick, it may reply with a quick initial packet. And in this case, we reply back with another initial packet saying that we want to continue the handshake. So we want to explicitly interrupt the session. If the destination doesn't speak quick, or maybe doesn't speak quick on the port we are targeting, probably we could receive an SMP port reachable. We are still happy because we can conclude the trace route. Otherwise, in the worst case, we won't receive any reply back. In this case, the trace route will conclude with a timeout. So the nice side effects of this trace route are that, first of all, you can check if the path from the source to destination supports quick, or if for any reason is filtered. Also, you can check if the destination speaks quick. And another thing that you can check is if the destination supports the explicit congestion notification mechanism over quick. This is possible because with this trace route, you can set the ECN at the IP level inside the probes that we send. And we can check the ECN counters in the quick reply. I won't go more in detail about that for the sake of time, but also because I saw that there will be a talk later today about ECN over quick, so I don't want to spoil anything more. So this slide summarizes the algorithm that we use to perform a quick trace route. This recalls a little the TCP alpha open technique, because in TCP you send a SYN. If the destination replies with a SYNAC, you reset the session with a reset. Another announcement that I'd like to talk about is called TCP in session. TCP in session is related to TCP trace route. In classic TCP trace route, each probe is a SYN packet. This means that when you do a TCP trace route in a very short period of time, you send a lot of SYN packets to the destination. And this has at least two main drawbacks. First of all, different SYN packets may legitimately follow different paths toward the destination. And this could be not a desirable behavior if you want to achieve, for example, consistency within a single trace route measurement. Also, sending many SYN in a very short period of time may trigger firewall protection rules from the source to the destination, because it may be seen, for example, as a SYN flood attack. So we try to overcome these problems by implementing TCP in session. In this mode, we firstly open a TCP session with a destination, and then we send trace route probes, which are TCP data packets with 1 byte payload and incremental TTL. This is inspired from TCP sidecar, but differently from sidecar, where they send duplicate data inside a previously opened TCP session, we explicitly open the session for the sake of doing the trace route. So let's say that we have this setup. There is the source, there is the destination, which is 2 hops away, and we send 2 parallel probes per hop. So the first thing that we do is to open the TCP session in usual way with the 3-way handshake. Then we start sending the TCP data packets within the opened session. The first thing that you may notice from this slide is that the sequence number that we use is not the expected one, but we explicitly insert a gap inside the sequence number stream because we don't want to bother the destination application. So since we don't know in advance how far the destination will be, starting from the very first TCP data packet that we send, we insert a gap. So we are sure that when the destination receives a packet, the TCP stack at the destination will not deliver the data to the application layer because it is incomplete. So when the data receives it's the destination will reply with an ACK. Now, the problem in inserting a gap inside the sequence number stream is that the ACK generated by the destination will ACK the same sequence number, which is the very first sequence number that is missing in the sequence. So we are not able to match properly the ACKs with the probes that triggered the ACK. So we can't compute a proper round trip time. So to overcome that, in this mode, we require the destination to support the selective acknowledgement mechanism. And this is negotiated during the TCP handshake. And if the destination supports that, each ACK that is generated will include additional information about the probes that were received by the TCP stack at destination when the ACK was generated. So in this way, we can match the ACK with the sending probe. The algorithm is a little bit more complicated than that, so I encourage you to look at the blog that we wrote about that. So to summarize, the cons of TCP insertion mode are that, first of all, it requires the destination to support the selective acknowledgement mechanism. This should not be an issue as of today, but you don't know. Also, it works only if the destination is listening on the port that we are targeting with traceroute, something that is not required by classic TCP traceroute. Another cons is that we actually open a session with the destination. So for the time of the traceroute, we consume some resource on destination. The pros are that, first of all, we send just one SYN packet per traceroute. So we avoid the problem to be seen as a SYN flood attack. And also, traceroute probes are seen as part of a data flow. So they are more likely to follow the same path from the source to the destination. This is an example of the difference between classic TCP traceroute and TCP insertion. On the top left of the slide, you have a classic TCP traceroute. We are using the standard Linux traceroute configuration, so we send 3 parallel probes per hop. You can see that for each hop, you have multiple IP addresses replying, meaning that the different SYN packets follow different paths. Also, you may notice that the destination replied only to 1 out of 3 probes. So it seems that you have some packet loss. On the bottom right, you have the TCP insertion version. And you can notice that all hops, almost all hops, have one IP address replying. And also, the destination replied to all our probes. So this is useful to achieve, let's say, more consistency within the measurement. The last announcement that I'd like to talk about is the possibility for traceroute to work into the Azure environment. So the context is the following. Let's say that you have a virtual machine, a Linux virtual machine with a private IP address hosted by Azure Cloud. So you make sure that inbound ICMP packets are allowed. But despite that, if you try to run a traceroute, you get all asterisk for all the intermediate probes up to the destination. So we investigated that, and this happens because there is a mismatch at the IP layer between the content of the probe that we send respect to the content of the ICMP TTL exceeded that we receive. So in the slide on the right, you can see the probe that is sent. In this case, this is an ICMP echo request because we are talking about an ICMP traceroute, but this affects all flavors of traceroute. In particular, you can see that the source IP address of the probe is the private one. But if you look at the payload of the ICMP TTL exceeded, as you know, you expect to see into the payload the original probe that caused the expiration. You see that the source IP address of the probe is the public one. So also, please notice that the destination address of the ICMP TTL exceeded is the private one. So somewhere there is a missing translation back between the public IP and the private IP into the encapsulated probe. So we asked Microsoft why this is happening, and they simply said that if traceroute is not working, you should use ping. This was not like a good answer because we wanted really to use traceroute. So we found a workaround to that. We introduced the so-called loose match mode inside traceroute. In this mode, we open an additional ICMP row socket. And with this socket, we are able to receive every ICMP message that is transiting on the network. And we do the checks that the kernel will do to deliver the packets to the application layer directly inside traceroute. So we check everything except the source address of the encapsulated probe. So despite that, we are pretty sure that we have enough information to be sure that the ICMP error is related to the probe that we sent. For example, in the ICMP case, we have the identification number, the sequence number, also the destination address of the probe. So there are many more enhancements that we did. The important thing is that this version of traceroute is completely open source, like the original one. Also, I want to thank Dimitri for the work that he did in the past. So feel free to contribute, to check the code, to open issues, to ask anything. And if you happen to be around Pietrasanta, feel free also to come by and meet us in the office. Thank you. And
that was brilliant and interesting. Do we have questions? Yeah, okay. Go.
Hi, my name is Alexander Azimov, Younger. Thank you for your report. I really enjoyed the idea behind the TCP traceroute. I wonder if there is an opportunity to see multiple paths by running it, but not running it multiple times.
So do you mean if you run multiple times the TCP in session, you...
Yes. So the advantage of the TCP traceroute that you can see all kinds of paths to the destination.
Yeah. So it depends the use that you want to do with the traceroute. If you want like the consistency along all the measurement, maybe you are more interested in one thing. If you want to do multipath tracing, yeah, you are absolutely right. Classic TCP traceroute.
I'm just thinking that maybe this way of traceroute can be even improved if you run multiple TCP sessions simultaneously.
Sure.
And give an output showing different paths that were discovered with these sessions. For example, have a flag that says, please run not one TCP session, but 5-10 sessions and give me the output of all these sessions.
Oh yeah, that's a good suggestion. And okay, we can work on that. Yeah, thank you very much.
Anybody else? Excellent. Thank you very much.
Thank you.
Okay, and our next speaker is Valentin Heinrich. And Valentin is a research assistant at the Technical University of Applied Sciences, Augsburg, and working mainly on network measurements and network protocol design. And take it away, Valentin.
Yeah, thanks. So hi all. Today I'm also talking about traceroute, but this time in the reverse direction. So yeah, it's about reverse traceroute. And another fun fact to start, we are also following the naming tradition, and we will call this Augsburg traceroute from the place of origin. So then we already heard a lot of stuff about traceroute, so I will keep this one quick. Traceroute is often referred to as the #1 go-to tool for troubleshooting network-related problems. And this is a quote from Richard Steenbergen. He often holds these talks about correctly troubleshooting with reverse traceroute. As it turns out, troubleshooting with traceroute can be quite challenging, even though at the surface it appears simple. I mean, the output really just is the lines of hops and the measured round trip times. So we will see soon enough an example about such a situation that appears simple at the surface, but well, it's a bit more complex if we dive into it. So I will talk about reverse traceroute. I want to define, or we want to define a protocol extension. By we, I mean myself and Rolf Winter, who also works on the project and is a co-author of the draft. So we want to extend ICMP to allow our message exchange to carry reverse traceroute messages to allow us to implement reverse traceroute from endpoint to endpoint on the internet. We have running code online in the repository that you can see here. And very soon there will be Debian packages available. This code is open source. It's licensed under the GPL. So feel free to play around with it. So then, let's start. Suppose you assume that you have a problem, you fire up traceroute, and you get this output. Okay, so it looks quite simple. We have 5 hops in total, and we start at the router in Augsburg. We go over Munich, then 2 routers in Frankfurt, and then finally we reach the destination. And we can see that there is a spike in the reported round-trip times starting at hop 4. And this increase in the round-trip time, it also holds for the last hop. So what would be your conclusion? Basically, we have 3 different options. Option A, I mean, I don't see a problem here. This is how it should be. Option B would be, well, there must be something wrong between router C and D because that's where we can first observe the spike in the round-trip times. And the last option would be, well, we cannot really tell given this output alone. Now, if you go with option C, then you are correct because as we can see by this topology, you cannot really tell by the output alone because the trace that you saw before maps 1-to-1 to the topology you can see here. So if you were to run traceroute on the client on the left-hand side towards the server on the right-hand side, that's the output that you would get. And judging as an outside observer from the topology, we can see there is no problem between router C and D, but in fact, there is a problem on the return path. And that's a major limitation of traceroute because while traceroute is only able to illuminate the forward path, to measure the forward path, the round-trip time measurements for the forward path are still influenced by the return path. So in this example, when the client's traceroute probes reach the router D, and they generate a time to live exceeded message, this ICMP error message will take the return path over router E and F and not the forward path anymore. So the congested link in this example between router E and F will introduce the previously observed spike in the round-trip time measurements. And this may lead us to false conclusions. So there is a simple solution to fix this. We need to get the entire picture of the network. And for this, we cannot rely only on forward traceroute, on classic traceroute. We need reverse traceroute as well. So reverse traceroute, that's not a new idea. It dates back to 1993, where it was implemented as an IPv4 option. So the idea was we define an IP option, we encode the originator source address inside this IP option, and then we send the packet towards the destination. Now, each router on the path towards the destination that encounters this IP option sends back a special traceroute message to the originator. And now the originator only has to collect these special traceroute messages and is able to discover the complete forward path. Now, the same holds for the reverse path. When the destination replies and keeps the same IP option intact. And following the same manner, the originator can simply collect the issued packets and also illuminate the return path. And this is a very elegant solution, but it has a few shortcomings. And one is router support was involved. And we all know that when we need router support for an implementation, that deployment will get much, much more difficult. Also, IP options were employed, and IP options in today's internet are frequently stripped or filtered. And there was also a potential attack vector where the originator's IP address in the traceroute option could be spoofed, and thus an amplification attack could be launched. So we want to learn from this past attempt, and we don't want to require any router support at all. We do not use IP options, and we also want to keep the attack surface for amplification attacks as low as possible. And this led us to the following message exchange. Now, I already mentioned that we are using ICMP for reverse traceroute. And the way it works is that the client sends one reverse traceroute request over ICMP to a server. Now, inside this request, the client can supply a configuration, and the configuration determines what attributes the probe that will be issued back by the server towards the client will have. So specifically, the client can specify, do we want to use a UDP, TCP, or ICMP probe? The client can specify, of course, the time to live at which the traceroute probe should exceed. And of course, the client should be multipath aware. This means the client should be able to control a field that is relevant for load balancing on today's internet, so that when a load balancer is present on the return path, the client can actually perform multipath tracing. It can control on which path the probe should travel. So then in step 2, after passing this configuration in the reverse traceroute request, the server assembles the probe and it sends it back in step 2 towards the client. In this specific example, the time to live of 2 was given. So at router E, the probe expires in step 3. We get back the time to live exceeded message. And yeah, we can calculate the round trip time now between receiving the probe's response in step 3 and sending the probe in step 2. We augment this information with the source address of the probe's response, and we deliver this information back to the client in a new ICMP reverse traceroute response. And this way, a client is able to request reverse traceroute measurements probe by probe from a remote destination. Well, basically, that's the message exchange. Now, I want to dig a bit more into the details, specifically the code points. But first of all, reverse traceroute is defined for both ICMP and ICMP-v6. And for both, the message typically starts like this. I mean, we have a type, we have a code, we have a checksum, and then some message-specific data. And now the question that we have to ask ourselves is, do we want to use new types and new codes for these reverse traceroute messages, or do we want to reuse an existing type? And really, the decision of which approach we choose, it boils down to which one does actually work on today's ossified internet. And for this, we tested a few metal boxes. But first, a few notes about ossification. So ossification in the internet is unfortunately quite common, and the biggest contributors are middle boxes. So ossification happens when a middle box assumes that it has complete understanding of how the internet works today. And when it sees unseen packets, it thus enforces a restrictive behavior towards those packets, which means that unseen packets, unknown packets can be dropped by those middle boxes, which makes the implementation of new protocols really, really hard. So we tested 12 different NAT implementations, which were typical home gateways. And we wanted to figure out which option works, option A or option B. So we first started by sending ICMP echo request packets through these middle boxes. So we start with option B first. And we did not send regular ICMP echo request packets, but we used a new code, codes 1 and 2 respectively. And if these requests, they made it through the NAT implementation, then we followed up with a response and checked if the response with a magic code was also able to traverse the NAT implementation. And you can see in the first 2 rows of this table that the results were actually quite promising. So 11 out of 12 of these NAT implementations, they actually correctly forwarded both the requests and the responses with code 1 and 2 correctly. Now only a single implementation actually dropped the response. Now, if we have a look at the results for the yet unassigned types, which would be types 7 and 252, we get a different picture, because in this case, only a single middle box correctly forwarded the traffic. Now, the majority of these NAT implementations, they dropped these unknown types, and bypassed is really interesting because a bunch of these NAT implementations, they actually forwarded the traffic, but they did not perform network address translation. So they sent out a packet and left a private source address in place. So this makes no sense at all, but yeah. So in the previous measurements, from the previous measurement, we can conclude that reusing the ICMP echo types and extending those with new codes is good for deployability. On the other hand, using unassigned types will fail at the home gateway boundary. So with regards for deployability, we can forget this case. But just because these ICMP echo types with the new codes make it through home gateways does not give us any guarantee that these packets will make it through the public internet. So to figure this one out, we performed another measurement. And this time we picked 10 million IPv4 addresses at random, and we pinged each one of those. And the ones that pinged back, well, the ones we kept in the list. So for each host that responded, we then sent another ICMP echo packet with now the new codes, code 1. We collected the responses and we categorized the responses as shown by the table below. Now, filtered means that we did not get any response to these echo requests with code 1 back. This is the case in about 4% of the total collected responses. So reflective means we did get the response back and that the responses code matches the requests code. And this is really good news for us because what this means is that both the echo request and the echo response with code 1, they made it through the public internet, unfiltered and unaltered in the vast majority of cases, which means we can use these echo types with code 1 well to deploy reverse traceroute messages. And that's the case in over 92% of the cases. Unreflective means that we got back a response, but it was really just a typical ICMP echo response with code 1. And erroneous are any responses that we cannot put in any of the previous bins. So overall, the conclusion that we can take away here is that we have to use the existing types, extend them with a new code, and this is exactly what we are doing in our reverse traceroute draft, where we use ICMP echo and extend them with a new code. So as a conclusion, if you are interested, then you can read the draft, it's online. You can join the discussion at the Interior Working Group mailing list. Any feedback would be welcome. If you want to get even more involved, you can offer to host a reverse traceroute endpoint. As mentioned, the code is online, and we will soon have Debian packages for ease of installation. You can use our reverse traceroute client, which, by the way, is also multipath capable, and it renders multiple different paths to a graph. And you can send us the output. And what, of course, would be a huge boost if we could talk about reverse traceroute as being part of Atlas in the future. Thanks for your attention. That's all.
Thank you very much. Thank you. Oh, I'm not going to even ask. We have a question.
Hi, my name is Alexander Azimov-Younger. Thank you for your report. A couple of questions. First question is, don't you feel that you are using RPC call on top of ICMP transport?
Can you ask the question again, please?
So I have a feeling that you are using reinventing RPC with ICMP transport. You are making a request to execute something on other device, but using ICMP for this purpose.
Actually, no, that's not what we're doing. We want to extend ICMP to function like ping, but implement this reverse traceroute functionality. We don't want to these remote procedure calls, as you call them.
Okay, and another question. Okay, what about spoofing and how the service discovery should be working?
Service discovery is actually quite easy to implement. So the client sends an invalid time to live in its request, and the server then responds with a packet that can be easily distinguished from a typical ICMP echo response. And so this way, the client can figure out that this endpoint is actually running a reverse traceroute instance.
Okay, and what about spoofing?
We don't have any countermeasures for spoofing as such. Well, we rely on source address validation, but the next release for reverse traceroute will have source network filters, so you can restrict the addresses from which the request can be requested.
Okay, thank you for your answers.
Thank you very much. Okay, really quick, please, really quick.
Yes, Harry Cross here. Just an extension of the last point. Have you thought about adding authentication, just so that you can control a little bit further who can request a reverse?
No, we have not yet thought about authentication. We wanted to keep it as simple as possible.
Thank you.
Thank you very much. Thank you very much, Valentin. Okay, and then we go with the next presenter, Sander Konstantin. Oh, it's remote. I forgot about it. Sorry. So Sander Konstantin is 40-year PhD student at Aachen University in Germany. His research interests center around modern network protocols, where he analyzes their usage and performance. Then the remote stage is yours in this case.
Yes. Thank you for your introduction. Yes, as said, my name is Konstantin. I'm a PhD student at RWTH Aachen University, but this is joint work with my colleagues and also colleagues from Technical University of Munich. And we looked into using ECN with QUIC. We already heard that QUIC can use ECN. And we looked at it in the wild and made a large-scale measurement campaign to check whether it can be used. But before getting into the details, let me give you a short recap on ECN and how it can be used. So let's say we have a transport connection and we are not using ECN at the moment, and everything is fine. Packets are sent from our sender and are received at our receiver, and our receiver just acknowledges this. But we can see that one of the routers already has a filled up queue. And when we get to the point, of course, when the queue is full, packets are lost. And then, of course, our AX stream is interrupted. And our sender has to wait some time until it triggers a retransmission, and then it can also reduce its sending rate, for example, to then relieve the congestion. What we do with ECN is that we mark packets instead of dropping them during the congestion. So when our router sees that the queue is filling up, it can mark the packet now, but can still forward it. And this marked packet is then received at the receiver, and the receiver can acknowledge it, but can also tell the sender, okay, there has been some congestion on our path, please reduce your sending rate, and then the congestion is relieved. This, of course, requires some interaction on the network layer, so our routers have to mark packets, and on our transport layer, because our end hosts have to send back this information to the sender. And on the network layer, we have a 2-bit ECT field. This basically tells routers that ECN can be used. So this is signaled by using ECT0 or ECT1 signals. These signals had the same meaning at the beginning, but now have a different meaning. I will get to that in a minute. And then there's also the congestion experience flag, which is basically used by the routers to mark the packets. And of course, our transport layer has to mirror this congestion experience back to the sender so that it knows that it has to adjust the sending rate. However, ECN has been standardized after TCP and IP have already been standardized. So TCP has to negotiate ECN support. There's a lot of related work on this, which sees that from its introduction in 2001 up to now, we see a rising support. But this related work also found path impairments, which can hinder ECN. Of course, if there's a router on the path, which basically just removes the ECT fields, or if there's a middle box, which changes the meaning of these fields, this can, of course, impair ECN. With QUIC, stacks should support ECN right away. In the RFC of QUIC, it's said that it's a must that every QUIC stack has to basically mirror these ECN signals back to the sender. However, this is kind of opaque. It also says in the next sentence that a QUIC stack can decide to not do this, although it's a must. So there's also an erratum on this where this sentence should be changed. But what QUIC does is that it has some code point pointers. So it's not mirroring just CE, but also the ECT0 and the ECT1 information back to the sender, and the sender can then do some ECN validation. And some stacks also already support L4S, which is reusing these ECT0 and ECT1 fields to distinguish between different traffics. So this is the point where the signals ECT0 and ECT1 now have a different meaning than before. But related work also finds there's very low ECN usage on UDP port 443, which is basically used for QUIC and H3.3. So we see that there are new stacks, a completely new protocol. There's this new ECN validation method, and we see hints for low usage. So the question is whether ECN can be actually used with QUIC. And for this, we look at whether stacks are mirroring ECN, where they are not doing so, and whether ECN validation always passes. Okay, so let's get into our results. And what we do is that we visit websites via HTTP3 and log ECN counters. And we do this for the Alexa, Trenco, Umbrella, Majestic top lists. These are top lists based on DNS or somehow other computed top lists. So, for example, the Alexa top list reused toolbar information. And then we also have the ComNet.org domain lists, which we then scan basically for QUIC and ECN usage. And what we can find is that of 2.7 million domains of our domain top lists, we see that around 1/10 supports QUIC, and only 3.3% of these QUIC domains basically also support ECN. For ComNet.org, we see that 180 million domains were scanned by our measurements, and only 17.3 million support QUIC, and of these 5.6% support ECN, so are mirroring back ECN signals. So given that mirroring should be actually mandatory, we see a very low support. We then also looked into the hosts which are involved, which is a lot less, but we also see a higher support among hosts and among the domains on a relative scale. So we see that fewer hosts are accountable for more domains which are not supporting ECN. So this is a potential hint at content centralization and content provider stacks not supporting ECN. We analyzed this further and looked into the ASs which are involved. And indeed, we find that the big hyperscalers such as Cloudflare, Google, Fastly are not supporting ECN, but we see that smaller ASs and, for example, also which are then using Lightspeed HV3, and for example, Amazon CloudFront CDN is using ECN. And we also see some tests by Google where suddenly ECN has been mirrored. Okay, so we see that only a few domains supported. The question is now why? And this could be either due to stacks that are ignoring ECN or due to the network clearing code points. So it could be that a stack is not receiving any ECN code points because one of the routers on the path is simply removing the information. And for this, we are using Tracebox. We already heard about traceroute. Tracebox is a traceroute variant, you could say. And similar to related work, we are using this to trace the paths of all the domains that are supporting ECN and which were not supporting ECN. And we found for 97.5% of the domains that there hasn't been any visible ECN clearing for this path. For 2%, we found a visible clearing, and for 0.5%, we didn't trace this as we are subsampling our measurements to relieve the network. And for this 2% where we saw the visible clearing, we saw a single tier 1 ISP, which impacted 98.6% of these domains. This especially affected smaller hosters, especially after we saw route changes in December 2022. We are doing our measurements from Aachen here, which is using the German research network. And there has been some route changes at the beginning of December from one ISP to another. And after that, we suddenly saw a rapid decrease in ECN usage here. But what we can also see is the missing support by content providers. These were not routed through this ISP, is not due to clearing. So we even tested whether they support ECN via TCP. Most of them do. So either the QUIC stacks or undiscovered middle boxes on the path are simply removing ECN here. Okay, so now we see that a lot of QUIC stacks are not supporting it. They are also routers. But the next question is, just because ECN is mirrored, it doesn't mean that it's also used by our transport connections, because QUIC requires an ECN validation to use ECN. Basically, this ECN validation checks whether the first packets have had a timeout, so whether there has been some ECN blackholing, for example, so routers that see ECN signals simply drop packets, or whether there have been wrong code points set, so we are using ECT0, we are signaling ECT0 at the beginning, but our reply basically says ECT1, so there has been some change on the path, or whether we saw missing or undercounted code points. So for example, when the path changes, that one router does not support ECN anymore, but at the beginning, the path supported ECN. And we looked into this and found that 0.2% of the ComNet.org domains only passed this validation. So a lot of domains failed this. And 96% of the mirroring domains that failed basically failed due to two reasons: undercounting and remarking. For undercounting, we've mainly found the Google AS. Here we see very weird scenarios where suddenly we see only one packet, for example, marked with ECN. Already we are exchanging a lot more packets, or seeing a lot of marked packets, although we are only not marking our packets at the beginning. And related work suspects that Google is using some kind of data center TCP inside its data centers. And it could be that QUIC, for example, here leaks internal data center TCP states through its connection. And another way that we found that ECN is unaccounted is the Lightspeed server, which we already heard at the beginning that the smaller hosters are using. And here at the connection initialization phase, ECN was still mirrored, but at some point the implementation switches between packet spaces, and from that point on, ECN is disabled. For the remarking, we again found network elements of the tier 1 ISP. So there are not just clearing code points, but also rewriting code points in the routers. And again, Google's AS, probably again due to the data center TCP usage. Okay, so what does all of this mean altogether? ECN with QUIC is challenged due to multiple effects. We have seen that several QUIC stacks do not mirror ECN. We have seen that some network elements clear signals, and we have seen that often ECN validation fails due to stack and network impairments. However, what we also saw in our paper is that usage is not limited just here in Aachen, but also on a global scale. On the global scale, we do not see more than 0.4% of past ECN validation. So basically with all of the domains, or let's not say all of the domains, but with many of the domains that are supporting ECN quick, ECN cannot be used. And we also saw that the usage is limited for IPv6 because especially the hyperscalers are using IPv6 and the smaller hosters often do not support it. So the ECN validation ranges are even lower in that regard. We also saw this on a longitudinal scale, but I will get to that in a moment. However, this is not just interesting for ECN, but these findings also present challenges for novel ECN mechanisms such as L4S. As I already said, a lot of quick stacks are already supporting L4S, but L4S can also be used with TCP. And it's very important that the ECT0 and ECT1 signals are not changed. We saw a lot of these ECT0 to ECT1 remarkings on our path, however. And this remarking is detrimental because then traditional and L4S traffic mix up in the same queues. Traditional traffic gets a lot of ECN signals. For example, a lot of congestion experience signals, and the L4S traffic and the traditional traffic mix up in the queues, so we also have higher packet loss here. But this is the good thing that we saw in our measurements. The trend is probably to be increasing. We see a lot of changes over time and a growing trend. There's an RFC erratum, which may trigger rework of quick stacks. It will probably not trigger 100% support, but we already see a lot of changes in stacks. And we also have open tickets with stack vendors, and an ISP already debugs its routers to see why ECN fields are changed here. This is it. Thank you.
Excellent. Thank you. Excellent. Thank you very much. Do we have questions? All right. I actually have a question. So do you think that given that if the trends continue and we would reach a point where the ISPs will be free of remarking and all the the quick stats would mirror ECN, we would never see packet loss on the internet again?
That's a good question, because just because ECN is not impaired on the paths doesn't exactly mean that it's working. This is really hard to check because, of course, this congestion experience signal has to be set at some point. So the routers have to decide when to set it. And just because they are not impairing the ECN signals doesn't really mean that they're also using these methods to decide when to say, when to mark packets as congestion experience. So it's hard to say, and probably a lot of routers are not configured in that way. So I guess packet loss will be here to stay.
Damn. Okay. Well, thank you very much anyways. It was really interesting. So next up is Robert Kisteliki. I still can't pronounce your last name, even I tried many times. And as we all know, Robert has been the lead of the RIPE-NCC research and development activities for the past 15 years and is now a principal engineer at RIPE-NCC. But so he's going to do the RIPE-NCC tools update as always, and thank you.
Okay, thank you very much. 15 minutes, what am I going to do with 15 minutes? I usually get -2. That's fine, but we're still here. We're still going to do that. As usual, I'm giving you update about the measurement related activities of the RIPE-NCC in this form. First of all, RIPE-RIS. So that's the routing information system, as you probably all know. The RIS team plans to make a change in how routing beacons work. This change is scheduled for Q1 2024. The details you can read in the Labs article that we published during the summertime. The short version of that is that, as some of you may know, RIS is not only a passive measurement system, but it also injects some stuff into the routing system, in particular beacons. So there are things that go announced and then revoked later on. As I said, the team wants to change that behavior. Particulars are in that article. And of course, this working group and also the RIS users will be in the loop of this. Peering strategy. So it's not always true that more data is always good. More information is better. And what we've seen is RIS is collecting a lot of redundant data from full feed peers, from other peers, and that results in increasing volumes of data that we have to store and provide to the community. So the question is, should we change this? And the team has been moving into this direction recently in the last year or two. As you can see, they have been targeting particular populations, tier 1 networks, and then countries well not covered, and then regions. And we wrote up what we've seen as a outcome of that, again, on RIPE Labs, so you can go there and read the details. For this reason, for the moment, we temporarily suspended the peering form, so you can't just fill it in and say, let's peer together. And if you have stuff to say about this, then Michaela is one person who you can talk to, or Jelena, not in this room, she's in a different room, but you can also just talk to us via the usual channels, forum, and the mailing list and so on. RIPE-Stat. As you probably know, RIPE-Stat has what we call, I think the team internally called it the classical UI that was added in 2013. This is a collection of widgets and some framework around that. You can use these widgets yourself, you can embed it in pages and so on. But this has been aging, so the team had to look at it because it was using older technologies. So they upgraded it, revitalized it, so to speak. Feel free to use it still. And if you're using the old version of the widget API, then you're strongly encouraged to move on because the new one is better and more secure as well. At the same time, they have introduced a new UI, which we anticipated to be generally better than the old one. But the feedback that we got is not necessarily confirming this. So the team is looking at, again, whether this is a direction that they should still support, whether the old UI should come back, the new UI should go, whether there are different niches where they are useful. So they're reviewing all that feedback and going to make a decision, or at least a proposal to go forward in the coming period. They also brought back the MLab widgets, as we call them. So these are widgets that are powered by data coming from the measurement lab people. Thank you for that data set. They include the bandwidth capacity, so any random network has bandwidth measurements run by MLab and their partners, and the data is exposed in stat as well, and also network activity, which sections of the network were active, and so on. And these support prefixes and countries as well. The stat team is also focusing on the data quality. Of course, you can imagine all the services have ups and downs, hiccups, and so on. They are trying to stabilize the backend, and I think they made good progress on there. They're also looking at the data quality presented by RIPE-Stat, because that's one of the feedback that we get, that we should really be focusing on that, not only on stat in general, but in this particular case, in stat. Now, RIPE Atlas. Some of you may recall that RIPE Atlas was launched here in Rome, almost exactly 13 years ago. So it was November 1st, I think, or 10th or so, 2010. And Andreas and Victor were sitting in the hall and giving out probes to people who were interested. So that's an interesting historical remark. What's happening nowadays is that we are working on renewing the user interface of RIPE Atlas. You may have seen changes already. In particular, sorry, this is coming later on. Renewing the big data backend that we have. We have been using a Hadoop/H-based backend for a long time now, and it's aging. We have to look at how that works and what can we do with that. And in general, we are trying to be more cost conscious and looking at options about how we can still store and provide this data. In particular, we are going to move older data out of this, what we call hot store, into a colder store, and try to do it in such a way that the users don't even notice. So if you're asking for older data, you will still get it. You may have to wait a slightly longer period, but you will still get it. That's the plan, at least. And at the same time, we are renewing what we call the hot store. So that's like the most recent data, the last couple of days or weeks or months. We're also renewing the infrastructure components. You can imagine that There are a whole bunch of components running the show, managing the probes, storing the data, the metadata, and so on, serving the data to the users, user interfaces, and so on. We're busy renewing those as well. And for all of these, we're looking at how the cloud technologies can support us, whether it makes sense to move some data or components onto the cloud when it doesn't make sense. Now can we come to the user interface? You probably have seen changes. In particular, the documentation side and the coverage and statistics have been renewed already. But we also put out a new measurement form, measurement listing, probe listing. These are meant to be nicer, better, more responsive than the old versions. And we plan to decommission the old versions after the RIPE meeting. So they are still there. If for some reason you need to go back to the old forms, the old listings, you can still do that. And we also put out what we call the beta UI. So if you really want to look at what is our kind of ideal goal, where we want to get to, then feel free to go there and take a peek. Also, Michaela is doing user testing, so usability, user interface, user experience, and so on. So feel free to find her and her companions in the coffee break area. Thank you. And we're still working on the probe firmware packaging. We haven't made as much progress as we wanted to, but we're on this as well. Now, excuse me. So in the second half of the presentation, I'm going to talk about two proposals that the RIPE Atlas team and the NCC in particular is putting out for the community and the MAT working group because of we see what's happening in the system, and we get signals that some things may need to change. So we would like to be a bit proactive and make two proposals in particular. One is the role of the aggregators. A recent discussion on the mailing list highlighted that there are users of RIPE Atlas who are acting as some kind of integrators, repackaging Atlas's functionality into their own offerings. And these could be sponsors, these could be profits and non-profits, and so on and so forth. But they do provide additional value to the community via these activities. So we have to recognize that. Especially in cases where the Atlas team itself or the service itself cannot get there because of resource reasons or other reasons. But this also skews our understanding of what the users are doing, how many there are, and why they are using the service. So what the proposal is to basically put this on the table, so to speak, and not just under the table. So let's formally recognize that this thing exists, and let's call them aggregators for the sake of arguments. We want to change the framework that we have to accommodate for this, and just say, yeah, this is a thing, but then if you do that, then the following rules apply. For example, we would propose that this should be an account that is identified as such. This is an aggregator account, as opposed to I'm using this for the whole of my NOC activities. So my NOC people are using also this account. Most importantly, I think the aggregators would need to supply some kind of identification of the users. Now, we're not talking about PII, personal information here, but it is more like a signal that this client is a different one than that client. Okay. This would also let the aggregators do kind of anonymous services if they want to do that, right? So we don't necessarily need IP addresses, email addresses, or anything that the aggregators may not even know, but it is a signal that there are different clients and how many of them. As you can imagine, at some point, if this goes above some limit, then this is a lot of usage. So if an aggregator is doing 100 measurements a day or 1,000 measurements a day, that's probably fine. But when they do multiple thousands or millions of measurements a day, in the extreme case, that is something that we might want to emphasize, that then please be a sponsor of RIPE Atlas. Okay, so with this change, we expect that the community will be aware of this, that this is actually happening, and then we can consistently enforce the rules against it, right? So if there are responsibilities and benefits, then all those will be consistently applied to everyone. And internally, and also when we report back to you about usages and so on, this would actually let us count properly to know how many users we actually have. Because if you think about it, in the extreme case, If there are 10 aggregators and everyone is using the aggregator services, we would think that we have 10 users, and that's not correct. So then the other proposal. RIS and Atlas have been around for some years now, since 1999 and 2010. And they have been collecting and serving that data to the community and to all of the users. All the historical data is still available that we ever collected. There is arguably high value for this data. We sometimes hear that explicitly said out loud. Sometimes we understand it from the actions of people that this data is still used, even if it's historical, even if it's old. There is a lot of value to it. But for the NCC purposes, it has costs that we still keep around this data. We serve it to you if you ask for it. That definitely comes with some costs. In our efforts to be a bit more cost conscious, we are reviewing if we need to do this, we need to keep on doing this, or we need to change. So in particular, we put out the proposal, and both of the proposals, by the way, have REBS articles behind them. So if you want to read the full text, I would ask you to read those articles. But in this case, about the data retention, we would like to propose a principles, so to speak. Okay, we don't want to call it policy, but let's call it principles. First of all, this is mostly from more generic to more specific order. So first of all, the NCC should retain as much data as possible in a financially sustainable way, right? So it's literally what it is. In general, all this data should be available to the users. Right? If we keep it, we don't want to keep it to ourselves and do analysis that you yourself couldn't do. The data should be available to everyone. However, because some data is accessed more frequently, especially the newer data is accessed almost immediately, and as it ages, it's less and less frequently used. We want to tailor the system such that we find cheaper solutions for data that is not as hot, not as frequently used. It's logical, but it is one of the principles that we want to lay down. Then, of course, Atlas is different than RIS. They probably will have different systems and different cutoffs and different policies on what we call old data, what we call new data. So these kind of tiers would be tailored to the system itself. We would also like to ask people to identify themselves when they are asking for this data. At the moment, fully anonymous access to all this data is possible, which is okay, that's totally fine. But then if we, in cases exceed bandwidth limits and so on and so forth, it is highly useful to know who these people are, if we can pool them together, or we need to provide bigger capacity to some group of users. It would also let us know how many people are actually downloading the data, and maybe we can ask why that is. And the most specific thing is RIPE Atlas has something that we call non-public measurements. You can call them private measurements, but the official term is non-public measurements. And there are reasons for this. The users have been asking for this, so that's fine. But this data is not available by its virtue. It's private data. It's non-public measurement. It's not available to everyone. So we would like to propose that the retention period for this should be much shorter, because it is only really useful for the people who wanted it, and for them probably only in the short term. So these are two proposals, and I guess it's going to be up to the working group chairs to decide how the discussion is happening. But from our perspective, we would really love to hear you if you agree, disagree. Should we change these? In general, it's fine. Just go for it or not, because this is, from our perspective, a proposal. And while the discussion is happening, I have been asked by the lovely training team to put up this slide. And if you want to have some feedback to them, you can do that right now or later on as well.
All right, thank you, Robert. We have in the queue, Simon is in the queue on Meet Echo. Simon, can you enable your, here we go. Can you enable your audio and video? And while you click around, we'll take the front of the mic, please.
Yeah, I think something's happening. I see
sorry.
myself. I hope someone can hear me.
Will you allow Simon?
Oh, awesome. Thanks. Yeah, thanks for working on this. I'm happy to that you consider the needs of these aggregators. And actually, this is something I'd like to encourage you to do, and try not to make the requirements too onerous. I see the NCC as the stewards of the Atlas data, and hope that you will not fall in the trap of thinking you have to a kind of monopoly and have to see how to share the data and lose control of like accurately counting the visitors. I hope this can be done in a pragmatic way. On the retention, I think that's also good thinking. What I'm wondering about is this goal of sustainability. How can you decide? Because I'm see that this can like easily be skewed one way or the other. How do you decide whether the costs of storing the data or retaining the data is sustainable compared to what? Is there like income related to the stored data, or are you looking for sponsors or something to ensure sustainability? That part is unclear to me. To me, it's very qualitative. Some manager will decide, well, this is too expensive, and they will say it's not sustainable, and then they will be thrown away. Or do you have any objective criteria in mind? Thanks.
Not at the moment. I think we are also looking for guidance on that, what can be considered sustainable. But let me give you a negative example. What is not sustainable is to say, please keep all the data and don't spend money on it. Right? So that would be somewhat unsustainable. So of course, we want to and can be more specific than this. But that's, as a principle, as a guiding line, let's put it, this is what we want. On the highest level, I think that needed to be said. Okay.
Okay. We are about to run a little bit over time. We're going to allow that. We're going to give a few more minutes for this because this is an interesting topic. But if we can keep questions fairly short.
Hey.
And then this is going to be taken to the mailing list for sure.
Yeah, Gerd Döring. I generally agree to the principles proposed.
Yeah.
On the sustainability bit, it might be useful to actually have numbers like we are paying 50 million for the storage of the data every month. And if we just move it all to this old tape drive, it will be down to 10 euros. More realistical things like I could see like fast access in the cloud being really, really expensive and having a RAID array somewhere being less expensive, but I don't know how much. And of course, this needs to be in relationship to the budget and the NCC budget discussions and all of that. But I actually wanted to ask about the aggregators. If they can do thousands of measurements a day, they have to have credits. So if they have credits, they provide probes. So they bring value. So having the aggregators here is a good thing because they bring measurement value. But trying to formalize this in a useful way is also a good thing. So go on.
Okay, thank you.
Randy Bush, IIJ Research and Arcus. I'm a consumer and I'm not going to weigh in on these proposals. I'm interested still for the 1,312th time on knowing what kind of peering each RIS peer gives. Is it a customer view, an internal view, et cetera, et cetera? We've discussed this. I'd like to keep that question alive. I'd also love the security test of the QR code.
Thank you, Randy.
So Massimo Candela, the first thing is, as Matt working group chair, is like, if you can briefly provide exactly what the people have to do to like, do you have a form? Do you have a questionnaire? Do you have something? Do they have to send just an email about the 2 proposals? That's the first question. The second question is, I removed the hat of Math Working Group Chair. So I think the entire topic, I just say that I'm strongly against the aggregator thing. I'm sorry. I think the entire topic started because of lack of attribution, and I think we should focus on that. And the aggregator thing is, the original deal was you have credits because you host a probe, then with the credits you do whatever you want. I'm totally in with providing you with metadata so that you can recognize user and whatever. But I'm against, for example, things like, oh, if you reach a certain level, then you have to sponsor something like this. So in addition to host probes, you have to sponsor. Basically, to me, it looks like a bit like commercializing. There is a free tier, and then you have to sponsor to. I mean, I really prefer the model that you host, you have the credits, whatever you want to do with it, that's fine. Also, we all do some kind of earning with Atlas in a way. If I do troubleshooting for work, I am doing something that in the end is business related. So I really don't see how you can draw the line, and it looks to me something that is going to complicate and put limits on how to use the data and the usefulness of hosting probes and stuff. So this is my feedback, as I said, not as a chair. Please.
Okay. So to answer your first one, we have a forum topic open for one proposal and another forum topic for the other. We have the Math Working Group mailing list. I personally, encourage everyone, whichever you prefer, to provide feedback there. But it's not only feedback. I think it's a discussion that we need to have. Like what you just said makes sense to me. This is one view. Whether that is a consensus or not, that we don't know yet. But that's why we would like to hear people's opinions and input to this.
Perfect. Thank you very much.
Thanks.
Christelle Belser, UC Louvain. So I'm a big user of RIST and RIPE Atlas data, which I find very useful. And I think storing all this data on Corder storage makes perfectly sense. What we've been working on with some of my PhD students and postdocs is on looking forwards on how to store the data. Because as you said, there is a lot of redundancy. So we are investigating ways to determine what is redundant right from the start and to discard it right away. So we have a submission at Hotnets who is presented today. And so you may want to have a look, and we may collaborate on this if you're interested.
Yeah, that's a really good idea. Thank you.
Just a quick comment. My name is Ivan Beveridge. With regard, as you're aware, I believe that some of the use of the aggregators is potentially commercial, but some is kind of providing facility for other users. So this, person may be doing it kind of for free for hosting a website and providing functionality. So it's not necessarily that there's commercial gain from that. It's just a comment.
That's very fair, and I can imagine a scenario where we make a distinction between academic aggregation versus for-profit versus non-profit. That's I guess it's all possible. Whether we want to go that far, that's I guess that's part of the discussion.
Okay, thank you, Robert. Thank you all. There are topics on the mailing lists. We will probably bump those. It would be good to continue the conversation over there. And so this was our agenda. I guess is this hot? There we go. Yeah. Let me figure out this. Yes. So this was our agenda. Thank you to all of our speakers. And yes. So comments and remarks onto the lists, either directly to us for the chairs or onto the general Math Working Group mailing list. Two important announcements that we need to bring up. One is verbal. The PC elections are open, so vote early, but hopefully don't vote often. You can find the nominee bios on the RIPE87 website. And even more important, logistics for this evening. There will be shuttle buses running to the boat. I hear we're going to be on a boat. And the buses will be departing from buildings 1 and building 2. The return buses are running every 30 minutes, but apparently there's only one return bus that will stop at the Ibis Hotel. So if you're staying there, you have to stay out and enjoy yourself until after midnight. That's a requirement. This is mandatory fun. And that's it. See you at RIPE 88. Thank you all.
Yep. Yeah, he's over there. Yeah. Hi, everyone. Can you hear me? So, welcome to the last session of this day, the multicast BOF. The title is IP Multicast Revisited, Setups, Use Cases, and Interdomain. And it's my pleasure to host this session together with Flavio from Namex, Freddy from Init7, and Viljana from Z2. So this is a birds of feather meeting in case it's your first. BOFs are usually about fostering discussion. So this one is specifically about fostering discussion on interdomain in brackets multicast. So most of the time on this slot, we won't have a fixed agenda. You hear that I'm saying most, that also means that part of the time we do have a fixed agenda, which is rather unusual for BOF meetings. But I will explain in a few minutes why. So we want to make your voice heard on this topic, but we limit mic time to 5 minutes, just for you as orientation. And, you know, it's an open discussion, so please behave like a human being and also be aware that this session is recorded. And in general, I want you to feel free to talk about your multicast setups, your use cases, your experiences or challenges, and especially if you have experiences with interdomain setups, we would be interested in hearing those as well. So why are we actually here? So multicast is a very old technology. And I have a little anecdote from last week's DENOG meeting. I was talking to some guy from a small ISP in Germany. And he told me, you know, I love my job, but I'm fed up with building my network for the soccer championships. And I think that pretty much hits the point because, you know, live events like soccer and flash crowds are really dominating and can be challenging for capacity management. And we see an increasing deployment of multicast within ISPs for live streaming use cases, exactly like the soccer championships. There are several also large incumbent providers that are deploying this. And we're here because I want to know whether we as operators can manage multicast better, for instance, interdomain. And as someone working for a large IXP, I'm in particular interested in should or could IXP support interdomain multicast on the internet. And that brings me to the agenda. So now we have the introduction, and multicast is a multifaceted topic. So it very much depends on what network you run. And that's why we decided that we will have upfront three 5-minute presentations from different perspectives on this topic. So the first one is the ISP perspective by Freddy. The second one is the IXP perspective by Flavio, and the third one is the content provider perspective by Viljana. And after that, we're going to start with a discussion session for around 40 minutes until 7. So I know I'm standing between you and the social, but no worries. The buses will leave much later, 2015, so you won't miss anything this evening. And as the first speaker that is now going to present the ISP perspective is, as I said, Freddy. And Freddy is the CEO and network architect of Init7. At least that's what LinkedIn says. Freddy, is that correct? Init7 is an ISP in Switzerland, and he's very well known for his stance on high quality internet and for battling large incumbent providers into submission on last mile issues. So if you want to know more about that, just Google his name. I assure you it's entertaining. And with that, I would like to pass over to Freddy. The floor is yours.
Buonasera. As you know, Switzerland has 3 languages, actually 4 languages. I tried to learn the third one, Italian, so buonasera. I'm quickly going through this multicast slide, so what we're doing. First, few words about Init7. We are one of the remaining independent ISPs, and we operate an FTTH infrastructure, and this gives us the ability to use multicast. So we run our own equipment. There are about 215 FTTH POPs currently and about 100 under construction, and we use a unique vendor in the access. It's Cisco 9532 and 9548 switch with 100 gig backhaul, so we use them also to distribute multicast. This is a POP map. You can soon see that. It's a preliminary screen. And the product is Fiber 7, which is 10 and 25 gigabit Ethernet, free choice of router. So a NERD-compatible product. It offers also multicast TV. We also have a EC7, which is plug and play for anyone with no clue. And we got also some medals. Yeah, you can look those boring slides later. Marketing slides. There's always one marketing slide. So we do some multicast, and that's why I'm here. And I proposed this discussion or this BOF about a year or two ago. I don't remember exactly. And lucky us, the DE-CIX people, took over the organization. A quick word about our multicast ingest network. This is completely separate from the main network. Why is this the case? Because multicast is a bit difficult to handle, so I'd rather have these on separate boxes. And if we do something wrong with the main network, not everybody is affected, because basically multicast, as you know, is very is basically the first thing in the chain, in the supply chain. So we have the two switches we usually use for the FTTH. We took them away from the delivery and use them as multicast ingest network. They're just two in two different locations with redundant passes, and all the multicast feeds are delivered there. And so you can see there is a redundant SRG. These are the 7 channels of the Swiss television. 7, of course, two German, 2 French, and 2 Italian-speaking channels. And then we use the Cisco DCMs, the 9902, basically for nothing else than address translation. So these are basically the multicast NAT boxes. I think there's some other purpose also, but mainly it's address translation. And what the customer gets is they can actually download our multicast playlist and use whatever device they want to use it to play these streams. We also have Apple TV and Google Android TV app, which is compatible to use this multicast, to play these multicast streams, the live TV. Quick word on the technology. With an Apple TV, it's basically the VLC engine we use there. And there was actually a topic about a couple of years back that some channels, some private German channels, they require encrypted transmission of live TV, which is silly in my opinion, but anyway. So we did a bit of research work in terms of how to encrypt multicast. So that's DRM. It's mainly it was actually a bachelor thesis of the ZHW, Zürcher Hochschule für angewandte Wissenschaften. That's a university in Winterthur, and one of our former employees was studying there and working part-time in our TV team. And he actually addressed this with 2 colleagues. So there's the concept is available on GitHub. So if you ever think of doing some open source DRM stuff or whatever, then that might be a hook to start. That's about it. This is me, and I hope we can have a lively discussion and bring multicast, which is claimed to be dead, alive again. Thank you.
So our next speaker is Flavio Luciani. Flavio is the CTO of NAMEX, the Roma Internet Exchange Point. NAMEX connects more than 230 members at multiple cities in Italy and the Balkans. At the same time, he's the local host of this RIPE meeting, which deserves a round of applause on its own, I guess. So we prepared this presentation sort of together, and this also reflects the views of DE-CIX. So, Flavio.
Yeah, thank you so much. I would like to say also thanks to my colleagues that they are here about, yeah, I work for this RIPE meeting, but probably they did as much as work as possible and not myself. So thank you very much, Matthias, for this introduction. Yeah, my name is Flavio Rugiani and I work for NAMEX, the local exchange. This is a really brief presentation about the IXP's perspective on multicast, and in general, I would like to underline, and I would like to, I would like to underline what IXPs in general can do in terms of support and facilitate network operators about the adoption of multicast. Just a very brief introduction of this presentation, and I would like to also give you some insight about what we usually see at internet exchange points, because typically we see at internet peaks of traffic, and they are related to especially events such as software updates and game releases, and very recently also live streaming applications. And I would like to give you my personal opinion about live streaming application, because I think that we have to see live streaming closer in this period. Just to give you an idea, in Italy in 2021, there was a revolution because DAZN, the broadcaster, won the broadcasting rights for the transmission of the Italian major football championship, so the Serie A, with 7 matches, football matches in exclusive out of 10. And it was a revolution because we moved from a satellite distribution to live streaming on the internet. And not only, because also we have Amazon Prime Video. Amazon Prime Video broadcast the UEFA Champions League with several matches in exclusive on Wednesday. And, you know, these events have a huge impact in terms of load on the network. And my question is, just to feed the discussion later, can be, for example, live streaming one of the driver to let me say to support the adoption of multicast for network operators? Just open mic and we can discuss later. We did something many years ago. Probably at that time I was at the elementary school, but some of my colleagues here can remember, because more than 15 years ago in NAMEX, we Marco Ditri probably reminded that time, but we provided a multicast VLAN under the request of some of our members, and it was experimentation. We suspended after, I don't know, a couple of years, 3 years, the experimentation, because probably it wasn't the right time, and because there wasn't a need and benefit to do so. But now times probably have changed, because as I mentioned before, we have probably several use cases that can support the adoption of multicast among network operators. But have times really changed? I don't know, because if you look for the word multicast on PeerInDB, you will get just one result, the LONA multicast peering VLAN with 0 peers. So no interest, no volume, because we are not used to use PeerInDB for multicast. I don't know. Also, we can, just to feed the discussion later, this is something for the discussion. Let me just say that, I don't know, probably exchanges are not so we are not the main actor in this game, but we exchanges, at least NAMEX and DE-CIX, at least Flavio and Matthias and the other guys from DE-CIX and NAMEX, we would support new attempts at multicast VLAN. But before doing that, we would like to hear from you. We would like to hear that there are demands among network operators, all, I mean, both access providers and content providers. And, you know, probably this is the right place where we can discuss it. And we would like to hear from you if we can do something. Probably we are now at the early stage of multicast, at early stage of live streaming and other applications, but we can start now to be prepared and ready so in the future. And thank you very much. This is all by me.
So the last speaker in this little row on perspectives on multicast is Viljana Ivanova. Viljana is the engineering director of Z2. Z2 provides IPTV services for television channels and video on demand content in the German, Austrian, and Switzerland region. Initially, Z2 was founded to stream the 2006 FIFA World Cup. And I tried to look up what the current number of users is. I've only found very old numbers. So in 2016, they already had 2 million users for live streaming. But maybe Viljana will update us on that number in her talk. I don't know. But I would think that today it's probably a lot more. Viljana is joining us remotely today, and I'm very grateful for that. And well, Viljana, the floor is yours.
Hi, I hope you can hear me good. Okay, good. So as already presented, the tool has actually two products. One is OTT in the DACH region, so Germany, Switzerland, and Austria, where we do have our own live TV product that users can download on any smart device that we have nowadays and watch live TV with the features of restart, recordings, catch up, and so on. And we also have an IPTV product that's white labeled for operators, telecoms, like for example, in Germany, 1&1 is our customer. So we built the whole IPTV solution for them, or Air in Ireland, or Salt in Switzerland, and that's unlimited in the world. So whenever we have a customer. What is our network currently looking at? We do everything in-house. So we have our own headends where we have more than 30 satellite dishes with the reception of many channels that are still not delivered directly from the playouts. We have at the moment more than 1,300 channels with multiple sources, which means minimum 2 per channel. So that's around 3,000 signals flying around in our network. User-wise, so on the OTT product, so that the one in Germany, Switzerland, and Austria, we have around 6 million active users, but the peak that we see is between 500,000 and 600,000 users in the evening. So it's still quite a lot, and we operate our own CDN for that delivery. So how does our multicast work? We do multicast only for our acquisition and the backend. So as I said already, we have our headends where we have DVB-S or DVB-T ingest. Then we have also multiple direct IP multicast ingest, luckily from the playouts directly. And we have also internet ingest like HOS or SRT for whoever is knows the setup. I can't switch. Yeah, now I could, sorry. And we collect all those ingests, all those channel sources, and then we encode them into IP multicast to transport them to the different video backends. We have 2 video backends, and we have 5 main acquisition POPs at the moment. So every signal goes to both backends for delivery, and this is fully multicast delivery until the video backends. But we use only level 2 multicast delivery that is isolated from the rest of the network in VLANs, and it's dedicated only for that. And then our product runs fully on unicast, because of multiple reasons. So when we started, we had only the OTT product and it was focused on mobile devices. So obviously the solution then was supposed to be unicast. But with the time also and the introduction of the different services like non-Wi-Fi traffic on top, that's catch up for recordings or pause or restart, and even VOD nowadays. So VOD is not our main business, but we do have some, as everyone. We needed to keep the unicast, and we can already see that this traffic is growing more and more. So we built everything on HTTP-based adaptive video delivery. We built direct network peerings, and we can also stream over the open internet for most of the users if we don't reach them via network peering. And the unicast gives us better functionality in this ways. As I said, also the non-Wi-Fi traffic is much more. 35% of our traffic at the moment is really non-Wi-Fi, and I don't mean VOD, I mean really like people who skip the ads or pause or restart or just want to watch the Sunday show on Monday because they couldn't catch it then. When we started also mobile devices, and now it's still the case, we're not supporting multicast, so that's a big chunk of our users. Like a lot of people commuting are using the product, the OTT product. And on big screen, when we built the solution also for our telecom providers on our B2B business, then we limit them only to the setup box that the provider gives you. While we see much better performance now on an Apple TV, we built an Apple TV as an operator app. We were the first one actually in Europe to do it, and that would only work on unicast solution. And then we can also have like the smart TV applications, Fire TV, Chromecast, and whatever else comes on the market. So that's why we do keep everything in unicast. And that's how our solution works. And thank you for having me here in this presentation. I'm curious to hear what everyone else has.
So thank you for all the speakers for providing their perspective. The run-up to this BOF was very short, so it was just 1 week. So Vilania went the extra mile to present this here remotely. Thank you for that. And I think we can now open the discussion phase. As we have had the presentations before that, I could prepare a few discussion items that might be of interest. You can see them here. And besides that, we do have a survey that you might take. It lasts about 8 minutes. And it's just to catch your opinion on the whole topic. So I would be very grateful if you could fill that in, because it allows us to gauge the interest of the community into this topic. So, please.
Marco Ditri, CWeb and also MINAP. I'll start with an historical perspective on the Namex multicast LAN experiment. It failed basically because there were no access networks. At the time, the access market in Italy was much more consolidated. There were most of the users were shared among a very small number of very large operators, and they were very clear in saying that they wanted to be paid for the privilege of sending multicast traffic to their own customers. So this went nowhere. We connected because at the time I was interested in multicast. I also had multicast transit, but we are an hosting and cloud infrastructure provider, so in some way a content provider. We did not actually have any real content. Anyway, there were just no eyeballs, so there was no point in continuing the experiment. From the IXP point of view, I will just say that as far as I know, supporting multicast at an IXP requires PIM snooping and whatever is needed for IPv6. So it requires advanced switches that maybe not all exchanges use. Thank you.
Thank you for your opinion.
Hi, Gerd Döring. I have almost as many gray hair as Marco. And I have been part of the multicast LAN at DE-CIX. So you had one.
Well, probably I wasn't around at the time.
You might have been born. It was like about 20 years ago.
You're not that old, Gerd.
I am. I'm 52.
But experienced.
That was really when we thought multicast was the solution to everything. And we had been providing audio streaming for one of the Bavarian radio stations. We still do. And they basically provide for about 2/3 of our outgoing bandwidth. So it would be really, really, really nice to just send one stream every direction. It would reduce our bill with 3320 significantly. The thing is that what we learned at that time and why we decided at some point to completely turn off multicast routing in our network was the total lack of debuggability. The moment the usage was very, very low. So about once a month, somebody came and said, I tried to listen to your multicast stuff and my local ISP says it should work, but I cannot hear anything. Then you do unicast traceroute and find out that there's 3 different ASs in between and they all claim to do multicast. And one of them has again turned up a link and forgot to turn on PIN. So you have a black hole somewhere in between, which you cannot debug without actually really knowable engineers in the middle AS. There's no real tool that tells you anything beyond, yes, black hole there. No, yes, black hole on the way, but not where. So with the very small take up we had back then, the cost benefit relationship absolutely made no sense. So this is why we discontinued our multicast engagement. I still think it makes very much sense for this sort of real-time streaming at a soccer game or whatever, or an audio session. But there's a technical gap to be filled to be able to actually trace and debug all this.
Okay, that's a very valuable comment because that's also something that I have on this discussion item slide here. Is multicast feature complete for the use cases that you have? And I guess your answer at this point is no, it isn't, right?
The debuggability was, I haven't followed the development in the last 10 years, but back then it wasn't.
Okay, thank you.
Hello, my name is Marco Marletta. I work for an Italian network. I am here to bring my experience to the people here. I have worked on multicast since the year 2000. So it's 23 years now that I started. So is there anyone before? Or I'm the older one here? No? No? More than 2000? Earlier than 2000? Wow, fantastic. As a multicast, okay. Wow, fantastic. So I started working in 2000 and my first job was let's bring multicast into the network. And in 2001, I had a working multicast environment in my network, which was actually a special kind of multicast network, which was it was an internet multicast. It was not just send data from a source and receive data on the same network, but send data to everywhere in the world or receive data from anywhere in the world. Of course, this was a specific part of the internet. It was only the research network. So it was what at the time it was called the M-boon. So basically we started deploying all the stuff, SSM, ASM, everything, many protocols, lots of troubles because the implementation of the control plane was not working as it was meant for.
And of course, this was working somehow for many years with little or no use at all. So basically, we had a working implementation. We started also developing tools to monitor this kind of implementation, but no one was using it. Then suddenly in 2018, there was a research institution which is called UMETSAT, sorry, which launched a project called UMETCAST. It was 2018 or roughly, yes, roughly, yes. So they launched this project and they started sending scientific data coming from satellite over research networks using multicast. And it was like waking up from being asleep. Okay, so we started seeing streams, we started seeing active states, active multicast states on routers, which was fantastic. Wow. But of course, it was also a responsibility. So now we need to make it work. If we change something in the network, it still needs to work. Okay, and this is the new challenge for the future. So what I would like to emphasize on my experience is that I've seen some implementation talking about how they send and receive data on the same network. But I have never seen an internet-wide multicast implementation, which is what I would like to see for the future. There has been some proposal, which I've seen, which was multicast tunneling, I think it was a draft called automatic multicast tunneling, yes, which was had also a nice surname, which was multicast to the grandma. So how to bring the multicast up to grandma house. And this is, I think, the real challenge for the future, how to make multicast work across network boundaries, not just inside the network boundary. That's it.
Thank you so much for that. So I like this very specific use case. I was also wondering whether anyone out there is using multicast for something else than live streaming. That's a very nice use case, even though it's a very specific one, right? Thank you for sharing your opinion.
Yeah, Maria, developer of BERT, I'd like to say that we haven't implemented almost anything from multicast. And I must admit that those RFCs are quite hard to read and hard to comprehend. So it's not so easy to take something from the multicast world and implement it. Let's aside that there are several versions of the PIM protocols. So my basic question is whether it's even needed inside BERT, mostly from the point of view of IXPs who are using BERT quite heavily. And second, if there is a need, which protocol, for example, whether it's which kind of PIM it should be or which other protocol should we implement, because looking into the RFCs and implementing all of them would take us like 3 years, and I'm very underestimating this. So if anybody from the IXP world can do a assessment, or I can help with that and do this discussion, please reach out to us. We will try to do our best. Thank you.
So maybe I can comment to that as an IXP person, even though I'm chairing this BOF. So actually, if I think about an architecture, I don't think a BERT would be too much involved in that, because as stated beforehand, probably it would be something like PIM snooping on the IXP platform. But of course, probably we have to talk about, if we talk about global multicast on an internet-wide scale, whether we need BERT to redistribute multicast space, right? But that would be on a BGP level from my perspective. And that would probably also require changes in address policy and the like.
Hello there. I'm Tom Hill. I work for British Telecom. So we talk a lot about multicast, but a lot of this is also personal opinion, so I should point that out. There are obviously a number of different TV mechanisms for distributing live content at the moment, and certainly we've seen some examples of multicast in use, and that's great. We do have this looming problem of those other mediums not working anymore. Either the satellites are going to fall out of the sky at some point and not be replaced, or the DVB frequencies will be stolen for 5G, 6G, whatever. So someone's got their eyes on all this bandwidth, right, and all of this stuff, and the money involved. So whilst I believe absolutely that there is a really valuable position here for a working group to help collate multicast requirements across ISPs and across countries, massively important, that would be brilliant. We do need to think a little bit further outside of network protocols. There are so many external factors to this problem, and I would hasten to point out, and I think that's why it's never taken off in the tens of years that folk have been working on it. So I think the first and foremost thing that we have to concentrate on is the end user and how they're going to consume these services. Certainly in the United Kingdom, we have something along the lines of, obviously we implement DVB-T standards, but we have this association called Freeview, and they produce standards for television boxes that are compatible with either what we call FreeSat, which is DVB-S or DVB-S2, Freeview, DVB-T, DVB-T2. And when you buy a box in the UK to put under your television, a set-top box, it will probably come with one of those things written on it. Where's the standard for multicast? Right? But that's the kind of thing that we need to be thinking about in terms of how we get these things into homes. It's just an example, probably not the best example, but yes, this could be a brilliant thing for the industry to start working on, particularly as we see those other mechanisms, those mediums failing or going away. But we do need to think a bit further outside of network architecture, quite significantly.
Forgive my ignorance, but does British Telecom also provide mobile services? Because I would really be interested in a perspective on that, because that's also the end user problem that you're talking about, right? So
we do. We own everything everywhere, EE, which is a mobile.
That's a tough claim, but
we own everything everywhere. Yes, I know, that's a brilliant one. It's like having an extreme meeting, extreme networks. Yes, we own EE, and it's quite integrated into BT now. So we have a single converged core with a single internet platform, and then we have radio, mobile core, and broadband network. And this is a result of tons of years of extra hard work and all sorts of things. Getting multicast ingested just into the network from third parties, it's the collaboration piece, I think, is the hardest thing to get around, right? It's to some degree it's chicken and egg. Do you build it and they will come, or do you force them into doing it in some other fashion? It's quite difficult to get there. There is a lot of industry collaboration required across all parties, and of course you've had 3 different perspectives, and that's great. This is why I say that a working group in this particular forum would be fantastic, but there are other things that we have to consider outside of our usual realm that I think are very, very valid.
I have a question with a tiny bit of self-interest. So would you join an IXP multicast peering LAN as a big incumbent provider?
I couldn't say that for sure at the moment.
But you would consider it?
Put it this way, right? Why did we build IXPs in the first place? To reduce the burden of having to send traffic all over the place, over to the US and back, or to a different country. If IXPs can reduce the burden for everyone, then I assume it would be a natural benefit to a multicast internet.
Okay. So does Melania want to say something?
It's Rudolph.
Yeah, Flavio, there's a question in the online queue. So sorry, we had a bit of trouble setting up the online queue. We will come back to you once we have this settled. So yeah, thank you very much for your opinion. And okay, I think next one, please.
Hey, Sylvan here from Open Factory, or owned by VT, as I just learned. So with regards to the use cases, I have spent several years in a TV head end learning about all the weird effects of spanning tree on multicast networks, especially. What I see as a use case, because most of the TV content, apart from the old times of, I mean, back in the day we had Northern Ghost, who still remembers that used multicast on my network. It's often that you get commercially transported TV channels, so I'm not sure that the content provider who operate the headends are too much willing to give their traffic out for free on an IXP where they can barely control who actually subscribes to the traffic, because I think that's fairly difficult to control. What would be an interesting use case would probably all like the public TV stations, which would be fairly interested getting their channels easier over to subscribers. A personal challenge I'm following up for many, many years is how do we get people to adopt glob space? Because I think a lot of people forgot about that. If you have a 16-bit ASN, you have your own /24 subnet for multicast. And I think that would be something that should be also part of getting proper route objects and other things. There's no way to get a route object for my glob space in RIPE database, even though my ASN is in RIPE database. So that's also something we should change. And yes, I would join and I would at least consume channels, even though I'm not able to bring in channels.
Maybe is there someone from RIPE in the room to which we can relay the address space question? Because in preparation of this both, I was quickly grabbing through the RIPE policy and I could find multicast on a single line, and this whole policy and essentially says we don't handle multicast. So is there any mechanism in RIPE to handle multicast addresses? I don't think so, actually.
As far as I understand, no. There's this glob space, which means 233.uras number./24, but that's outside RIPE because that's just IETF. And if you have a 32-bit AS number, you're lost. But RIPE has nothing.
256 addresses. Yes. For each operator, which I don't see.
So before going with the next person in the microphone queue, I would put in someone from the online queue. So if that's fine for you. So I don't know who it was. William, yeah? Okay. So multicast definitely helps reduce peaks during football championships, for example, but we easily compensate that with cache servers that are positioned based on the telecom network and needs. And for non-live content, you still need to have the caches anyway. And this way, you do not need to support two protocols. The overall advantage to save traffic in a fiber optic world is less than the complexity of the network one needs to support. Also, multicast ABR is not that flawless to do. And then when the user home setup is bad, then it just does not work.
So that's not what I wanted to comment, actually. It was on the last thing about the multicast delivery of the channels from the playout to the distributor, like we do, for example. That definitely multicast is the best option. And we also do it. We aggregate all the 2000 channels that we have, for example, and we can deliver it to someone in multicast. And I can see that happening in an IXP where they are the aggregator of those channels. And I just tell them, hey, I have the content rights for Discovery, just enable that multicast for me. As for the IP addresses that are not regulated by RIPE, for us, that's kind of a big problem because on every ingest that we do from the playouts directly, we do need to make sure that we rewrite them with our own space so that that's not duplicated and we don't have issues.
Thomas Schmid, also working for National Research Network in Germany. Yeah, we do multicast also for a long time now, and I just wanted to follow up to what Marco was saying, that when we set up this humidcast infrastructure, monitoring was a key component of it. And in the inter-domain case, of course, monitoring requires multiple parties. And as was already mentioned, we easily end up in having multiple topologies that you lose the fate sharing of IP forwarding when it comes to multicast, which makes things really difficult. And this might require, of course, a higher or another level of working together between different ISPs in order to deliver an end-to-end service for multicast services. And yeah, that's one thing. And then AMT multicast tunneling, yeah, it reminds somehow of IPv6 tunneling back in the days. I don't know if this is a good way to go when you think of Torito 64 tunnels and so on and so forth. But I'm curious, AMT, I haven't heard much of it lately. I don't know what the status is. And so I also have the question to the audience here. What is the status of AMT? I'm not sure. Maybe somebody can answer or comment on that one.
Yeah, I'm not sure about that either, but would be interested as well.
Hello, this is Luciano Venuto. I work for TIM. We have an experience, as stated before, delivering multicast of the Premier League Serie A in Italy for football. We deliver each match, all the, I don't know, 6 or 7 football matches are delivered via multicast. The main thing I want to say about our experience is that multicast is useful for the operator because it helps, it's elementary, but helps your network to not explode, because we perform multicast ABR, we have each match transmitted in several coding, which is one audio channel. The main issues I can see that is that it is useful, but the main thing we have to say about multicast is you have to have multicast to the end customers on the access network. Is it PON or VDSL or GPON or anything else? So the most useful thing, the best effort is to sensibilize, to have access network equipment available for multicast. It is not in the 100% of the access networks. For example, in the radio networks, in the cellular network, 5G, 4G, 5G, there's to be an effort to implement multicast also in mobile network, I think. And the other thing is to have more compatibility and interoperability with the terminals and set-top boxes. Or you have to let to be the final terminal unicast, for example, and have the conversion, something in your network, in your home network, in some part on the network that makes a conversion from multicast to unicast if your terminal does not support unicast, the multicast, excuse me. And for the access network, to have the full compatibility for the last version of protocols. For example, we have several boxes which do not implement IGMP version 3, so they are not available for PIM SSM. These are not so theoretical problems, but they are practical. If you can use PIM SSM, you can have more relaxed in the management of multicast address and so on. But what I can say that the development of multicast in also not so linked to an application, for example, not multicast for football, but also for dynamic events, for example, the presentation of the new releases of the console and so on. The network could be able to switch from multicast, from unicast to multicast dynamically. So if I am at home, I'm seeing an event on television, perhaps you have to be the intelligence at home to switch from unicast to multicast independently from the terminal. So you can make the network more free from bandwidth occupation. But I think we are still at the beginning of this adventure. we had some problems to implement it in the customer user. We have a strict interaction between unicast and multicast. So if a customer has the set-top box able to see multicast, he will have his content in multicast, but it is transparent to him. You just select what you want to see, and the network decides for you, because multicast is more useful for operator best than the customer or the content provider, I think. Thank you.
Yeah, thank you. So before moving on to the next speaker, you still have time to fill in the survey within the session. So maybe I'd like to encourage you to do so if you haven't done so yet. So next, please.
Okay, hi, this is Marian from NixCZ. I just small comment here. We still run multicast on roughly 30 ports in our infrastructure, but I haven't seen any request past 2 or 3 years. So the infrastructure is there. We still run it historically, but there is no interest from the operators.
Is it no interest from the operators or no interest from the content providers?
Both. Because we're connecting them together. Yeah. They are distributing these live streams through the infrastructure. So, well, that's it. Thank you.
Okay, thank you.
Chris, DE-CIX. So I can hardly wrap my head around it, because actually we have discussions which go on for like years, whether we need it or not. And some suggest, hey, I would love to see that implemented on the one hand side. On the other hand side, like the really large, I mean, we had really cool statements from Tim and BT say, yeah, well, the devil is in the detail, and let's look. But I believe what would be really the next step to crack this, that we really have someone standing up and saying, hey, really, I want to explore this, because I believe the IXPs, and Flavio made this also pretty clear, for us it's rather easy to kick this off and to get started. And as we just heard before, some IXPs even operate it still, and there's still no demand. So I believe without having really like either eyeball side now or after the meeting, going to Matthias or to someone else from DE-CIX, Namex, or some of the IXPs, like really cheering for this, championing this idea and saying, okay, let's start it over again. I need it as a content provider, or I need it as an ISP. And we're happy to start with a pair, right? So with one content provider who's really interested and one ISP is really interested. Well, that is sort of at least the crucial mass that we actually need. And yeah, I'm somewhat failed to really see it here in this room. That's the summary, right? A lot of technical reasons, but no one also went down in direction of what are the commercials, right? So as an ISP, how can I save money? Okay, I understand traffic, yeah, but is there more to it? Or as an ISP, is there another monetization strategy actually that I could pull out?
Yeah, there is a Flavio Luciani from Namex. There is a question from Mitko, from Zubair Sediki, probably for Luciano, for Tim. And the question is, I was wondering how was the user experience, the latency, video resolution during peak hours, watching live streaming events using multicast services. Any idea on that? Yeah, see.
Our customer experience is pretty good, because the multicast, as you can see, is not growing the bit rate on the network. So during peak level, you have something related to unicast, which is, can be, you can have problems. But as regards multicast, we have also an increasing of quality level. So the prioritization on the network for multicast packets is also an help for us. But the other thing is that at now, multicast is not the only solution to provide a good user experience, because we try to prevent congestion by dimensioning our network links in the way that you can see you can have the match also if you a large number of customers are in unicast. So network is very good, how to say, very robust for this. But multicast, in my experience, is a very simple protocol. I think that multicast is like whether you open, you close. There's not as very low problems that are, I think, more related with unicast part, because our multicast is not really independent from unicast. In the stream you have from the match. Sometimes I'm not expert in this. You need to receive some packets from your provider in unicast, and perhaps the problem could be in this interaction from unicast and multicast. But if a stream is just like multicast, we should have no problem, because multicast is one stream for 1 or 2 or 3 streams for each box, independently from the number of customers. And this is the very strength of multicast. So the user experience is good, and we think that it will be better if the number of customers which use multicast will increase. This is, I think, very simple to understand.
Okay, thank you. There. Yeah. Can we get? Okay,
should I continue until?
Yeah, maybe
okay.
you continue until we get that sorted out. Thank you.
Freddy from Unit 7 again. I think the question was raised before, is there really a need? So I think to conclude all this, we need basically 3 things. We need an IXP, which provides a multicast VLAN, maybe without extra costs to facilitate it. That's probably the easiest part. And then the most difficult part, and I think we really need to address this, is the addressing. What was it? Global 233 something? Yeah. I mean, 256 addresses per ISP is not enough. Liliana said before she has some 1,300 channels in her network. And the biggest issue, she said, was renumbering. And I also mentioned this, renumbering really sucks. So we need something, a system which gives, I don't know, a /20, a /19 to those participating ISPs in a multicast VLAN to pick up channels, to offer channels. And otherwise, this is not going to work. So the layer 2 part is one thing, but I think we need to have a proper addressing scheme. Otherwise, it's not going to work, because everybody addresses whatever he thinks is good. And yes, I think it's also an option for long tail channels, for regional channels, which could be for create some interest in other regions, channels which are not on satellite. And if they could be picked up by ISPs in an exchange, that would be a widening of the offering of the TV selection.
Thank you. Freddie, I think you're in for writing a policy proposal for the address policy working group.
Totally agree.
You got volunteered. Okay, we have someone in the online queue. Okay, then we go ahead. Okay, then please go ahead.
Thank you, Flavio. Stefan, Open7. I've done some work 3 years ago, last time with video encoding, and we have also done tests, and the Institute has done some tests there. And I have MBone, some people maybe know this, and RIPE has this stuff also discussed 20 years ago. At the end, why is multicast dead? It's dead because nobody uses it at the end boxes. That's the simple solution. And
I like your first question, multicast use cases. What's your case? So where's the case? NTP I've seen. Nice idea. Maybe that could be something, a killer application, but I don't think so. So we are living in a time where we stop having linear television. We have non-linear television. In Germany, the price structure for, I think, more than 98% of all households are connected to a cable network. So actually, DVB makes no sense anymore. I think one of the local operators in Munich already switched it off because nobody's looking DVBs. And then they had done some really huge mistakes, but not going into detail, but of course that's wireless stuff. In the end, non-linear television cannot work together with multicast. And the problem with multicast always is that if you have ever tried 20 years ago multicast with a box, you press a button and then there's a picture. With the next channel, and then you have a picture. And people want to have switch. They want to go flip through the channels. And you can only accomplish it, and it was, I think, somebody already mentioned it, by combining unicast and multicast. But this is a complicated technology. You need special boxes for this. You can support this and all these things. So if you want to have it really cheap, you do unicast. As simple as that. And most of the people, and I would say it's not prophetic to say that 90% of the people will go non-linear in the next years. So please show me a multicast application, a multicast service, which really would give a reason for IXPs to put effort, engineering power, money into doing things, and not mentioning all the problems with the address space and the renumbering Freddie has mentioned actually. Thank you.
Thank you. So we're running out of time, so I would like to close the mic after the next two speakers, right?
Yeah, just a short, naive question. Do we need, with the addressing schema, to keep IPv4 itself? Don't we have IPv6 with that FF/8? I forgot to state my name and affiliation. I'm Maria, an internet IPv6 terrorist.
Hello, I'm Marcus. I'm speaking for myself. Multicast is heavily used by financial networks. I think there's a lot I could learn from them. I've worked in this industry like for the past 7 years. Yeah, basically doing multicast every day. Yeah, on the technical side, I believe there's a lot of things a lot of ideas we could borrow from these networks and try to implement on the.
So financial data is a use case that we hadn't had so far. So
yeah, especially like financial exchanges, high frequency trading companies. Yeah. They do a lot of multicast.
Okay, thank you. So last comment.
Very quick. At least for the Italian market, we are wasting our time if we expect to use multicast to measure each single viewer, or else they won't be able to sell advertisements. So we need to solve that if we want to use multicast for TV.
Okay. Yeah. Can you hear us?
Can you hear me? Yeah, if you can hear me. Oh yeah, I hear the echo through the room. Sorry for that. No, I wanted, so there were a lot of interesting comments made today. So I've been starting to work on multicast as an operator in AT research until '99, when I moved over to vendors and worked with a lot of different multicast deployments over the time. And so I can, reflect on many of the things that were said here. And it would certainly be a lot of fun to have a mailing list, at least to refresh this discussion and help people understand are that we have. And obviously the full end-to-end multicast over the internet is still the biggest question mark use case, right? But I think the one thing to remember is that multicast is successfully used for at least part of the distribution chain of a lot of content. I mean, in many service providers still uses multicast up to the end caches, and whether or not that is meant to be in scope or not is for you to decide. But I wouldn't say that multicast is dead. It just never, was visible as an end-to-end service over the internet. And the result, sure, how many of you are operating those, and in other applications in enterprises, of course.
Thank you. So I think that was the last comment. Is there one left? Ah, okay.
Yeah, hi. Rudolf from the Netherlands. I've been discussing multicast since 2001. Can you guys hear me? Yes, good. So even then, it was hard to find a business case, in part because the promise is it saves traffic, but really, how much capacity do you need? In India, they just did the Cricket World Cup for 59 million people over the mobile network, doing unicast, and it worked. If you want to do a unicast football, yes, it's a couple of terabit, but if you put the caches deep enough in the network, and latest caches do 500 gig to a terabit per cache, you can easily handle 1 million customers per terabit cache. And who here really has problems handling 40 terabit of traffic in an ISP telco network? You shouldn't, because the boxes are bigger than that. And this has been the case for the last 25 years. There are Internet Protocol Journal articles from 2001 and 99 about why multicast isn't successful. And it's because too many engineers have been building too much capacity too fast. And it causes too much trouble. So yes, there are special use cases, but across the internet, it's too hard and doesn't save enough money.
Okay. So this was the last comment, I guess. So thank you for participating in this BOF meeting. We have heard a very wide range of opinions on this topic, and it was very interesting. I think we'll find a way to share the results of the survey some way or the other. And yeah, have fun on the social. Thank you for participating.